Test, test. Pardon me? Okay, I can just so I can just go to the stage, introduce the speaker, and then I come back. Okay, and for question and answer, it's the same thing. Okay, the question and answer. Okay. All right, hi everyone, good morning, and welcome coming back for the third day of the workshop. For this morning, we will have a very exciting session of deep learning sparsity with system co-design. And our first speaker will be Professor Gita Gutiniak from LMU Munich. So with that, let's welcome Gita.
Yeah, thank you so very much for the introduction, and also thank you very much for the organizers for the invitation. It's really a great pleasure and honor for me to give a talk here. I already enjoyed very much this workshop, so I think it's a great opportunity to, in particular after the pandemic, reconvene, meet colleagues, talk about exciting topics. So thanks so much also for inviting me. Now, in my talk, I would like to talk a bit about reliability of AI, which I think is one major question and one major problem these days worldwide, because it's known that AI technology is not at that level of reliability which we require. And according to the topic of this workshop, I would like to also reveal in certain directions how this intertwines with low dimensionality. So why low dimensionality can also help for reliability, and then, in particular in the second part of the talk, also talk about what limitations AI has these days, because I think that's something which is often overlooked. In particular, concerning the fact that we train neural networks on digital hardware. And so what we will see is that there are fundamental limitations and that we might need to think about going beyond classical hardware to maybe also then analog hardware. So that's the plan for the morning. Not for the morning, but for my talk. Okay, so I think, I don't need to tell you how important AI is these days. We see, all of our public lives is intertwined with AI approaches already, self-driving cars, telecommunication, then also think of, for instance, legal issues, which is in many countries already, let's say, pre-decided to a certain extent by AI-based approaches, and then the whole medical sector, which, as we know during the pandemic, unfortunately these days became even more important than it already is. And so from my perspective, and that's also how I came to this area, because originally I was working on imaging sciences, inverse problems. What we saw was when the first wave, or maybe the second wave of deep neural networks hit us, that these methods were extremely successful in various problem settings. So in particular in the area of inverse problems, imaging sciences, this started around 2012, and we already saw and heard beautiful talks in this direction. Many problems were attacked and easily often led to the state of the art. The second area, which was much slower to be embraced, yet also extremely important from my perspective, is the area of solving partial differential equations with neural networks, because there it was first thought, why do we need learning type methods at all? Because the PDE is a rigorous physical model, so it might not make sense to take learning type methods into account. However, what turned out is, in particular, in the high-dimensional regime, these methods are extremely important, and that relates also to the topic of this workshop, because neural networks can sense the underlying low-dimensional structure. And then also, very lately, modeling. So there's this new trend which aims to use AI-based approaches to automatically detect physical laws behind data. And I think that's also a very exciting direction. I would not talk about that, but I think that's something also which we will see more about the next years. But then on the other hand, there were also, concerns about whether AI is reliable, and so there was this interesting incident which you might have heard of. It happened during one of the AI conferences where a researcher, Ali Rahimi, gave a plenary speech. He received an award and gave this plenary speech, and in his speech he claimed that AI has become a form of alchemy. He said researchers do not know why some algorithms work, why others do work, which architecture to choose. So it's a lot of trial and error. So now, certainly from a theoretical side, we are 4 years later. We have done a lot of work There are very exciting results, which you also heard during this workshop. But still, for instance, think of the training algorithms, it's still a lot of trial and error, so I mean, there's a great need for driving this further, because also there are problems, and here is one, for instance, article from BBC News, which says computers can be made to see sea turtle as a gun, and I think it's well known that, for instance, self-driving cars, which react sensitively on traffic signs, can be misled by putting stickers on traffic signs in a particular pattern. So then the car reacts in a different way, maybe takes a wrong turn. And so this is the sensitivity of, for instance, neural networks for modifications, sophisticated modifications of the data. And also there we heard several talks already which discussed aspects of that type. So in general, this is a major problem these days, the lack of reliability of AI technology. And well, I mean, coming from Germany and Europe, there, and this is true also for other countries worldwide, there are now very hard restrictions on getting AI technology approved. So people aim for certifications of AI technology concerning its reliability. And it's still not clear what now a certificate for AI technology is. For instance, I mean, in the European area. So from my perspective, this is actually a really exciting chance also for theoretical foundations, because from my perspective, for deriving understanding, in particular concerning reliability of AI, one has different, let's say, levels of how you can understand AI. There's the heuristical understanding, empirical, and maybe the gold standard is to really drive the theory further to get a deep theoretical and mathematical understanding of AI. And this might then also be a key ingredient for, in the end, deriving certificates for AI technology. So these are all aspects, I think, from my perspective, for reliability, which you need to take into account. So now, from my perspective, I mean, concerning theory, mathematics of AI, there are two main directions. Mathematics for artificial intelligence, so can we derive a profound understanding? Can we ensure reliability? Which aspect does low dimensionality play? And then also using AI for mathematical questions, in particular in the area of imaging sciences, and also, for instance, partial differential equation solver. So let's be a bit more detailed, which directions I deem in general interesting, and we heard already several talks during this workshop which touch some of these directions. There's the area of expressivity, which asks questions like, which approximation capacity do neural networks have? So for instance, Tommy gave a very nice talk also in this direction. There are several areas from mathematics which play a role there. Certainly the learning question, so I train neural networks, does stochastic gradient descent converge? To which extent does it converge? Which local minima are preferred by such algorithms? And also there, a lot of mathematical tools are these days used, also maybe exotic tools like algebraic differential geometry to understand the shape of the minima. Then certainly generalization, maybe the holy grail in a certain sense of theory of AI, or in particular deep neural networks. So can we get success guarantees, particularly on the test data? And so then maybe also one direction which I find personally very exciting. We heard already two talks in this direction. One, for instance, from René, which is explainability. Why did a trained deep neural network reach a certain decision? And so here, the question is, we have a trained neural network, so maybe in René's case, he already pre-designed the neural networks so that it is interpretable, but often we might have a neural network which is not designed that way, and then we want to understand which decision it reached. And then on the other hand, there is AI, let's say, for mathematics, in particular these two directions, which I already said. One is inverse problems, which was one also major topic of this workshop, asking, for instance, questions like how can I combine AI-based approaches maybe with traditional methods, and then in the direction of partial differential equations, where one main question is about high dimensionality and can we sense low dimensional structures. So what I would like to do in this talk is I would like to focus, as said, I mean mainly on reliability aspects, touching upon what one might need for certifications for reliability, but I would like to also, according to the topic of this workshop, always discuss which role the connection of deep neural networks with no low dimensionality plays. And so I would like to start from an application perspective. I would like to touch about those two topics, show you some results which you obtained. And what you will see, hopefully, is that in the first direction, you can improve the performance of neural networks if you prepare the data in a particular way. Namely, you already extract to a certain extent lower dimensional structures. So you prepare the data by, let's say, more traditional methods for the neural network so that the heavy load of the neural network is eased, and that way it doesn't need to do, let's say, the heavy lifting, but the low dimensionality structures are already prepared, and that way you can often significantly improve results. I would like to also touch upon this direction, which was not discussed that much during this workshop, but which I find very important concerning, in particular, this question about low dimensionality, because there I think you can really beautifully see how neural networks can extract the low dimensionality, because there you have a very specific problem setting where you know you have low dimensional structures. This is already in the model, and then you can prove that neural networks can extract that. I will then just very briefly, a few slides, discuss also explainability, which is a general approach to also understand underlying structures, and then in the second part come, as also the title indicates, to limitations, which I think is also very important for understanding reliability of AI, and I think this is something which is often overlooked. There are limitations of, in particular, deep neural networks, since we train this on digital hardware. And so the question is, which impact does it have? And we will see that, in fact, I mean, there might be sometimes serious problems with training neural networks on digital hardware, so we will take a computability viewpoint on that. And we will see that these problems might be resolved if we take the turn to analog hardware, because there we have much more flexibility. And so we see also rigorous theoretical results in this direction. Okay, so that's the plan for today. So let's start with, as I said, understanding a bit how low dimensionality can be an asset if it's prepared by traditional methods for neural networks. And that way also improve reliability, because the traditional methods, we certainly have all guarantees which we want, and that way, in a sense, we have an overall guarantee which we can deduce. So let's start with reviewing just very briefly, because there were already several talks about imaging sciences and inverse problems. So many problems in the area of imaging sciences are an inverse problem. So you have an operator, you have your input data, F, your image, for instance, the operator operates, you have the output G, which is maybe an image where certain parts are taken out, and then you want to invert the operator. So you want to go from this image to this image back, and this is typically done by a version of Tikhonov regularization, which you see here, and which we also saw during several talks. So this term aims to solve the inverse problem as accurately as possible, and then you have an additional, the regularization term, where you can incorporate additional properties of your solution. And one direction sparse regularization. So I think, if I remember correctly, this was not discussed yet in this workshop. So you have a sparsifying representation system. Think, for instance, of John's talk very much in the beginning at the tutorials, a representation system which sparsifies your data, and then you place the L1 norm on, and this you use as a prior information. And so let me show you one of these representation systems, because we will use it later on. Wavefits were already discussed during John's talk, but there are a lot of other methods, and I would like to very briefly touch upon the last, which is also a method very effectively to extract low-dimensional structures of data, and we will use this to prepare the neural network in a particular manner. So this is, I mean, as we all know, the world is compressible. That's also why we have this workshop. We have low-dimensional structures apparent, and wavefits are one great way to actually extract this. So, I mean, you saw these slides many times. So you have the wavefit transform here, and the wavefit image shows that you have a lower dimensional structure underlying, which is indicated by these white areas. So you get good compression rates. However, I mean, in truth, your data, in particular if you are in the area of imaging sciences, they have curvilinear structures. That is their key features. And so the question is whether we can design better systems for then sparsifying, in particular, images of that type. And wavefits are not that great for that, because wavefits are isotropic elements, and so if you would like to analyze lower dimensional structures, here one-dimensional structures, then what you might need are elements which are aligned with the lower dimensional structure themselves. And so this led, for instance, to the introduction of curvelets by Candes and Donohoe, and also what we introduced were shearlets, which are a system which is very much directional based. You see this here, and you have 3 operations. You have one operation to translate those on the image domain. You have one operation to scale it, and then you have also one operation to change its orientation. And so what you can in general show is, so this is the frequency partition of shearlets, or given by shearlets, and what you can see is that for particular model classes of images, so-called cartoon-like functions introduced by Dave Donohoe, these fulfill the optimal compression rate. And so if you're interested, and I was also asked during one of the breaks, I mean, we have a lot of software on that, so you can try things out. Now, we want to use this for imaging sciences, for inverse problems, but let me stop here for a moment, because I said these are systems which sense underlying structures, which are able to detect low dimensionality, and in fact, let me just review one a bit older result in this direction. What one could show, or what we could show, is that deep neural networks are in fact able to achieve optimal approximation rates of all affine systems combined. So no matter which affine systems you take, wavelets, shearlets, curvelets, and so on, neural networks are as good as those to, in a sense, give or sense the underlying structure. And not going too much into the details, basically what this result shows is that you can mimic what people did in classical approximation theory now with neural networks. So let me just very briefly discuss this slide, as said, not going into the details. So typically, I mean, you have a class of functions, let's say cartoon-like functions, whatever you want. You have a representation system, say shearlets in this case, and classical approximation theory now aims to the following. We take an element out of our class, we approximate it by linear combinations. This gives me an error, and then I'm interested in, if I let the number of elements go to infinity, how fast does it converge? And this is this gamma. So this gives me the approximation rate, and now I can do similar things with neural networks. So instead of here taking a linear combination, I can take neural networks of a certain complexity, and I can show that neural networks then achieve basically the same approximation rate. So this shows that neural networks are able to sense underlying structures, low-dimensional structures, as good as all affine systems which we have worked on before. Okay, so let's also now take a look at whether this, what I just said, works numerically. And if you take, for instance, neural networks which are designed in this way, so these are functions from R2 to R, and you see in these compartments you also have functions from R2 to R. And then you train this neural network on a very simple function of this type, curvilinear, where we theoretically know that the best approximation would be by, for instance, shearlets. Then you see that in these compartments the network learns something similar. So in that sense, I mean, neural networks are able to mimic what we have done in approximation theory for a long time, and so this indicates that they are very good, one indication, very good in sensing underlying low-dimensional structures. So now we use this to prepare basically the neural network for the data, and let me just mention that there are many results which aim to combine classical approaches with deep neural networks. So I mean, there are, for instance, ad hoc approaches which first use a neural network, which first reconstruct classically and then use a neural network afterwards. There are approaches which combine neural networks with classical methods by breaking open the algorithm, and we also heard a talk in this direction concerning deep image prior already. So now here I would like to focus on a specific application and show you there how we can use, in particular, shearlets to prepare the neural network in a particular way for these low-dimensional structures which come. So this is an application from CT, from medical imaging. A CT scanner samples the radon transform, as you might know. So we compute line integrals through the human body. This gives me one slice of the sinogram, and then I rotate. And this problem becomes really hard if you cannot sample the 180 degrees. So these are, for instance, true in dental CT, electron tomography, and so on. So there we have problems with reconstructing because, in fact, you have a whole chunk of data missing in this direction. And so the reconstruction you get are really bad. So here you have a 60-degree missing angle. This is your original image. This is a very classical reconstruction, filtered back projection. And then if you do what I just said, sparse regularization with shearlets, it is still, something you really don't want to work with. So what can you do? Now, the first question is, how do you now incorporate these traditional methods to prepare the neural network? And for this, let's take a look at what not really movie, but what I'll show you here. So here you have a 15-degree angle, which you know and you reconstruct. And if you increase the angle, what you observe is that certainly the reconstruction gets better, that's for sure. But also what you observe is that certain directional structures are visible at a very early stage. And so here, so you see this schematically. So for instance, if you sample in this direction, then these singularities you will detect at a very early stage, whereas these will be smeared out. So since you just smear them across the whole image. And so this we can now use. We can phrase this theoretically. We can say that, in fact, you can phrase the problem in such a way that what you need to do is you need to reconstruct a certain part of what's called the wavefront set. So the wavefront set is a mathematical object, and this is what I also said during the panel discussion. We used in these areas micro-local analysis. So this is nothing mysterious. It's the singularity, and at each point assigned the direction in which the singularity occurs. So a wavefront set basically looks like this in phase space. And what we are doing is we are missing a certain part of it now, which we need to reconstruct. And so everything else we can do, for instance, with shearlets, but we know precisely what the neural network has to do and also how we need to prepare the data. So we use shearlets for that because shearlets can identify the wavefront set. And so let me show you the algorithm in this direction. We first just solve very classically the problem with the radon transform as an operator and the shearlet transform as a regularizer here with the L1 norm, which is weighted. We get the bad reconstruction, but then we do another shearlet transform. So again, now we prepare the data for the neural network, and we see that certain parts, certain coefficients, so inner products of my reconstruction F star with shearlet coefficients is almost equal to 0. This is where we are missing data, and the others are reliable and perfect. So then we only reconstruct and learn those, and the others we don't touch. So what we do is we now train a neural network to get these as an input and reconstruct these missing coefficients, and then we combine both. And so if you do it that way, so surgically just using the neural network for what the classical method cannot do otherwise, and also preparing the data that way, so helping the neural network detecting the underlying low-dimension structure, we get reconstructions like this. So this is the traditional reconstruction. This is one of the methods which trains the neural network end-to-end, and then if you combine, let's say, both, so you use the classical methods together with the neural network in the way I discussed, you can get significantly better reconstructions. And you can use this general conceptual approach also for other tasks. For instance, here, this is a very classical task, detecting edges with their direction. These are classical methods. This is what a human would do. And so this is what we can do by, again, preparing the data using a shearlet transform in a certain way, and then training the neural network on the already prepared data. And so you see very fine structures here that way, and the color coding indicates which direction the edges have. So the essence or the message here is, if you, in particular in this area, first of all, concerning reliability, it might be good to think about also incorporating traditional methods, because there we have already the deep theoretical framework. And secondly, concerning low dimensionality, if you prepare the data in a nice way for your neural network, it has a much easier job, and the results are significantly improved. So if you have additional knowledge, you can prepare the data, for instance, using a shearlet transform, you will do a much better job. Okay, So this is one direction. The other direction in this theme I would like to show is that neural networks, if we don't prepare the data, they are also still very good in sensing underlying structures. And as said, I mean, we didn't hear a talk about this, so maybe bear with me. But here in this framework concerning partial differential equations, which is basically a very universal theme if you would like to model any, let's say, natural phenomena, there we can really rigorously prove that neural networks are then able to detect underlying low-dimensional structures. So, well, I mean, I hope everybody knows how a PDE looks like. We have a differential operator, we have on our right-hand side, we have the solution U, and typically what people do now since basically 2017, with research taking off, is to use neural networks for approximating the solution. So then the neural network is also incorporated, if you train the neural network, the whole PDE, the operator, and the right-hand side is used and encoded in the training process. Here in this talk, I would like to show you and take you to a bit more general setting, which are parametric PDEs. So parametric PDEs appear in basically any type of science you can think of. So, for instance, design problems where you have a partial differential equation and you have a lot of parameters which can be tuned depending, for instance, on the heat and on the design and so on. So you have partial differential equations of this type. You have here, again, your differential operator. You have the right-hand side. You have your solution. And everything is governed by this y, which are the parameters. And certainly what you want, if you want to design, for instance, an airplane wing, what you would like is for each set of parameters, you would like to compute the solution. So you have here your parameter, and each time you want to compute the solution. And this is a huge problem if, for instance, your parameters are in, let's say, R100. Because then, the curse of dimensionality will beat you, and you have a serious problem because the computational costs might be too high. But this is what people in that area call a multi-query situation. So each time you have a parameter, you want to compute the solution, and you need to do it a lot of times. Okay, and so now you can ask, what can we do with neural networks in this setting? So first, certainly, we need to bring it down on the finite dimensional situation. So what people typically do in this area, they have some high dimensional, finite dimensional space, I don't know, in R, again, 100, let's say, which is where you have an orthonormal basis. So your dimension of your very high dimension but finite space is D, because typically the modeling, as I said on the previous slide, and again discussed during the panel, typically the models are analytic, but if you would like to compute it, you need to go in the finite dimensional setting. And so then, the question is, can a neural network now approximate this map, given a parameter, maybe in RP? Can we compute the coefficients of the solution? So this has a lot of advantages. After we train the neural network, we get a very fast method from each parameter to compute the solution. We also have a very flexible universal approach. And it also shows, and we will see that neural networks are able to basically, are universal in that sense. They are able to handle also situations of this type. And so key questions which you can ask in this direction is, you have an accuracy. Do we find a neural network which approximates the solution up to any degree epsilon for any parameter? And also, how does the complexity depend on P, which is the dimension of the parameters, and capital D, which is the overall dimension? So this question is crucial because this would show that the neural network is able to sense and feel underlying low-dimensional structures. And last but not least, then also how does it perform numerically? So there are certain methods which already do that to a certain extent. They are very complicated. Let me just very briefly discuss this here at this point. So what people before did was, you have your solutions here, for instance, on this continuous structure analytically. Then you bring it down in the finite dimensional situation, so this gives you a certain error. And then in the finite dimensional situation, what people did was you compute for certain parameters, you compute so-called snapshots. And from those, there are then methods somehow to deduce points which are in between, solutions in between for certain parameters. So this is something which people have done. These are called reduced basis methods. So basically you reduce the space and then calculate the solutions this way. But I mean, for several PDEs, this does really not work. It's very complicated. You don't really know how to maybe choose the basis for your low-dimensional space and so on. And with neural networks, I mean, you have a very universal method where you can basically solve all those problems, and the results are actually, I think, quite convincing. So let me just very briefly, maybe not go to all details, show you, the following. So let me just say, at this point, so these reduced basis methods, we have a low-dimensional space. So this dimension is d epsilon, and the low-dimensional space we put in such a way that basically every solution, or we assume it can be put so that every solution, every true solution is approximated up to a certain degree. And so there are methods to show that there exist such spaces, but typically it's a general assumption that there exists a space. So for the neural networks, we don't need to find it, we just know it exists. And this is typically the case. And so then, I mean, usually, I mean, these methods, so let me just not go too much into the details. So the solution coefficients in the low-dimensional space can be explicitly computed. But now with neural networks, we can basically, I mean, I wouldn't say throw this all overboard, but if we now train a neural network to compute this parametric map, what we can show, and maybe let's first take a look here, we can show there exist neural networks of this complexity. And with complexity, I mean the number of non-zero parameters. As you see, I mean, this complexity is extremely nice. This high dimension is only linearly in here, and the dimension of the reduced space is only cubically. So there's no exponential term here, which you would expect if the cross of dimensionally would still be present. So there exist neural networks of such a nice complexity, so that the neural network function approximates my solution up to a certain epsilon for any parameter. So this shows that basically now with neural networks, we can, in a certain sense, solve this universally. And what you also see here, let me just briefly discuss the hypothesis. This is a very natural hypothesis, which basically says there exists a nice low-dimensional space, which lies in that sense that if I compute solutions for it, it approximates my true solutions in a nice way, but you don't need to know it. It just needs to exist, which is usually a general assumption. And there exist neural networks which approximates the forward operators, which is also usually true. So then, I mean, you can drive some numerics to check whether this also happens numerically. Again, I don't want to go too much into the details because, I mean, I guess not everyone is an expert here in PDEs. Parametric diffusion PDEs is a large area. And we have here our parametrization. You see this here. You have the set of parameters which are encoded in a certain way in these terms. But here you see the y's. And this is encoding. There are different ways of encoding. Some are more difficult, some are more easy. There are more easy ones, which are of this type. There are more difficult ones, the so-called non-affine parametrizations. And typically, classical methods have huge problems with those types of parametrizations. Now, what we then did was we set up, I mean, in a very conscious way, let's say a battery of experiments which were all done in the same way. We always had the same fixed neural network with 11 layers, with this number of neurons in each layer. We have always the same activation function, always the same number of training samples, always initialized with the same way, I mean, to really have, let's say, a conscious setup of comparison. And the dimension of the parameter space was set up to 91, which I think in your case, you think this is, I mean, extremely small, but in this area, this is already extremely high and very difficult. And so what you can see for certain parameterizations, you can see that, I mean, the parameter dimension, if it goes up, that then the error which you make in the test phase just goes up linearly. So again, you don't see any complexity blow up. So this behaves all very benign, and this is true also for other settings, for other affine parameterizations. Again, you get this linear behavior. Also, the training error goes down nicely. Everything behaves very smooth, very benign. And also, even if you go to the non-affine parameterization, also there things behave very nicely. So what one can show is, in that sense, the performance does not suffer from the curse of dimensionality and is also efficient for non-affine parameterizations. So I think this is, a great asset. What we saw there is that neural networks can sense the low-dimensional structure very well. We can prove it here. And also, for this whole area, neural networks, in particular, that ability to sense low-dimensional structures is extremely effective. And since we have the theoretical results, we also get reliability in that sense. So let me just, before I come to the main second part concerning limitations, just maybe very briefly touch upon explainability, because I think this is something which is extremely important for reliability and is also extremely important for revealing low dimensionality. So now we saw a lot of applications, but again, for instance, in the imaging problem or imaging application, we didn't have complete rigorous theoretical results. But explainability is one way to solve this problem, and I think this will be one key ingredient then also, for instance, for getting certifications of neural networks and AI technology. So maybe I can skip this slide because we already heard very beautiful talks concerning explainability. The main question is to explain black box predictors, to understand how they reach decisions, and maybe as compared to René's talk, here the neural network is not prepared in a particular way. It's a standard neural network which is not really designed to be interpretable, but it's just any neural network. And so one way, we viewed the problem was from, let's say, an information theoretic viewpoint. If you have, let's say, your initial signal X, if you have your neural network, then you would like to transmit, in the sense also of signal transmission, the key, the crucial elements to the second person, who should then verify whether with the same neural network the same message. And so now, since you just transmit parts of it, it needs to obfuscate it to a complete image and then get the result. So this is in the setting of rate distortion theory, where you transmit a certain small part, the size is the rate, and the distortion is the error which you make. And so certainly, what you aim for is you want to drive the rate down, so you want to have very few key components, in the sense also of extracting the low-dimensional content of it. At the same time, you would like to have low distortion. And certainly, you can imagine this you cannot compute. So this rate distortion function, lowering the number of key components versus keeping the error under control, this is something you cannot compute. It's NP hard, NPP complete even, and so you can relax this in the canonical way, which I think in this community is very standard. So you relax it concerning the L1 norm. You take now continuous elements for each pixel relevant scores between 0 and 1. And so just showing you maybe one image here. What you see here is that the explanation which we get that way reveals also the low-dimensional structure, which is important for the network for that decision. You see here exactly, basically, the low-dimensional singularities in a certain sense. So since we train for conciseness and aim for conciseness, then what is revealed are exactly, basically, to a certain extent, the boundaries. So it shows that neural networks, this is what they take into account, the low dimensionality. It's another instance of what we already saw before. And so if you compare now concerning how many pixels you require for a certain distortion, then these algorithms, because they are also tuned towards that, certainly here have the steepest curve. You can extend this in certain ways now, and I don't want to go too much into the details. Again, there you can extend it by taking also, if you know that, the data distribution into account, because you might not want to obfuscate by random pixels, but you would like to maybe have something which is a bit more natural. And also, and this brings me back to the beginning of my talk, you might not want to have relevance scores for pixels, but maybe for higher dimensional structures. So for instance, René showed us so blocks of pixels, and his framework was also flexible enough to, for instance, include wavelet coefficients or shielded coefficients. So here, indeed, we also then take relevance scores of wavelets or shielded coefficients. And so maybe just to finish this part with two examples, what you can do in this direction. So for instance, what you see here is an application from telecommunication. You see here a city map. The red dots are cell phone users, and the white blob is a cell tower. And the neural network computes this black and white background, indicating at each point how strong the signal there is. And now you see there's something very strange happening here, because this is an area of bad reception deemed by the neural network, but this area is right in front of the cell tower. So this doesn't make any sense. And you can ask now, with these type of flexible explainability approaches, why did this occur? And the explanation is that, in fact, the neural network looked at those structures, and these actually have bad reception, and that led it to mark this area in dark, in black. And so the network did actually something sensible. So what we found out later on was that there was actually a building missing in the city map. So the neural network really did something correct, and we revealed it by these explainability approaches, which we wouldn't have done otherwise. And maybe just as a last example, where we now take wavelets also into account, there, what we found actually quite interesting is you can, for instance, concerning adversarial examples, detect reasons why adversarial examples occur, and then maybe prepare the neural network also for improving this failure. So here is an example where this was classified as a diaper, although it's obviously a man with a dog, and this was classified as a screw. And now, if you take the wavelet-based explanation, so basically what I showed you before, but now the relevance score on wavelet coefficients, then you can reveal what the network has mistakenly seen. And so if you now overlay it, if I overlay it, you see, I mean, this could be then actually mistaken as a baby, and then the diaper is not that far off. And this can be mistaken as a screw, and so then a screw is actually a good explanation for that. No? So now, I mean, with such a flexible explainability approach, which is also rooted in theory, so reliable itself, you can, well, maybe get some additional insights also in neural networks. Okay, so this was just a brief excursion, and let me now also come to limitations, because I think that's an area which is often very much overlooked. I mean, we see great results of neural networks, but they have limitations. I mean, they're not a Swiss Army knife, and so this is something I think we need to take into account. And this is also, for me, one key aspect actually of reliability, because if you want to have reliability, we need to very consciously analyze what we can do and what we can also not do. Yeah, so, I mean, if you look at theory, we have beautiful theory, and there were amazing talks in this workshop concerning, for instance, expressivity, generalization abilities, and so on, of neural networks, conversions of training algorithms, generalization abilities. However, I mean, from my perspective at least, what we do not consider enough is what happens now if we train neural network our laptop on classical hardware. So what is maybe the sample complexity if we train it on our digital hardware, on our GPU, and in particular limit of the computability on where we perform our neural networks today on. Because, I mean, I guess everybody of you has a laptop in front of you. This is a piece of digital hardware, certainly. GPUs are digital hardware. This is what we use all over the place. So there's a theory to practice gap in a certain sense. I mean, the theory is beautiful, but I think this is something which might need a little more attention in this direction. And so the question and the goal of the last part is to examine boundaries imposed by digital computers. So what is a computable function? So think back of your CS class, maybe there's a whole theory on computability, and let's say in a nutshell, a computable function is one for which the input-output relation can be computed on a digital machine, which is typically modeled as a Turing machine for any given accuracy. So this is standard, and I mean a Turing machine is the classical model and the widely accepted model for digital hardware which we use these days. So what problems are there? Well, I mean the underlying problem, is it feasible? Well, I mean for that, to analyze this, we need computability of the ground truth. If we cannot compute it, I mean we will always have an error which we might not be aware of. The neural networks need to be computable. Otherwise, I mean, we cannot assess them from a theoretical viewpoint. And also, what we need, the neural networks are computable by minimization problems, so we need to compute the mapping to the approximation, which we deem important. Certainly, I mean, if things are not computable and you will see that there are problems, you can tackle that in practice. You can still compute things. I mean, you will get some output. But, I mean, you might facing limited precision in that case, and also it's a problem with guarantees of correctness. So we might have nice error bounds, but if things become not computable, I mean, these error bounds, you cannot say if they still hold or not. Okay, so as already said, I mean, the key ingredient here is our Turing machines, which are a classical model for today's hardware where we train on. So the Turing machine, well, I mean, it's certainly closely linked to discrete problems, but typically, and this was again also part of the discussion yesterday in the panel, typically you have continuous type analytic problems. And so the question is, I mean, which problem does this deviation causes? And here again, I mean, a Turing machine, if you haven't seen that, but I presume everybody of you have heard that in one class or the other. So you have this tape where you have, let's say, some device which is able to move back and forward. Here you have 0 and 1, so a finite alphabet on it, and so the Turing machine is able to modify this tape, and then, I mean, the tape hopefully contains the output which you aim for. Yeah, but I mean, it's purely discrete. That's the key point here. And so there's a whole theory on what computability is. I mean, for instance, there's a definition of computable real numbers. So let me just, I mean, for the sake of giving you a bit insight, showing you this. So the definition of a computable real number is if you have a natural number on the initial tape, which you just saw, then it is computable if the Turing machine, when it acts, it terminates with a rational number so that the error is controlled. So the error between what you get out and the true real number is controlled by this 2 to minus n. So you have the accuracy first on the tape, then the Turing machine acts, and then you would like to get this rational number q up to this accuracy. And so you can extend this then to computable functions. Again, I mean, a function is computable if there exists an algorithm which gives for any computable real number and any n an approximation of f of x, again with this accuracy. Okay, so again, I mean, this is just a small glimpse. There's a whole theory, very beautiful theory of computability out there. And so what we could show is that, in fact, I mean, if you look at finite dimensional inverse problems, then in general, there might be some where it's computable, but in general, the solution is not Turing computable. It's even stronger than that. It's not what's called Banach-Mazur computable, in particular not by a neural network. So this is a disappointing result. Certainly one question is then, I mean, maybe to categorize what is still computable and what not. But in general, I mean, in a general setting, I mean, this is not computable, so what does it lead to? So in general, there exists no algorithm which on digital hardware derives neural networks which give you the solution for any given accuracy. In that sense, the output, you don't have guarantees, it's not reliable, and this could point towards why we also observe instabilities and non-robustness in certain cases. Yeah? And so as an illustration, even if you have, for instance, I mean, a theoretical bar, you don't know whether your neural network, whether the output, because you cannot compute it only up to a certain precision, will be within this error bar. Yeah, so the theory then, I wouldn't say become useless, but I mean, concerning accuracy, you might have a major problem. And for certain of these results, we actually also have bounds on how accurate you can compute, but how accurate you cannot. And so sometimes this error is within 1/4, which is actually a lot. So this is quite disappointing. So if we train neural networks solving finite dimensional inverse problems on digital hardware, we could run into these problems. So is there a way out? Well, I mean, also there, let's say, mathematics tells us the answer. And what we could show is that for analog hardware, and according to Turing machines, there's also an according analog model, which is a Bloom-Schupf-Smale machine. There suddenly things become computable. So the solution of finite dimensional inverse problems is computable on such an analog machine. So if you do the step from discrete hardware or digital hardware to analog hardware, then we might have much better and improved reliability. Again, looking now from a reliability viewpoint. So there might be a need to really reach reliable AI, to actually rethink which type of hardware we train our neural networks on and where we let our algorithms run on. Maybe the pointer is towards novel hardware, and there are already very exciting directions in this aspect. I mean, I'm sure you have heard of neuromorphic computing, neuromorphic chips. There's this area of biocomputing, and there's also this area of quantum computing. So for instance, there are already quantum simulators, which, I mean, in small scales, work quite well, but these are then true analog machines. Yeah, so in that sense, as said, I mean, it might be in general worth rethinking what type of hardware we train our neural networks on. And so this is, I think, an aspect which needs to be considered much, much more. And this inverse problem result is one instance. I mean, there are many other results you can prove in this direction. So for instance, classification problems, there are various classification problems which are not computable. The pseudo-inverse, which is the key ingredient in various algorithms, is also not computable. Also, if you solve partial differential equations, in particular, for instance, the diffusion equation, which is one of the easy type, we saw it just, I mean, what you observe there is that the solution is, from a computability viewpoint, I mean, exponentially more difficult to compute than the input of your problem. And also, last but not least, for optimization problems, there are also various optimization problems which are not computable. So in that sense, I mean, to really get mathematically reliable AI, we might need to go to, as said, analog hardware. Maybe quantum computing is one way out. I'm not, let's say, claiming that, but maybe other types of analog hardware, but I think this is something which is worth considering and worth also taking into account. The theory one derives is absolutely beautiful, but then if we break it down to practice, we might need to rethink that. Okay, so let me finish with some final thoughts, because I think my time is up. So I mean, from my perspective, I find this an extremely exciting area, AI. I mean, we see it now in various instances of sciences, public life, and also in particular from a theoretical mathematical foundation and perspective. I think it's really rewarding to work in this area. What I find also very exciting is that we see various different aspects of theory now entering this realm. And then, I mean, I discussed a little bit, I mean, which key directions I see. We touched then a little bit on some of those. I mean, we saw some results in expressivity, explainability, and also inverse problems and partial differential equations, each time from the viewpoint of reliability and from the viewpoint of low dimensionality. And so what we often saw is that low dimensionality is also the key which neural networks have to then achieve and succeed in these tasks and also get reliability. And in the end, I mean, one thing which we might need to consider more often is also limitations. And here, this is one instance of a limitation I see, which are problems with computability on low dimensional, on digital hardware, and said, I mean, in all of those, somehow low dimensionality was the guiding factor. And Let me just finish with maybe one slide, maybe a short ad, because I talked about reliability, and we are very excited that now, I mean, in Munich, we have actually a school for reliable AI, the Konrad Zuse School of Excellence in Reliable AI. It's a school between both universities of excellence, LMU and TU Munich. And as you see, mathematical and algorithmic foundations are one major aspect there, but also medicine, robotics, algorithmic decision-making intertwined with reliability aspects. Okay, and that's it. I would like to thank you very much for your attention.
All right, thank you very much, Gita. And I think we have time to take 1 or 2 questions, if any. All right, here, please.
Hello. So you use only ReLU activation function. Does not any other activation function works to approximate the solution of differential equations?
Sorry, could you say it again? I didn't really...
Okay, so you use only ReLU activation functions.
I use what?
ReLU activation function.
Which activation? Oh, ReLU. Oh, really?
Yeah,
sorry,
yeah.
Yes, okay, sorry.
So does not any other activation function works to approximate the solution of differential equations?
Oh, yeah, sorry, certainly, yeah. So we looked at ReLU because that's the most common activation function. But certainly, I mean, these results, I mean, we also have results to extend this to other activation functions, yes.
Okay.
There are extensions of that.
One more question. What's the input of the network when you find the solution of differential equations?
So the input here, I mean, okay, so you don't mean for parametric PDEs. So for parametric PDEs, the input are the parameters then, if you would like to compute the parametric map. I mean, for a normal PDE, you would input, let's say, the initial data on your, let's say, unit square, for instance. Okay. I mean, so it depends on the type of PDE. So, but here our input is the parameter which we then use. I mean, and the output then, if the and the output are the points on the square.
Okay, thank you.
Hi. Regarding using neural networks for PDEs, so you discussed using fully connected neural networks, but if I understood correctly, you could have used any other parameterized family of nonlinear mappings. So in this area, are neural networks really, there's like strong evidence that they're considerably stronger than other nonlinear mappings? I mean, is it like in vision that for many neural networks are considered far superior to anything else, or is the situation less clear at the moment?
So here, I think it turns out that right now it's actually becoming very clear that neural networks have a huge advantage in the high-dimensional regime. So in the low-dimensional regime, if you have, I don't know, a 2-dimensional PDE, you have optimal classical methods. There is no need for AI or for deep neural networks. But if you go to the high-dimensional regime, and this is also, I mean, concerning the topic of the workshop, because neural networks can circumvent the curse of dimensionality by sending these low-dimensional structures, then neural networks really now become the state of the art. Yeah.
Okay.
Hello, thank you for the talk. I had a question with your first work about the limited angle CT reconstruction, in which you used shearlet-based regularization. So I was wondering, how does this perform in the situation where the CT system might have some noise like scatter, blur, and or Poisson, uncorrelated Poisson noise? Is it still able to reconstruct those edges given that you have a shearlet-based regularization?
Yes, yes. So from our experience, I mean, it does, because, I mean, the problem you solve in the beginning already has, let's say, this term, this data fidelity term, which kind of incorporates problems with noise already in there. So in that sense, I mean, this kind of, let's say, takes the noise to a certain extent out of the problem. Yes. So, but I mean, then also, I mean, it's also a question, certainly, as we all know, on the training data. So here, what we do, I mean, we train it from artificial data. So we have artificial ellipses and so on, and then we train on real data from a Mayo clinic in the US. And so this is already a bit noisy. So you could do, I think, an even better job if you already train it with much more noisy image. But again, I mean, this reconstruction strategy has already, let's say, a built-in fail-safe for, to a certain extent for noise. Yeah.
Hi. The last part of your talk about the limitations of deep networks at learning with finite or digital machines was very intriguing. Recently, and this was Stefano Soato, was giving the example of the difficulty of learning the concept of the number pi, because if you give the number 3.1459 to a human, eventually after 6 digits or so, a human will say that's number pi. But if you keep giving numbers, in his example, he had 2, 2, 2, 2, 2 eventually. And so it was not number pi.
Yeah.
So you had a long list of examples. The first one was on classification. Could you provide more fundamentally what is the challenge, for example, on what kinds of classification problems this is a fundamental issue that we cannot build machines with finite precision that would be able to, say, classify certain concepts?
Yeah, so thanks for that question. I mean, so we don't have, let's say, a whole, let's say, classification of which classification problems are difficult. We have in the paper, I mean, some examples of which are problematic. And so this is also, I mean, as said, I mean, for the other results, I'm not saying that, let's say, all of those problems are not computable, but I mean, for each of these instances, I mean, each of these classes, there are problems for certain situations. And so there, I mean, for classification problems, I mean, if you have, for instance, I mean, different classes and the classes are aligned in a certain, let's say, unfortunate manner, I mean, then it becomes a problem. But I mean, so we have special, let's say, special situations where we can then prove non-computability.
This would also be a problem for the explainability framework you had, because if I give you any subset of the digits of the number pi, you can't tell that it's number pi.
Yeah, exactly. So, I mean, also what I showed before, I mean, these results on inverse problems and partial differential equations, I mean, the last part basically, I mean, sets this into perspective and shows that actually, I mean, the theory which one develops there then also has a problem in this direction. Yeah, absolutely.
Gita, over here. Thanks for the wonderful talk, and also I was very intrigued by the second part on computability. So I was wondering, you know, how much of this sort of challenge comes from the fact that we're taking real numbers as a reference. It's like I can go in both directions. So let's say, you know, John Conway, late John Conway, the discrete math guy, the group theory. He had all these crazy ideas about games that can compute any number. This Fractran game, I don't know if you know. So they are not a classical Turing machine, but they're equivalent and they're universal. And so through this game playing, he also came up with a completely new number system. It's called the surreal numbers that contain, you know, all finite fields and infinite and whatever, also ordered and so perfectly fine. And so we could just as well take these surreal numbers as reference, but then we would make our problems even harder, right? Because it would be even harder to sort of compute these numbers. And in the other direction, there's this Dutch mathematician, philosopher, Brouwer, who, you know, came up with this intuitionist math, for which now there is some evidence, actually. There's also a mathematician in Geneva who that basically says at a philosophical level that real numbers don't exist, right? And so if we don't assume that real numbers exist, then many paradoxes in physics get resolved easily. Or not easily, in a complicated way. But like, what are your thoughts on that? You know, taking these real numbers as reference seems a little bit arbitrary. And yeah, well, that's not really.
Yeah. Sure. Thanks a lot for these, I mean, different thoughts in that direction. Yeah, I mean, certainly the real numbers are the problems. I mean, if you look at, I mean, from this viewpoint concerning Turing machines, which real numbers are computable, I mean, it's a very small set. It's in fact a zero set. So in that sense, I mean, this is exactly the problem. So if you have a purely discrete problem, I mean, then you don't run into these computability issues. So this is the problem, but I mean, so we discussed also during the panel discussion that these analytic models, I mean, have a huge value because you can drive very beautiful theory, and we know from also mathematics that if you go from the continuous to the discrete world, I mean, then own problems occur. But from a computability viewpoint, if you have these analytic models, I mean, then you might need to be aware that you might not be able to compute them in this way you aim for, and that your error bounds might not hold. Yeah.
Thank you.
Just a silly question, technical question about what you mentioned about the pseudo-inverse, that it's not computable in the Banach-Mazur sense. Would that be different if you'd have regularization so a regularized inverse instead of the limit for lambda going to 0 of the regularized inverse?
Yeah, so in some instances this might help, but as said, I mean, I'm not saying that any pseudo-inverse is not computable. I mean, there are classes of pseudo-inverse which are not computable, and so one next step, which we are also now looking at, is classifying exactly those problems which then are computable.
Okay, and if you had a regularization, would that make it computable? It depends.
Yeah, I would need to look into it. I think it's an interesting thought. Thanks for that. But I mean, maybe sometimes it helps, but I don't think it's a general, let's say, a general approach which helps, because also think of the inverse problem. I mean, there are the finite dimensional solutions. We also regularize. Still, I mean, things can be non-computable.
All right, I think for the sake of time, let's the speaker and take more questions offline. Thank you, Gita. Thank you. All right, our next speaker will be Dr. Beidi Chen, currently research scientist at Meta and soon joining CMU as an assistant professor. Beidi will talk to us today her recent work on hardware-friendly sparsity. Beidi, if you can hear us, would you please start sharing screen?
Can you see my screen?
Yes, looking good. Okay. Take it over, please.
All right, 1 second. Can you still see my screen? Okay, I assume that's a yes. All right, thanks for inviting me. And today I'll be very excited to present several joint work with my wonderful collaborators on using hardware-aware sparsity to perform accurate and efficient foundation model training. So in recent years, foundation models has made great contributions in image synthesis, language modeling, or scientific discovery. For example, you probably all heard this, models like AlphaFold, GPT-3, ChatGPT, Imagen, and so on. However, while achieving those great performance, they're very expensive to train, of course. This is mainly because the model and data size are exponentially growing, and the computation is usually performed on costly data center hardware. For example, a single training run of GPT-3 will take 4 months on 1,000 GPUs and cost $10 million, and at the same time produce massive carbon footprint. Therefore, with this limited resource in practice, we definitely have to overcome these bottlenecks and find more efficient ways to perform this large-scale foundation model training. So there have been many work and study tackling this problem with less data or smaller models in various different ways. But the main challenge here is we need to trade accuracy for efficiency, as we illustrated in this symbolic chart. So the key question here is this trade-off necessary? Or can we actually get both efficiency and accuracy during the training? Well, the answer is yes. Sometimes we can get this best of both worlds with hardware-aware sparsity. So I will show you in a minute how, when, and why we can get there. So first, I will present a line of work designing GPU-friendly sparsity from scatterbrain to pixelated butterfly, finally to Monarch. And at the end, you're gonna see a simple and accurate sparsity, which can train a GPT-BERT vision transformer model 2.5 times walk-all time faster on V100 and 25% faster than the most optimized NVIDIA MLPerf implementation on A100. Then I will share several future directions and some preliminary work. Specifically, I will talk about two preliminary work on system hardware co-design called decentralized training and ACSGD, where you will see a simple activation compression method and scheduling method will allow you to train GPT-3XL on a 100 times slower network, the same speed as NVIDIA Megatron inside a data center. Great. Let's start with today's sparsity deep dive. So the idea of sparsity, of course, is not new. It has long history in machine learning and also driven fundamental progress in statistics, neuroscience, and signal processing. But the sparsity in today's context in this talk refers to the sparse model training. For example, some variants of pruning, lottery tickets, or other recent sparse transformer method. Here we can precisely define the efficiency to be the walk clock time speed up. So to be more clear here, theoretical speed up measured in flops sometimes is possible, but in walk clock time is very challenging. So it turns out that a whole line of work in sparse training have been struggling to actually have speed up in walk clock time without the accuracy drop. So why is it so hard, and what other challenges they all share? First, it's very difficult and expensive to search and find a sparsity pattern that could maintain the same level of accuracy of the dense models, especially when you're training it. So it's a combinatorial problem. So many methods like pruning or lottery ticket actually needs to maintain the dynamic sparsity mask, but this large overhead of evolving the sparsity mask can significantly slow down the training and complicate the implementation at the same time. The second is most existing method there's some famous trade-off between the structured, unstructured sparsity and accuracy. So unstructured sparsity, which can be efficient in theory, but if not taking into account the efficiency of the training hardware like GPU or TPU, which is especially optimized for dense computations, then there's a problem. Here's an example of the memory access. Compute is very similar. That the point is, for GPU or TPU, this block device, the access of this red spot is the same as this blue 4x4 locations. So even with the 99% of the random sparsity, we'll like to access the full matrix because of this. And finally, most of the method will target a single type of operation, such as tension or maybe large output space, but different model architectures often compose different modules. And in many applications, MLP layers are the main training bottleneck. And in addition, not only focusing on training, but there are many other phases that face different challenges in efficiency. So what would be an ideal sparsity? So the ideal sparsity should be accurate, which can mimic the dense operations, like the dense model accuracy. We don't want any accuracy drop. And it should be hardware efficient. So not only the accuracy should mimic the dense, but the sparse operations should mimic the dense ones, like static and structured sparsity pattern. Well, you also have to have a wide coverage of operators that apply to the most neural network layers like tension, linear, and in different settings like pre-training, fine-tuning, and inference. So let's go through each of them, each of these challenges and each of this ideal paradigm to see how we can realize the final ideal sparsity. First, what is an accurate or expressive approximation to dense matrices? Well, is related to the structure sparse plus low rank. So this is the intuition, what I mean by sparse and low rank, and why is it a more accurate and efficient approximation to dense on this simple 4x4 matrix. So say if you want to do a sparse approximation, best we can do is start filling out with the high magnitude entries. And obviously, we can do a good approximation. And similarly, look at these high values. In the diagonal, we can approximate it well with the low rank matrix, since this is basically full rank. But if we combine these two in an exact way, or the right way, we can see we can exactly represent this dense matrix with a rank 1 matrix and 1 row and 1 column sparse. So we can simply use this intuition on better approximating the attention matrix in, for example, transformer models. And of course, this matrix usually models the pairwise interaction of different tokens. In this case, I love randomized algorithms. And the darker color will represent the score and the interaction. Higher score represents higher interaction. And this is the bottleneck to the model with low range sequences. So if we have a paragraph or a code, or instead of a short phrase, it will be a big matrix scaling quadratic with respect to the input sequence length. So again, if we don't want to compute and materialize this full matrix, we can do some approximation. And we can characterize the existing ones, or the major ones, into two groups. First one is exploiting the sparsity, like sparse transformer, reformer, and the low rank properties of the attention, like linear transformer, performer, and so on. They usually work well in different cases. For the tasks like language modeling, or these ones that really rely on this sparse interaction between a few tokens, so usually sparse approximation will do better. And for the tasks like summarization, classification, and so on, which you need some global information, where the low rank approximation will do the job. So in the scattering, how we show that is like you can simply combine this sparse and low rank component in this simple and exact way, and you will get probably better approximation. Now let's dig into when this will have more advantage. So the result is that this kind of generation process arises a lot in attention matrix. And it turns out this structure, sparse plus low rank, has been very well studied in statistics and signal processing since the late 2000s. Naturally generalized low rank and sparse matrices just has been rediscovered in this transformer setting. Of course, robust PCA. So seems like this sparse and low rank structure is pretty expressive and accurate. And the low rank part is too small dense matrix multiplication and also efficient. Then what is the problem? So the problem is the sparse part is dynamic and unstructured. So it is not hardware efficient. So recall we wanted to be static and block aligned, which can mimic the dense operation, but still have the power to represent all this dynamic sparsity. Again, it's a combinatorial search, but show you in a minute that such sparsity patterns do exist. So it's related to a class of structure matrices called butterfly matrices. And I will walk through some simple examples to understand why this can represent any sparsity. So representing any sparse seems to be a very hard problem. We can first take a look at a special case of the sparse matrix called permutation matrix. And we can understand different ways we can represent them. So here's a small exercise. This is the bitwise representation from 0 to 3. And if we look at a permutation that has allowed them to swap the last bit. So 0, 0 and 0, 1 can swap or not. 1, 0 and 1, 1 can swap but not. They decide to maintain. So in this case, how can we represent this permutation matrix? Well, the permutation matrix will look like this. So if you multiply this matrix from our x0, which represents 0, 0 to 1, 1, we indeed perform this permutation. And what can we observe here? So we can observe that this corner matrix controls the position of x0 and x1. And this right bottom block controls the position of x2 and x3. So this location of 1 or 0 decides if we're going to swap them or maintained. So we can conclude that this sparse matrix can represent any permutation that swapping indices differing only in the last bit. So those blue locations here are the non-zero entries. And we can remember this sparsity pattern. And jump over the details. If we allow them to swap their second to the last bit. So these 4 positions will control the swap of x0 and x2. And these 4 positions will control the swap of x1 and x3. So now this sparse matrix can represent any permutation that swapping indices differing second to the last bit. So it might not be that obvious, but if we can put these 2 matrices together, we can represent any 2-bit permutation matrix. And similarly, if we combine all these 4 matrices, we can represent any 4-bit permutation matrix. So recently, our lab proved that for these matrices called butterfly matrices, the product can represent any sparse matrix with the near optimal time and space complexity, even with this fixed sparsity pattern. So this generalization from permutation to any sparse is also surprising to us. And recall, let's zoom out. So our goal was to find the ideal sparsity to start with and the fixed one. So this one gives us an opportunity to sidestep from the combinatorial problem of searching over all the possible sparsity pattern at a minor cost of an extra log factor in a number of parameters. And because of the sparsity pattern is fixed, this is also trainable with, for example, just gradient descent or on just the non-zero entries of those matrices, which is a nice smooth optimization problem. So just a side note that is what is even better is usually those matrices, which is a class of fast linear maps that encodes the schema, can represent any structure matrices like the ones that you heard of, like DFT, sparse, low rank convolution, Hedman, and so on, and is closely related to the pattern in the vast transform method like FFT because of the divide and conquer structure. And for the audience who is familiar with the network switching, this is the same pattern in the butterfly networks from the 1965. So butterfly matrices are so powerful. Why can't we just directly use them? So here are the challenges to directly adapt them in the modern hardware like GPUs on the left. And there are some simple fixed, we can make it more efficient while still retaining their favorable property. And I can go through them one by one. First, if you take a look at the sparsity pattern, they're not structured. They're fixed, static, but they're not structured. And recall that what we showed earlier about the memory access. So we want this block size to be 32 for at least 32 for GPU or 128 for TPU. So this sparsity pattern currently is not efficient. A simple fix is we can directly reparameterize them with this constant, like the 32 or 128, depends on what the block size you want. We can still tightly represent any sparse matrix with this extra log factor. It's a constant, it doesn't change anything. So even we have this block butterfly, it is still not efficient because they have many products. So we know that if we have a series of operations, we need to do a lot of read and write. And also in the training, if there are more matrices, it's not that stable. So a simple fix is one of the first try was we proposed this flat block butterfly, which we can take the first order approximation to the butterfly matrix, turning this product into the sum. So in this way, is going back to a single sparse matrix. But what is the problem? So the problem is, of course, turning this first order approximation breaks nice properties of the original butterfly matrices. and it can no longer represent a lot of other matrices that originally it can represent. So luckily, to compensate this reduce of expressiveness, we already had this low rank term in the proposal. So you can fix this a little bit. But we want to understand that is there an alternative or a better way that we can still maintain the expressiveness of butterfly matrices, but being efficient? Well, of course, the answer is yes. So more recently, we have an extension on the pixelated butterfly called Monarch. Recall this divide and conquer structure for butterfly matrices. The matrix view is on the right. So the leaf layer will indeed have the optimal big O n log and non-zeros with the log and butterfly matrices. For example, to represent any big O n sparse, butterfly needs to have big O n log and non-zeros. This is optimal. But if we take a look at the second layer, the total number of non-zeros in the second layer becomes n squared of n. So obviously, theoretically, there's a big gap between this square root of n and log n, and so it's not optimal. But the good thing about this two matrices is there are only two of them. And if you look closer, they're superstructured. So one of them is naturally block diagonal matrix. So basically, if you combine the first half of the log n factors of butterfly is naturally block diagonal. And the other matrix is kind of structured, but needs some work. For example, the permutation is up to a very simple permutation, also block diagonal. So in this way, Monarch matrices is a simple product of two block diagonal and two fixed permutation matrix. Can be very efficient on GPUs or TPUs. So Monarch is a very interesting result of interplay between theory and hardware. So they're not optimal in theory. Is n squared of n instead of n log n, but also not the most hardware efficient one because it's not a single matrix and it's not dense, but it's the best design if you consider both. So since this is a super class of original butterfly matrices, can also represent any structure matrices. So it's a kind of a super class of butterfly matrices based on the parameter counting. Well, so we're almost there for this ideal sparsity. Need one last piece on the different settings. So both pixelated butterfly and Monarch can obviously perform sparse pre-training, but what about the other settings? So it turns out that Monarch can unlock three different ways of using the sparse models, including training large-scale models from scratch, like what we just described, and dense to sparse fine-tuning or inference. So say if we have a pre-trained GPT, pre-trained BERT, if we want to have a faster fine-tuning or efficient model serving, this is also doable. And also inverse sparsification, which can transform a sparse model to dense. So how can we utilize this available large dense model to perform this sparse fine-tuning or inference? So this problem reduced to, can we derive a projection algorithm or decomposition algorithm to find the closest ones belongs to that class of matrices? So this is actually a very hard problem for most of the class of matrices. The only known solutions or popular solutions, algorithms, are for element-wise sparse, which we just picked the largest magnitude, and low-rank decomposition. For example, our lab spent years working on this interesting theory problem on what's the projection algorithm for butterfly matrices, for these log n matrices. But fortunately, this is probably as hard as the the tensor decomposition, and we haven't solved it. But surprisingly, we found there exists such algorithm for monad matrix because there are only two. So again, this hardware efficient design coincidentally help us make some progress or understanding on the theory side. So I will jump over the details for what exactly this algorithm looks like. That's very interesting. It's based on a recursively call for the rank 1 decomposition. But the key message here is after decomposing this dense matrix to the closest 2 block diagonal matrices up to permutation, you can utilize the pre-trained dense models and enable fast fine-tuning or inference with those monad matrices. And the last way is sparse to dense through the reverse sparsification. So in this process, we can start with a sparse model, say train 80% of the time, and then transition them to the dense model to finish. So the training in the remaining 20%, of course, is still dense, but it's important for some modifications, for example, the large language modeling, when certain amount of parameters seems to be helping with the performance. So if we still want to maintain the certain perplexity or certain performance, but still save some time for your training, this is the way to go. So next, I will show a subset of the evaluation results. We evaluate on the all settings and, of course, on the wide range of the task. And besides on the standard computer vision and NLP benchmarks, we'll also evaluate on the MLI reconstruction and PDE solving, since monad matrices or butterfly matrices can represent any structured matrices. So it's highly related to the FFT. So here are some numbers. First evaluation was on standard image classification on ImageNet. The experiment was on the MLP mixture, emerging architectures and vision transformers. We showed that even with this very simple fixed sparsity, we managed to train model up to 2.3 times faster than the dense model without lowering or hurting the model accuracy. The second one was on the large language modeling. The table on the top right shows the result compared to GPT-2 on open web text. We show that we can train the model up to 2.5 times faster than the dense model, also without the perplexity drop. Here we can also say a bit about the scaling law. So there are potentially more savings with larger models when we vary the size to do the sparse modeling. And the third one is fine-tuning BERT. So the table on the bottom shows the monad matrices fine-tuned model with very similar quality with the dense BERT model, but 1.5 times faster in speed. And also two tests, which we show monad outperforms FFT and CN on MRI reconstruction when there's a need to weight different frequencies for de-aliasing problems on the applications, like partial differential equation solving when there's a non-periodic boundary conditions, because monad can generalize Fourier transform. And our implementation is 25% faster than the NVIDIA super optimized implementation on MLPerf. And so now I'll show you how you exploit model sparsity with algorithm design, adapting to the hardware, getting this best of both worlds from scatterbrain to pixelated butterfly and to monad. But I will talk about several future directions and ongoing work or preliminary work. So the first one is the algorithm system hardware co-design. So super excited to continue exploring more efficient sparsity and actually co-design with the new accelerators. It's very hopeful that this dynamic sparsity can be lower power, if not faster, on the next generation of ML training hardware. But as we know that the hardware design cycles is much longer. Meanwhile, maybe we can exploit all the current available underutilized ones. So I will show our results on communication efficient decentralized training. So the GPU market shipped almost 100 million units last year, but many of these GPUs are underutilized. So leveraging this fact that the volunteer computing projects like voting at home, learning at home have sourced a lot of NVIDIA and AMD GPUs continuously. And this kind of incremental electricity cost of running a V100, for example, for a volunteer are 100 times slower than on AWS. So if we could make use of all this device in the decentralized open volunteering paradigm for foundation model training, this would be a revolutionized alternative to expensive solution offered by the data center. So of course, this vision inspired many efforts in decentralized training, but one of the main bottleneck is the communication over this heterogeneous slow network. So first, this foundation model is giant. So we need to go beyond vanilla data parallelism. And second, the network connections between the GPUs are slow and heterogeneous. So we also need to carefully schedule the communication among the GPU device for different parallel training communication paradigm. So formally, we can formulate or formalize our problem in the fully decentralized setting, where each pair of device may have different delay and bandwidth. So we can limit our scope on the data parallelism and pipeline parallelism. So in the pipeline parallelism, the model is partitioned into different stages, where in the forward propagation, the activations are sent from stage I to stage I+1, while in the backward, the gradients needs to be synchronized as well. And when combined with the data parallelism, the gradients of the parameters for the same stage needs to be also synchronized. So we can define a tasklet as the forward and backward computation of stage for a micro batch. The goal of our optimization problem is to find an assignment strategy that matches those tasklets to device so that the communication cost is minimized. So this is an example of, this plot is the example of how data and pipeline parallelism work with 4 devices. So how we assign different computational tasklets corresponding to a micro batch and a subset of layers to a collection of geo-distributed device connected with heterogeneous slow networks. So in this setting, we have to consider potentially exponentially many more distinct allocation strategies because the heterogeneity of the communication matrix. Even this subproblem of finding the best pipeline parallelism strategy is close to our hard open loop traveling salesman problem. So to capture the complex and communication costs for training foundation models, can formulate this problem involving decomposing the cost model into 2 levels. Into 2 levels. The first level is a balanced graph partition problem showing on this plot, corresponding to the communication cost of data parallelism. Whereas the second level is a joint graph matching and traveling salesman problem corresponds to the communication cost of the pipeline parallelism. And I will jump over the details of how exactly this bi-level scheduling works. So let's say we have a perfect scheduling, which we minimize the communication cost, but it doesn't mean that we don't have to communicate. So there's still an overhead. So how can we be smart about the communication that is done during the forward and gradient passing? Well, gradient compression has been widely studied for data parallelism. Previously, people have noticed that neural network can tolerate some compression for activations. However, to directly compress the activations the same way as how we quantize the gradients have some fundamental drawbacks. So theoretically, simple compressing this activations in a stochastically unbiased way will lead to biases in the gradients that cannot be measured easily or expressed in the closed form. So in another word, it's gonna affect the training accuracy a lot. And empirically, this approach leads to this suboptimal quality under the relatively aggressive compression on many models, like we illustrated in this plot. So if we do that in the fine tuning, sometimes it's worse than the zero-shot results. So here's an example of fine tuning GPT-2 with different activation precisions in the communication. So fortunately, we made an observation that the activation changes of same training examples, we can call it delta, are easier to quantize than the activation themselves. So this gives us an opportunity to redesign what to send in the activation communication. So the intuition here is we can compress the change of activation for the same data samples across epochs to enable an interesting self-enforcing dynamics. So the more training stabilized, the smaller the change of the model across epochs. And then the smaller the changes of activations for the same training examples across epochs will be, which will lead to smaller compression error using the same number of bits. So the training is stabilized more. So here's an overview of how exactly it works in the forward propagation, given a random sample data point. If it has not been seen before, we'll compute its activation, cache it in the stage 1, and then send it over to stage I+1. Otherwise, we'll quantize the difference between the current activation and its memory from the last update, and then this quantized difference to stage I+1, and update the memory by this quantized difference. And in the back propagation, we directly quantize the gradient, similar to any other existing approaches. So here are some interesting results. So ACSGD is an activation compression algorithm with rigorous theoretical analysis that allows the convergence rate of 1/√T without relying on assumption of unbiased gradients. And empirically also achieves the 2x end-to-end speed up compared to that of, let's say, P32, and successfully illustrating this importance of communication compression in the slower networks. And more notably, as we mentioned in the beginning, if we combine everything together, all this scheduling, system optimization, communication compression, when the network is 100 times slower from, let's say, 10 gigabits per second to 100 megabits per second, the training is only about 1.1 times slower than the NVIDIA Megatron in a data center. So if this system were to be deployed in a real-world geo-distributed decentralized network, the training throughput of this fine-tuning task will be almost as fast as the performance inside a data center. So of course, there are many more challenges and questions that are answered, like fault tolerance, or what about inference, which has totally different computation and communication challenges, but it is mostly important if we're able to, is deciding like we're actually gonna make it a product, right? Which is coming soon, but at a high level, besides the weight quantization, like the recent work like integer 8, smooth quant, GPTQ, we can exploit the activation function as well. and also the residual connection. And also, another very exciting thing is the data and sample efficiency. You probably heard this swing from model-centric to data-centric AI. And it's possible we can find structures in data and speed up training from a different angle. And the center question is, what is the scaling of training data for a model to reach certain quality? And there have been many great work recently about data distillation, data diet, data pruning from the FAIR group. And very excited to pursue this direction. And because under some computational constraints, the key is to find more efficient ways to learn from the data. So one possible direction, it may be to incorporate the non-parametric algorithms like retrieval or near-neighbor search during the learning process. The intuition is like from the sparse model training, which has used those algorithms to implicitly increase the model capacity without more compute, and as well as a line of work in the retrieval models like retro from DeepMind. Hopefully we can answer this under the weekly or unsupervised setting where we have a lot of data. So, and also there are several applications going beyond the traditional ones where the researchers have been looking into. For example, the computationally fluid dynamics, medical imaging, DNA sequencing. Actually, many algorithms that we've been using for exploiting model or data sparsity might not only be able to speed up the training, but also unlock the big performance improvement in those applications. For example, near-neighbor search algorithm like hashing, or those structure matrices which can generalize Fourier transform, right? So the sparsity as the inductive bias equipped with this learning capability can only be more powerful. For example, we've been recently working on applications like new material discovery by ML models for approximating the density function of theory, and also for antenna design through ML models for solving those Maxwell equations. Oh, I guess this is the end of the talk. Thanks so much for listening and joining me today. Hope you enjoy it, and happy to take questions.
All right, thank you. Thank you, Betty. We have time for questions, please.
Hi, thank you for your great talk. I have two questions regarding your first part and also the second part. For the first part, you mentioned something that the block diagonal matrix is not optimal to approximate the dense matrix, but it's good enough in performance. Is it because the model you try to train is too over-parameterized, so we don't need to be precise? We just need to some good enough metrics to do the training. Then it can give us the good enough accuracy. And the second question is regarding the second part. You mentioned something when you do decentralized training, you first need to do some data partition. So what kind of data partition you are doing? Does that affect your performance? Yeah, thank you.
Yeah, thanks for the question. So let me try to iterate on if I understand the question correctly. So the first question is to ask why we can actually use a sparse matrix to actually mimic the dense operations or the dense performance. Is it because the models are too over-parameterized so that even any kind of sparse one could work? In short answer, I think that's a yes. So the larger the model is, the more over-parameterized it is, the more headroom we can enforce the sparsity there. But a more detailed answer would be not exactly any kind of sparsity would work. So those kind of sparsity can maintain, for example, the monad matrices, can maintain the accuracy not only because it's block diagonal and efficient, but also all this permutation. So this two block diagonal with the permutation can exactly represent the regional butterfly matrices. And butterfly matrix is very expressive. It will be kind of a more general matrix than any other like sparse matrix. So that is the reason why it's a combination of the model is indeed very large. And also the algorithm is kind of smart. And for the second question, it's about the decentralized training. The question was, do we need to partition the data in a certain way so that we can maintain certain accuracy, and how we partition that? If I understand that correctly, are you talking about this part where about the data parallelism? That's just kind of random data partition for micro batches. So if you're talking about this part, about the communication compression, I was talking about for the same sample, if you see that on the same device, if you see that from epoch 1 and epoch 2, the difference of this activation can be quantized more. So there's no data partition involved in this part as well. So maybe I misunderstand something.
Yeah, you're correct. You understand it correctly. Yeah, thank you.
Okay, thank you.
All right, thank you. Next question, please.
Hi, Betty. Thanks for the interesting talk. I know you've always been a strong advocate for smart algorithm design over hardware acceleration. Some of your earlier work on dynamic sparsity was used to train large DNNs on devices using nothing but CPUs. With the advent of foundation models, and as models continue to grow larger and larger, have we, even with structured matrices, dynamic sparsity, et cetera, have we crossed that point of no return where we could train models such as foundation models on low fidelity devices using nothing but CPUs? Or is there still hope to train such large models using intelligently designed algorithms?
Yeah, thanks for the question. So it seems like you know my earlier work called Slide, which I code up the whole MLP training from scratch on C++ on CPU just to demonstrate that hashing can make the prediction for the computation that actually needs to perform and makes CPU faster than at that point the GPU. Yeah, thanks. I'm very happy to hear about that you're a big fan of that work. And the reason why I kind of moved to different kind of hardware devices, for example, on GPU, and now on like more decentralized devices, is I figured out that when the model becomes like larger and larger, is great to have algorithms to adapt to different kind of hardware. And with a combination on the C++ work or the CPU work was now a startup. So it's more like into the production and trying to help people who have all the CPU clusters to train recommendation models faster. I think it might be coming back. Because for a long time, I can't find such a large matrix that I can actually make CPU faster than, there's such matrix that there's more headroom for CPU to catch what GPU can be doing. Because for the transformer, which is kind of the major model architecture, the largest used to be like, for example, several K by several K. This is a very relatively small matrix if you want to do any matrix level optimization on it. The speed up we can get on Slide and the C++ work relying on you need a really large matrix, for example, in the recommendation models. So it's a little bit more constrained, but luckily or unfortunately, now the model on the 175 billion parameters have the matrix, which is 10K by almost 50K. And it also demonstrates this extreme sparsity. So stay tuned, slide is coming back.
Thank you.
Thank you.
Is there a next question? Okay. Okay, great. Thanks. Thanks, Betty, to help us keep right on time. Thank you for the great talk.
Thank you.
All right. All right, we're about to have a coffee break for 30 minutes, but before that, Professor Ima would have a few words about the after-workshop logistics. So, Yi, please.
So just a comment on the previous talk, right? So when I was a graduate student taking numerical analysis from Math Department, Berkeley, so the professor said one thing, I still remember, right? So it doesn't, no matter what happen in the future, right? The only two types when you're dealing with high dimensional computing, computing large scale problems, right? Solving linear equations and whatever. There are only two types of operator you can compute efficiently. One is sparse, one is low rank. Except the other special case like diagonal matrix, right? So those are the two generic type of operators you can and a human can implement very efficiently, at least with current computing infrastructure, right? If you want to scale everything, those are the only things you have to utilize structure. Again, reflect the theme of our workshop and also the future study, right? You have to utilize that if you really want to scale up. Right? Yeah, and also just to reflect on this a little bit. A few words before we head to the coffee shop. I know this is a workshop we have this is the third time we have this workshop. And we're still trying to, we will definitely plan to hold the workshop in an annual basis. Hopefully many of you, some of you will come back. And this will form a sort of community of people who are interested in this very important direction of topic of research. And because also, the culture of machine learning or, the AI has been also evolved very, very quickly, right? It really create all kinds of disruptive changes to the community, to the research community, and also in the forums, right? Like conferences, workshops, and so on. There's many, many mega conferences now. But we feel like, the reason we held workshop like this is that we feel like those mega conferences really doesn't have this kind of intimate, close, in-depth, focused discussion and sharing of knowledge, right? And so the signal-to-noise ratio, for a bigger conference is probably a little bit too low, especially for students, for young researchers. And in terms of formulating what are the important problems, what are the important directions, and so on. So we like to have this workshop on a recurrent basis in the future. But also we don't want it to, in one way, we don't want it to sort of compete with big conferences. They serve whatever purposes they serve. But we want our the workshops or conference in the future to be more complementary, really serve things we think are valuable to academia, to students and the researchers. So we would like to, this is our, definitely this workshop is not perfect, and there's a lot of things. What the forms you find, we hope after the workshop we'll send some survey or feedback to get your feedback about your experience with a workshop like this or before. And also, what do we like to suggest? What do you think are most effective for yourself, or right, to share ideas, to discuss intuitions, and how to select topics, and so on. Right? Make it complementary, make it really, really valuable for your future interaction. Honestly, personally, I myself benefited tremendously from when I was a younger professor, right? I benefited way more from a workshop like this than from big conferences, right? More focused, dedicated workshops, a series of them, and really continually driving in one direction. In computer vision early days, and later on in compressive sensing later days. But I don't see that kind of in machine learning, right? We don't, suddenly things get too big, too diverse, and very, very popular, very, very distracting news and topics, right? So for the younger generation, the younger researchers to get a foothold in this very dynamic, very, very active, fast-pacing world, maybe, maybe the new form of paradigm or forum or conference or workshop will serve better purpose. So that's, we'd like to appreciate you to give us some feedbacks as well, right? Again, some of the leadership or senior folks in the room or in the organization committee will also discuss things. Hopefully in the next couple of times, we can morph into something we think are more comfortable for most of us, right? Or more valuable. All right. Thanks a lot. I don't want to delay you for the coffee shop. We can continue the discussion and sharing ideas. You send an email. Maybe we'll also send some formal survey after this. And also, we'll feel free to send the emails or sharing your opinions, ideas, or suggestions to many of the organization committees. And their names or contacts are available on the website. Yeah, thank you very much. Yeah, thanks.
All right, we shall just have a half an hour coffee time, and we shall see each other again here 11:30, please. All right, people, thank you for coming back. And we're ready for our third speaker in the morning session, Dr. Rina from Google. He's a research scientist, and he will tell us about his brain-inspired work on the table of content for sparsity. Rina, please take it over.
Thanks for this opportunity. And I'll be talking about how should we think in terms of how a table of concepts might form over time. So the world throws at us sights and sounds, and we try to make sense out of these sights and sounds and find patterns so that we can predict what might happen in future or what actions to take. And what is the main algorithm that we're using here? What could be the block diagram of the architecture from an algorithmic viewpoint? Is it modular? Is it even using deep learning? Now, do we have memory, a table of memory where we store concepts? Now, there is this ancient mnemonic called the tabula rasa, which says that we are born with an empty slate in our mind, and as we go through experiences in life, we form concepts and notions and beliefs. And that's what helps us deal with the world. So is there such a table? So thinking about a table of concepts allows us to think of deep networks in a modular fashion. So this is useful because we can now things become more interpretable. For example, if you experience some event, then you can interpret it as the set of modules that fired and the order in which it was fired. And that gives you some very simpler way to look at that event. But I believe that modularity is useful not just for interpretability and to make sense, but it's also important to actually learn very high-level abstractions with a small sample complexity. So it's not just efficiency that matters here. So let's just think about how might we store experiences. So let's say you just meet someone for chat over coffee. Then how are we remembering this event? Who did we meet? What did we talk about? What was the setting? How many other people were there? How do we represent it? And more importantly, how do we index it? And if we meet that person again, how do we recall this event? Is there some kind of a knowledge graph that we build in our mind? And I want to emphasize that here we are not trying to understand exactly how the human brain or the mind does it, but what is the essential ingredients of the algorithm or the algorithmic architecture that we have. So this is not a physiological study. It's a study of the algorithmic architecture. So if we close our eyes, we can actually recall events from the past, sights, sounds, which means that we must be storing some kind of a sketch or a caricature of that event that can be used to approximately reconstruct those images or that event at some level. Another thing to note about our memory is we tend to forget very gradually. That is, we don't forget things all of a sudden. Maybe I might forget the fine details of a conversation, but I might still remember very high-level information like the topic that was discussed, and I might not remember all the people who were there in a meeting, but maybe I might roughly remember the main people I interacted with, or roughly how many people were there. So maybe if we just think of this as a thought experiment, then maybe in our mind we have a modular network. So for example, in a chat with someone, maybe in our mind we have a module for person recognition and a module for speech analysis. So, and there could be many, many other modules. Like you can have modules for math, for driving, or for other activities. But at a time, only maybe a small number of modules is firing. So in the conversation, only the person representation module is firing, and the speech representation module is firing. And we are trying to, the subset of modules which fire essentially captures that event. So at an abstract logical level, we can think that in our mind there is this set of modules. Of course, it's a big question, difficult question as to how do we even form such modules? Is it actually physically separate modules? But let's ignore that for now. Let's assume that we are born with some initial set of modules, and we'll see how that could be useful in maintaining a modular structure. So any event will probably just fire a small set of modules, and there is a certain skeleton of a DAG if you chase those firings. So, and every module is producing some embedding representation of whatever it finds. So when we want to remember an event, we can just remember it simply as the skeleton DAG that fired along with the vectors that were flowing along the edges of this DAG. So it's relatively easy to store this DAG and the set of firing vectors along these edges. And here is a very simple way to do it. You can just take the DAG and the firing values, and you can somehow map it to a dense vector. And the dense vector is sufficient to, from the dense vector, you can actually tell which modules fired with what values. And to see that, just look at one flat hierarchy of modules. So let's say you have thousands of modules in your mind, and only, say, a couple of modules are firing, like the person recognition module and the speech analysis module. So you can just, you want to remember which modules fired and the vectors that came out of those. All the others are producing 0 vectors or not firing. So you just do simple subspace encoding. That is, you just map the output of each module into a separate subspace. And if you do that, it's simply a linear transform, which means that you have a separate rotation matrix that takes the output of a module and packs it in some subspace, in a different subspace, and you just add them up. And you need to make sure that the output, and you get a single sketch for this event. So you need to make sure that the dimensionality of the sketch is more than the dimensionality of each individual output. So if let's say k modules are firing here, each of dimensionality d, then the sketch better have like a little more than kd dimensions in it to make sure that it preserves all the information about the sparse set of modules that fired. So maybe like if you have like kd log n, where n is the total number of modules, that's fairly enough to recover back the exact set of modules which fired. And this is the reason you can do this is because you can just use sparse recovery. You know that the final signal is a sparse combination of things in certain subspaces, and that's why you can get back the set of things. So one trivial way of doing this is you just look at the final sketch and multiply it with Ri inverse. And if R is a random matrix, then you can just multiply with Ri transpose. So if you multiply with Ri transpose, then those subspaces which have firings in them, they will stand out and have a high norm. But any subspace or module which did not fire will have a very small norm. So you just keep those Ri transpose multiplications which have a high norm, and that'll tell you which modules fired and with what values. So it's exactly like creating a sketch where there are a lot of component sketches in there, as long as the number of components is small. And every component is, you can think of a different type. So you can recover, it's like an object, and you have, the object is a compound type, and it has certain component objects, and then you can, each one is a different type, and you can recover the type of it, and you have pointers to those objects. So as I said, this is exactly like sparse recovery. And in fact, even if you did not know these RIs, to be able to multiply it with Ri transpose, you can actually treat it as a dictionary learning problem. So if you see lots of sparse combinations of these different module firings, then just by using dictionary learning, you can actually figure out these RIs. So in dictionary learning, you just have individual, the xi's are actually scalars, where either the xi is 0 or not. Here is the xi's vector, so it's a slight generalization of dictionary learning. But the same principle applies. It's the same generalization of sparse encoding and dictionary learning. By the way, if anyone has any questions in the middle, I'm perfectly happy to be interrupted and take questions. So this can be used to construct a sketch when all the modules are in one layer and only a small subset is firing. But the same idea can be applied when you have modules in different layers and you have a hierarchy of such modules. The way to extend it is very simple. You just recurse in the sense that when you are taking the output of a module, you don't just put the output vector of that module, but you also recursively compute the sketch of the modules before that fed into it, and you append that into this X2. So when you do that, then when you do the decoding and you find X2, then you've got, in X2, you've got the output of the module 2 itself, but you also have got the recursive sketch of the modules that fed into the module 2. And then you can just keep recursing downwards and you can construct the DAG. Yes, hi. Hi, Rene.
Isn't the model equivalent to simply concatenating all of the R's into a single dictionary, concatenating all of the X's into a single vector, and then requiring block sparsity in the sense that...
Essentially, yeah. The actual thing is a little more complicated. So to get certain guarantees, certain kinds of provable properties, you need the RIs to be have a certain structure. Like it's not a random matrix, it's actually identity plus a random matrix, and then some further additional block structures in there. But essentially, but at a high level, what you're saying is correct.
And what is the reason for requiring the R sub i's to be rotations?
Yeah, they don't have to be. I'm just saying that even if they were just rotation, actually, these are not square matrices. These are like rectangular matrices because naturally the output dimension has to be more, has to have enough dimensions to pack a couple of these xi's, which are non-zero. So why is it rotations? No, they don't have rotations. Just rotations also works. So you could do something more complicated.
Thanks.
So you can build a recursive sketch that can be used to encode a DAG of firings, a DAG of firings in this way. And it gives you a dense representation of this DAG. And you can decode it to get back the original DAG of firings, as long as the DAG is small and sparse. So what this does is it constructs one uniform sketch space, and you have concepts or representations of events in this sketch space in such a way that events that are similar will tend to get sketches in related directions, and which are very different, they won't have things in the same direction. And for example, if you have a meeting with some person on some topic, then the sketch of that compound event, which is the meeting with the conversation and the person, that sketch will be related to the sketch of that person, and it also will be related to the sketch of that topic. And the reason it will be related is because one thing as I mentioned, these RIs are not random with mean zero, but actually it is identity shifted, so identity plus random. So if you make it identity plus random, then what will come out is if x1 and x2 are the non-zero, the first two modules are the non-zero things which are firing, and the others zero, then just x1 times identity plus x2 times identity will bring the sum x1 plus x2 in the sketch, and plus the random rotations. So that's why the compound sketch, which involves x1 and x2, will actually be correlated with the individual objects of x1 and x2. So, which means that this meeting, a compound event, you'll be able to reference it into the individual component sketches. And also, when you have subtypes, like you have animals as a class, and then you have different animals within that, those subtypes could be subclusters. So all the animals might form a cluster in, might form a cluster in the sketch space, and separate animals might form subclusters within there. Because maybe you have some animal module that is firing something, and then you see that when animals of the same type are seen, then they all become you get sketches of the same type, and that's why you notice subclusters in there. And this can be used to also infer new concepts by noticing new clusters arising. So up to a certain level of abstraction, if you've already formed a library of modules, then the way you notice a new concept is because whatever representation comes out of these new modules, if you see a new cluster arising in a region which has not been seen before, then you know it's time to allocate a new module and train things about that thing. So, if you've not seen a tiger before, then maybe the representation that comes out of the animal module, you'll form and see a new cluster, and now it is time to train things what to do when you see a tiger. Like maybe you're training yourself to run away, or you're training yourself to remember the patterns in the images of a tiger. So this, so it gives rise to this picture where these sketches form a knowledge graph. So over time, as you go through events, then you'll keep accumulating sketches over time in your life, and they will reference each other based on their relations, and you essentially form a knowledge graph among these sketches. And these sketches are constantly interacting with the modular structure where a sketch is formed based, so when you meet someone over coffee, then you see that sketch, and you put it into this repository of sketches. And when you meet the same person again, you retrieve, you meet the same person again and talk about the same topic, then you get a sketch which is similar to the old sketch. So you'll go back to your database of sketches and you'll retrieve that, and that will inform the conversation that you're continuing with that person. So here are some provable properties that you can show about this method. So one thing is, it's possible to prove that if you choose these matrices appropriately, then it has the similarity preserving property, in the sense that if you have related events where almost the same set of modules are firing with similar values, then you will get same sketches, just because of the way you're composing things into a sketch. So it gives you this knowledge graph structure over these sketches where related events have similar sketches. And also it has this graceful erasure property that we talked about, in the sense that you will not forget things suddenly. Because it is packing an output into a higher dimensional space, so it's taking from d dimensions to, let's say, k times d dimensions. So there's a lot of redundancy in this. So as you forget half the dimensions, you might still be able to recover the outputs. So if you have many outputs from different modules, and especially if you weight them, you give higher weight to the important ones and lower weight to the less important ones, then as you remove half the dimensions, you might still be able to recover the higher weighted ones, and you might forget the lower weighted ones. But even if you forget the lower weighted ones, it doesn't mean you forget everything. Like you might still remember some aggregated properties about them. Like you might still remember the average values or the variances. So if you have, like in a room full with hundreds of people, and if you have a small sketch whose size is not 100 times the representation for each person, you still get things like averages like, okay, what are the typical height of the person? Were most of them wearing dark shirts? And the reason you can get that is because just look at this, the way the sketch is computed. If you have hundreds of things firing, and if each Ri is I plus a random thing, then the sum, with the average value here, will be very close to the average value of all the firings of the different outputs. And you can also get other higher order averages, like the second order moments and third order moments. And the way you would do that is, instead of just taking Ri times x, you could just apply a nonlinearity on these Ri times x and then add them up. So when you add a nonlinearity, then essentially what you're doing is you are not just storing Ri times x, but you're also storing higher powers of it. So you're storing things which have the squares of x, the x, x transpose x, and then the third order, and so on and so forth. So when you take averages, you can get things like this, the first order average and second order variances, and so on and so forth. So yeah, so you can get this kind of average, and it has this interpretability property. You can get counts. It's like roughly how many people were in the room. It also allows you to think about this in an object-oriented fashion, in the sense that you are composing objects into a structure and being able to decompose them. It gives you a protocol-independent way of communicating between modules. So normally in computer systems, when we communicate, we have to really agree, the compiler has to agree on how classes and their fields are stored, at what offsets they're stored. But here, this is one method, by just this random subspace packing or things of this sort. It essentially lets you communicate in a way where you're not fixing this protocol a priori. You also have this ability to view things in terms of pointers. So for example, you can have a sketch, compound sketch of many things, and from there you can recover the original sketches, or at least some hash of it. So those hashes could be used as pointers. So maybe the actual component sketches are very big. So you're not able to recover it fully from this final sketch. But if you have stored them in your sketch repository, then just the hash of it is enough to point it back and to bring out the original thing. So if you actually think further into this thought experiment, then the picture it gives rise in terms of how sketches are forming and how modules are forming is something like this, where you have external phenomena which is throwing in images and sounds, and then you have this table of sketches, and you can use some similarity preserving method like LSH or some other thing to index into it and retrieve out of it. And this table of sketches this table serves both two functions. One is to store sketches of external events, but also to store modules that are trained for different types of phenomena. Because as I said, when you are learning a new concept, all you're doing is you're hashing into a region of this sketch space, which was initially empty or initially had a very low access count. So when you start hitting a bucket where the access count is very high, you know it's time to allocate a new module. So at that, every entry, essentially, you just have a module. So it's like, for seeing a tiger, then you are seeing a new bucket, and you just train a small network to deal with this new phenomena. And there is this routing module which takes external phenomena or a sketch coming from the previously executed modules, and then decides where to index into this hash space, sketch space. So it's an iterative loop where you are constantly accessing some modules in the bucket. You're hashing into a bucket. You're finding modules to execute. You execute those. Those produce new sketches, and it comes back to the routing module. And you combine those sketches in some way, and you decide now a new location to go into this bucket and get new modules, and I keep executing. So it's like an iterative modular loop here. And the routing module is probably complicated. It's not just taking a sketch and it's not taking some output sketch from previous thing and just directly hashing it out, directly indexing into this thing in the next iteration by just doing some softmax. But it's probably doing things like taking a sketch and removing parts which are noisy and keeping the parts which are stable. So for example, if I see the sketch of a face, then I need to remove things like the orientation of the face or specific lighting conditions and keep the more stable parts before I look up this thing. And also, I might need to combine sketches. So if in one iteration, you might not just execute one module, but you might index into a few modules, and you get some output sketches, and you might combine them in specific ways, and then produce the new set of indices to look into. And there is probably also a graph structure across these modules, across these hash entries. And the reason you might have a graph structure is if you see two sketches which are constantly co-occurring, then you might want to think of those two as, create an association between them. So if I see two people are always together, and whenever I meet them, he's always another person, then you want to create an edge between them, or you want to create a compound sketch which captures both of them, and store that, which will reference to both of them. Or if I always see eyes with nose and mouth, then I want to create some association between the bucket entries for those, so that if I just see eyes and nose, I know that I can anticipate a mouth. So as I said, a new concept is just the constant access indexing into a bucket, which had a frequency of 0 earlier, and now it's getting a high frequency. And that's how you allocate a new bucket, allocate a new concept, and you have a knowledge graph structure on this based on co-referencing or association. Any questions? Yeah.
This question of determining whether a new concept has been discovered appears easy to explain, but the implementation of it is, I would argue, non-trivial because,
absolutely, yeah.
Well, first of all, what is, if I've never seen the concept, why is it new? And then how do I determine that I have, what is the computational implementation of popular, that I have sufficiently many new? In principle, I could just set a bunch of thresholds and numbers, but that's not going to generalize across a rich variety of concepts. And in particular, also, it depends on the level of semantic resolution, because say if the concept is face, and I didn't know what a face is, but eventually I might want to recognize your face versus another face.
Yep.
And so how do you implement all of this?
Yeah, so I agree. This is a very, very high level. We'll see some details of it for specific class of images. But I agree this is very sketchy. But some points I want to address into a question is, so you don't want, the clusters may not be just Gaussian clusters of uniform radius in all directions, but it might be a subspace. And that's why the routing module has a very important task of figuring out how to orient sketches or compounds or sketch combinations to remove the parts which are variable and keep the directions which are fixed, and only use those for indexing so that you get very, very distinct tiny regions that map into buckets. So when you have faces, all human faces, it's a cluster provided you remove those directions which are variable across different people. So that's the job of the routing module. Now, when you look at individual faces, then they are further subclusters in that all faces subspace. So it is probably much easier to do that. That is, when you take the sketches of same person to figure out what to remove and what not to remove to point out the single cluster for a person, is probably a much easier task than identifying that single subspace across all people, the face recognition, the face detection problem. So this is another view that comes out from that architecture, is that you have a graph across these modules, because the modules are sitting in these hash buckets, and you're constantly, through the loop, you are constantly accessing one module, and then that spits out some sketch, which lets you go to another module, and so on and so forth. You get a path like this. And you might be have many such parallel paths, like a few such parallel paths. So you always have a couple of or k such sketches in parallel. And the paths could merge, you could shuffle the sketches and get new forks. And also, you might have these associations that I was telling about. The chaining of sketches across the buckets is a very important, I think it's a very important thing, because that could lead to long chains in memory that are very frequently accessed. So for example, if you're cooking a dish, then there's this chain of always, taking a pan, heating it up, and then chopping the vegetables, and there's some specific set of things which are very commonly accessed. So even when you're learning a new dish, to cook a new dish, based on the context, you might go to a bucket and you might see that, okay, there is this frequently accessed chain of events which have high frequency associations. And so you retrieve those and then you adapt it to your new task of cooking the new dish. Some of these edges could be static, some could be dynamic. So these edges could be hardened associations, but they can also be dynamic based on the execution of a previous module. So for example, if you're doing a math problem where you're trying to solve an integral, then you don't know what is the next module I'll apply, but I will actually do some steps, maybe integration by parts, and then that tells me that now I have to apply this next step based on what comes out of the previous module. So they're both static and dynamic links here. And when from a human psychology perspective, when we are thinking through a chain of thoughts, then it looks a little bit like that because we have a thought at a moment and then we execute the thought, and that gives rise to produces the new thought that we then execute. And maybe we can abstract out execution of a thought as looking at the sketches in that thought, component sketches, accessing the modules that are related to those sketches, and then executing the modules and producing a new set of sketches, which forms a new thought. And now look at this, this becomes very similar to transformers in the following sense. So transformers do take a set of sketches, we call them tokens, and it takes different subsets of those by combining them based on attention, and then it runs a feed-forward module on each of these combinations, which produces a new set of sketches, which is a new set of token representations. And you can also think of this as a generalized decision tree or a decision graph, where the nodes of the graph are not just boundary decisions, but they're actually modules. So you get a graph over modules. Any questions? So let's compare this with today's transformer architectures. There's a lot of similarity here. There are a lot of architectures today which do combine transformers with some external table of knowledge. For example, you augment transformers with like a table of entities or a table of mentions, and either at the initial layer or once in a while in the middle, you look up which entity, some entities or previous mentions, you retrieve those based on output embeddings, and then you use those. There's also this mixture of experts where instead of a single feed-forward layer, you have many modules there. And based on what comes from the previous layer, you route it to one of the experts. So that is also very similar to what the picture I was showing in the last few slides. But one difference is that it treats this table of entities and mentions, it views this very differently from a table of computational modules, which is the table of feed-forward layers. And there is no real reason to view them differently because they are all ultimately using the same routing property, routing function. That is just routing the previously obtained sketches or previously obtained embeddings and deciding which entry here to go to or which expert to go to. So really you should co-locate these computational modules and the stored sketches, which is exactly what I was mentioning here, that these buckets are storing both sketches and modules. So, and another thing that's missing is the graph structure within these experts on these entities. I think that graph structure is very important. It's important to keep the associations, figure out common paths in those graph structure, and then condense those paths into a new compound subroutines or compound modules that call these individual modules. And you might also want to have this routing table, this routing module it probably needs to have a stack so that it can make recursive calls. So if you get a set of sketches, like tokens in a sentence, you might want to group them into a few sets, like a couple of subsets, and then recursively call modules for each of them, and then combine the answers. It's like, just like we used to do stack thinking, right? Where I have a problem and I use divide and conquer, I break it up into components and I run each one separately and then I combine the results. You might also need RL exploration in deciding these routing actions. So today they use just softmax routing. So they don't explore, let me try out different paths and see which paths, some kind of policy that could be beneficial. So I think that is a very important component. That could be a very important component in having the right ideal router design. So reality is far from, so today's MOE, today's modular, whatever sense of modularity we have in the state of the art, I think is probably far from the true richness that should be there in the design of modularity and in the routing components. And we don't at all see clear semantic DAG-like representations. So it's not like when I see a situation, I can really mark it out as distinct concepts with the right relationships between them. So let's talk a little bit more specifically into this DAG-like representations. What is the exact function of these modules? Ideally, the exact function of these modules is to create nice semantic DAG-like representations that were generating these inputs. So let's just talk about images, and let's talk about cartoon images. And cartoon images are nice because we know that they are generated using simple DAG-like representations using some graphics package. And reality, real things are messy because we don't know if it's completely possible. But maybe what we do, what our minds does is when we get a real situation, we just use the approximate cartoon-like situation that matches this one, and whatever DAG that, we just use that DAG corresponding to that cartoon-like situation. So that's one advantage of theoretically studying these cartoon-like images. So take, for example, this one. There's probably a relatively simple DAG structure in the program that generated this. So maybe there was an object or a node for each individual thing, and for each individual thing, it was composed by using like a head-like shape and with the dress-like thing and the shoes, and then combined together to produce one of them, and then two of them were produced, and then overlaid together with a handshake. So the task of our system is to actually to reconstruct back this DAG or something equivalent to that. So let's see some more details about how to discover concepts in these kind of cartoon images, and particularly in arising of concepts of different kinds of shapes in these images. So for cartoon-like images, here are two very simple building blocks that maybe these are some of the most important building blocks in these DAGs. So these DAGs are like the nodes are functions. They're not just plus operators. They're not ReLUs. The nodes are actually function compositions. So one particular important function might be a polynomial function or a polynomial threshold function. So for example, using polynomial threshold functions, you can generate shapes like ellipses, or using intersections of polynomial threshold functions, you can generate these kinds of things like rectangles and cylinders. And by unioning these, you can build cartoon-like stick figures. Another important one is low-rank products, which can be very useful in finding repeated structures. Like if you have a sequence of birds flying, then you're essentially taking the latent parameters of one bird and then just changing the position in an arithmetic progression. So it has a natural low-rank product in generating this image. And specifically, you can view the image as a map from pixel position to a color. and we are trying to generate the DAG or some representation that produces this image. So, for example, there might be some DAG. So just if the image is actually a smooth image, then there's probably a simple polynomial, low-degree polynomial that produces that image. So that function will be given by that figure on the right. You're just trying to discover the polynomial. That polynomial is a very good representation of that image. If it is a PTF, then it is just a polynomial with a threshold. So the image of an ellipse can easily be represented by that. If it is a rectangle or a cylinder, then it is a product of polynomial threshold functions, because the rectangle is just the product of the PTFs corresponding to the 4 edges. A cylinder is just the product of the PTF corresponding to the circular surface and the 2 things on the other sides. And then you can have a sum of products or a union of intersections to generate something like this stick figure of a man, and some more such complicated things to get that minions image. So the question then becomes, can we, by looking at the image, can we figure out that polynomials and the set of polynomials, the coefficients and the order in which they were intersected and unionized to produce that image? And as I said, the low-rank products is another very important operator in this DAG, besides the polynomial threshold functions. So even just texture, when you have an image, an object with a certain texture, that is exactly a low-rank product, because you can just remove the texture and represent a monochromatic image, which is just a 0 or 1, and then putting the texture is the same as crossing that binary 0-1 image with a texture vector that is multiplied everywhere. Same with motion. Motion also can be thought of as taking the description of an object and taking the motion parameters, like the position parameters, and then crossing it out so that you have many copies of that object at different positions. And the low-rank representation is a little more general than just the standard one, because first of all, the multiply operation could have some nonlinearities, especially something, it should include like convolutions or Cartesian products rather than just pure multiplication, the matrix multiplication products. And the plus also might need to be a little more general, like it should include occlusion so that you're not just adding 2 images, but you're occluding the parts where they overlap. So here is a simple DAG that you get just by composing PTFs and such convolutions or low-rank products. So if you have an image of a bouncing ball, like a red ball that is bouncing this way, then you have one polynomial that's describing how the center is moving. So that polynomial is a union of parabolas. Okay? And the base object, the red ball itself, is a PTF, is a polynomial threshold function, which is given by the circle thing. And you are now multiplying it with the texture, which is the color, red color. So the entire video of the ball can be obtained by just composing the circle is given by a PTF, but it is parameterized by the centers of the circle, which is a free variable. And you're binding that with whatever comes out of the motion, and you're feeding that, and that is how you're changing the position of the circle. So in the end, the entire video can be written as this kind of product and composition. So it can be thought of as some nonlinear operator on the Cartesian product of the x coordinate, y coordinate, and the time axis. So if you just take the 1 through the x coordinate number of pixels, 1 through the y coordinate number of pixels, and 1 through the time, then that Cartesian product gives you the video, and a simple nonlinear operator on that produces the video of the bouncing ball. So in particular, if the ball is stationary, then the operator is very easy. It's just you have a ball, and the same frame is being repeated. So if you stack these frames together, you get a 3D map where the map looks like a cylinder. So the cylinder is a simple PTF that describes the video of a stationary ball. If the ball is bouncing, then it is a union of PTFs, because when you bounce, one bounce of the ball is essentially taking the cylinder and twisting it into a parabolic shape, where the axis of the cylinder has been twisted into a parabolic shape. And it's a union of such things. So learning is trying to go in the opposite direction. It's going to looking at the video that is produced and trying to come up with this, reverse this thing. It may not do it in the exact same order. And as I was saying, even for repeated structures, this low rank products is useful, like in this bird's case, or even the petals of a flower. You just take the encoding, you're probably taking the operator for each petal, and you're just changing the orientation. And this gives you a very low rank structure, simple low rank structure. And if you recognize this, then even if a petal is missing, you know that there should be a petal there in the right position. So if we can have a method to look at the image and figure out that, okay, there are these encodings of these individual birds, and these encodings are all very similar except that the positions have changed, then it's easier to go backwards and recover such low rank structures. So one, maybe real events, especially cartoon-like events, can be represented well with the small DAGs of such polynomial threshold functions and low-rank products. And maybe when we are looking at such cartoons, or even real-world things, we are essentially reconstructing these DAGs in our mind that produce these cartoons. And maybe transformers also are just doing exactly that. That is, that transformers. So when we are uncovering the DAG, note that this is like learning, per instance learning. That means we're taking that one image or one video and trying to figure out the circuit or the program or the network of programs which produces this one video, which is a function from XYT to pixel color. So we're not doing learning over images or over videos. We're just learning the network that produces this one image or one video. And maybe transformers, as Ima's talk was also saying, that maybe you can view a transformer layer as exactly fitting as unroll loop of gradient descent to fit this particular input into a simpler network. So we won't be able to prove this generally, but we will be able to show that if you just have an image which is some product of polynomial threshold functions, then you can actually figure out this DAG, the two-layer DAG of sums and products that produce this image. And we'll also show that this can be used to create a table of concepts. And by concepts, I mean shapes. So if you have many images with different shapes in them, different unions of different shapes, then we can actually construct a table so that you will get one entry for different shapes. So here is how we do it. So first, what we show is that, let's start with just polynomial. If you have a polynomial, you could do things like, if it is a smooth polynomial, not a threshold, if the image is actually a smooth function which is output of a polynomial, so let's say it's a grayscale image, you could do something like just fit a polynomial, low degree polynomial which produces this. But that's cheating because you don't want to do that. You don't have to specifically do that. You might do more standard learning. And indeed, even very simple things work. Like even if I just do a random projection of a polynomial image, that itself is a good encoding of that image. Just from that random projection, you can get back the original image. And the reason is very simple, because images which are actually polynomial maps are exactly, which are low degree polynomials, exactly have low rank, because they are just union sums of the x squared, x cubed, or small low powers of x and y. So if I just take a random projection of that into a vector which is slightly more than the degree of the polynomial, then that's enough to tell me the coefficients, because the basis functions will actually be almost orthogonal even in this random projection. And the sketch that you get is linear in the original image, and it's linear in the coefficient vector, and you can invert it back to the original image. So this works for polynomials, which are not thresholds, continuous functions, but it doesn't quite work for polynomial threshold functions. You can't take the image of a cylinder or an ellipse and take a random projection of it and then say that somehow from there it's easy to tell back the parameters of the cylinder and the ellipse. And the reason that happens is because it's pretty simple. It's because even if I just take a rectangle, or just take an image with like black on one side, white on one side, and shift the boundary. As you shift the boundary, if you just do a random projection, then you will actually, random projection to one dimension, you'll actually get a Brownian motion. You'll get a random walk. And if you have few parameters, if you do dimensions projection, then you're actually getting a random walk in d dimensions. So the random projection of such images is not smooth in the latent parameters. The random projections of polynomial images are very smooth in the latent parameters. So you can't just do it to a random projection. But never mind, I mean, very simple twists work. You just take thresholded versions of smooth functions. So what we prove is that you can train a small circuit of depth 2, which gives you a smooth representation, which we can use to produce smooth representations. And if you take thresholded versions, then you can actually represent those polynomials, and it's easy to train the parameters of the smooth representation. And similarly, you can also deal with unions and intersections of PTFs. And the idea there is to use patches to look at different parts of the images and then try to fit PTFs for each region and then merge them based on similarity. And the sketch size is essentially the number of edges in these unions and intersections. It's just the total number of edges times the degree of each polynomial for each of the edges or the faces. So here is what you do for, let's take a polynomial function. So as I said, just for a smooth polynomial, which is not a threshold, you can just take a random projection, and that is good enough to preserve the original coefficients of the polynomial. But you can also use a different type of projection, which is actually better for thresholded functions. And the different kind of projection is just tile it up into some random tiling into such squares, and then just store the average color in each tile. So if you have a constant number of tiles, like maybe 5 by 5, 25 tiles, and you just store the average value, then you just get a 25-dimensional vector for this entire image. And so this is a different type of projection, and this also works for polynomials. And the reason it works is because this is nothing but a smoothening filter. So if you have a few such random tilings and shifts of it, essentially what you're doing is you're doing local smoothing. So it's like a low-pass filter, like a Gaussian smoothing, almost like a Gaussian smoothing. And as long as the original input is smooth, that is, doesn't have high-frequency components, then you have the information about all the information required in this smoothened version of the image, which is exactly this 25-dimensional vector. If you take these 25-dimensional things, vector, and if you take the sign of the value there, then it can be used to produce a thresholded function, which has sharp boundaries. And you can train these values so that it gets a better match. So, the sketch that you get by this is not the same as the coefficient vector of the polynomial which produces these, but it is isomorphic to it, in the sense that it is enough to recover the original thing, and it is smooth in the original parameters. So you get these smooth representations, which you will not get if you just do a random projection for sharp images with boundaries. So pictorially, it can be represented in this way. So you're training a single model for just one image. So it's per instance learning. So you have pixel positions, and you want to predict the color. Let's say it's monochromatic now. So you're predicting the gray value, the grayscale color. And you're doing this tiling, which means it's like an LSH, locality sensitive bucketing. But just think of it as tiling for now. So you're mapping every pixel position to some bucket or a few buckets, and you're storing the average color there. And to predict the value, you just take the average of the buckets, the few buckets it went to. And this is already good enough for low frequency images. Because for low frequency images, the averaging doesn't change the thing too much. But you can also train the values in this rather than just taking the average. So, for example, if you just take the averages, that you can view that as a first iteration, and then you just look at the delta, that means the error in the prediction, and you just keep correcting the values in there. So if you keep doing this, it's like training the values in there, and we know that there exists the right values here to produce any low degree polynomial. So this is like training this network to exactly match the image. And instead of just predicting the average, if you predict the sign of the average, then you can represent polynomial threshold functions. So, and we know again that there exists some values in here which will exactly map to the ellipse, and it's a convex function because you're only training you're putting a signed version of a linear function, And if you use cross entropy, you can just exactly fit it and learn it. So notice the difference between, notice the similarity between convolutional networks and this. So here, I was doing per instance learning. But if you look at this averaging and tiling, it looks a little bit like CNNs. So CNNs also do this average pooling. And if you unroll the iterations of this power iteration to change the values within each, to keep updating the values, maybe the CNN is doing something similar. So the same idea can be used for intersections of PTF. So what I did before was working for one PTF like an ellipse. But if you have multiple PTFs, like an intersection of PTFs like this rectangle, again, you can apply the technique. The sketch size that you get is going to be proportional to the number of edges and the degree of the polynomial in each edge. And the idea is, again, just break it up into tiles and take a few random tilings, and now learn a sketch within each tile. So if some tiles will have two edges, will have two polynomials in it, but most of the tiles will be pure. That is, they'll only have at most one edge or no edge. So for those tiles, you can get very clean representations. For these corner tiles, which have both of them, you may not get a clean representation using a small size sketch. So, but you just recurse. Whenever you get a sketch which doesn't easily recover this thing, then you break it into smaller tiles, further smaller tiles, and keep increasing things. So you get like a tree-like representation of this rectangle where you're constantly expanding the corners, and once you go to log in depth, then you get a pretty good representation sketch. And this sketch is also like progressive, like you can make it approximately reconstruct the rectangle by just using the initial few layers, and they get finer and finer with more layers. And another thing you do is you don't need to keep this as a tree. You can actually convert this into a DAG. Why? Because the sketches of these two patches are the same, or they're going to be very similar, because they're using the same polynomial. They're constructed using the same polynomial. So you can merge sketches which are similar. So the way you merge is that you use another hash table, locality sensitive hash table, that stores these sketches. And when two sketches are the same, they'll just point back to the same entry in the table. So you just replace the sketch by a pointer into the table. So that converts this into a DAG-like structure. So this exactly gives you a DAG which generated this with this rectangle. And it's producing variable size encodings for different regions. So it's producing a variable size encoding for it's using very small sketches for the pure black and white patches. It's using a slightly more complicated for this one and even more complicated for this one. So that is for learning one image or reconstructing one image. Now let's see how to learn the concept of shape. Like how do you represent the concept of all ellipses or all rectangles? So this point is a little subtle. So just pay attention and ask me if you have any questions. So the important thing to note is that if you look at things in coefficient space, that means you take an image of a shape and you look at it in coefficient space. So look at ellipses. If you could convert the image of an ellipse back into its coefficient vector, so let's say you write it as just ax squared plus bx squared minus some constant, then the concept of ellipse is nothing but a region in this coefficient space. So if you take degree 2 functions, degree 2 polynomials, then there are like 6 coefficients. But let's say for simplicity, we're just looking at the x squared and y squared coefficients. Then the ellipse is nothing but a rectangular region in the top right quadrant. And hyperbolas will just be another rectangular region here. So the concept of an ellipse is nothing but a specific, image or decomposition of this. So you look at this set of points, you take all the different images of different shapes, you put them in sketch space. Here it is only 2-dimensional. And what you will get is one image. But this is a meta image, it's not a visible image. It's an image that you draw by taking sketches of individual images and populating it as pixel values in sketch space. And what you get is this one big image, and a shape is nothing but different regions in this meta image. So ellipse is nothing but a rectangle or an intersection of PTFs, and hyperbolas will be another thing, and so on and so forth. So you can just apply the same algorithm again. So that means whatever algorithm you were doing to study one image and describe it in terms of regions or intersections or unions of regions, you just do that again in the sketch space. You take all the sketches, put them into a map, and they have a low degree, low dimensional structure, and you just apply the same algorithm again, and connected regions in here is actually a concept. And in fact, you don't even need labeled data. Like if these regions are disjoint, I don't even need to label that these are ellipses. I can just say that, okay, I see these distinct regions. Each of them has a continuous structure, has a nice intersection of PTFs. And I can just give them some new names, and these are my concepts. And there you get pretty robust definitions because maybe ellipses are all, you can easily distinguish between ellipses and hyperbolas because in hyperbolas, the B will be strictly far from negative and in ellipse will be strictly positive. So in this representation, things are very far apart in the sketch space. So I think I'm out of time. The main thing I want to point out is that we are far from this pictorial theoretical structure that we see out of this thought experiment. And the whole notion of MOEs and knowledge tables can be thought of as an initial step in this direction, but I think we have a long ways to go. And we need to go a long ways in terms of adding the right ingredients into today's transformer mixture of exposed architecture with tables to get there to create nice DAG-like representations. And at least maybe we can hope for that in cartoon-like synthetic inputs. So that concludes the talk, and here are some references. Happy to take any last few questions.
Right. Thank you, Rina. We already get a lot of questions along the way. Do we have any left questions? Please.
So I was wondering how do the results extend when you have noisy images? So for instance, in all these examples, your images that you are working with are exactly generated from some underlying DAG. What if you now have, let's say, salt and pepper noise in the images, or let's say in the minions example, you have, let's say, a few pixels that are not rendered properly, given the actual DAG.
So if you have random noise, then it's relatively easy, right? Because if you take an ellipse,
but then you have to reconstruct it exactly, right? So doesn't the sketch size blow up?
No, because you don't want to reconstruct it. Like, I don't think we would be reconstructed exactly. We would only be, like, you would keep reconstructing it, and if the, beyond a certain point, if it becomes too big, then you drop at that point. So for a noisy rectangle, you can very easily reconstruct it in terms of up to some high level of accuracy, which is these 4 edges. But to get every pixel right, you will need a very big sketch, so you just drop it at that point. So, or even if you do reconstruct it, remember when I was saying that you combine objects, when you combine objects, you keep sketches of small size. So high level details are always downweighted in that sense.
I see. Thank you.
Is there any other question? If not, Rina, I'm wondering, so if you want to offer some take-home messages for people working on transformers or MOE those days, what should be learned as a practical design choices from those very interesting findings?
So you're asking for what would be specific things to include in today's MOE? In
today's MOE, if someone want to improve that for the next step.
Yeah, I think there are quite a few, 2 or 3 things. One is you want to have a more intelligent routing module, like not just a softmax based thing, but the routing module itself should have its own tables, routing tables, decision trees, that kind of thing. Another is you should not think of MOE as separate from knowledge tables, table of entities, but they're the same things and they should be co-located. Another thing is you want to have a graph across these modules and entities based on co-occurrence, or if you're frequently routing to one module followed by another module, another one, then you could track these paths based on frequency. And you find common subgraphs and make them into like a higher level module, subroutine. So I think that's 3 or 4 things which I think are very important.
Okay. Is Google already trying out some of those ideas?
Well, let's see.
All right, thank you. Is there any more questions? All right, no, I think we are adjourning the morning session and have a 1 hour lunch break. So please come back and we'll see you at 1:30 for the afternoon session. Thank you. And thank you, Rena, again.
Thank you.
Okay, 1, 1. Can you hear me? Here? Hello, hello?
Hello, everyone. Welcome back to our final afternoon session of the workshop. Please join me in welcoming Daniel Sudri from the Technion, who will speak to us about catastrophic forgetting and linear regression and the implicit bias of minima stability.
Thank you very much, Sam. It is a pleasure to be here. And as Sam said, I will talk about 2 different subjects. The first is joint work with my student Itai Evron, postdoc Edward Moroshko, and collaborators Rachel Ward and Nati Cerebro. And we're asking how catastrophic can catastrophic forgetting be in linear regression. Okay, so this will be the first part of two-part talk. So if you don't understand something in this part, you can always, I'll remind you to wake up so you can maybe understand in the next part. Okay, so let's start. So what is catastrophic forgetting or continual learning? Let's try to explain the setting. So we have tasks that arrive sequentially, each with its own distribution. For example, we have an autonomous car, and you want to train the car, and you see the car sees some settings in the morning, and then in the evening, and then in the night. Each time you might drive to a different country, and you want to continuously train this car to learn on all those different environments and times. So the goal is that we learn the model on all the tasks together. So we perform jointly on all tasks together, even though we train sequentially. So what is the problem? One major problem is forgetting. When we learn new tasks, we might forget the previous task we've learned. So this is a nice picture from Couture et al. That shows this, that when we learn one task, we have these 2 clusters we want to separate. We learn some decision boundary, and then we learn a new task. What ideally we'd like to do is to retain the decision boundary on the previous task, but still have good performance on the new task we've learned. So what happens in practice, that there's no reason when we learn the new task, unless we do something, there's no reason that the boundary will still be good on the previous task. So it kind of changes because of the training procedure or the implicit bias of the algorithm, and then we get bad performance on the first task. So that's we want to prevent this forgetting or catastrophic forgetting, meaning it's a very bad forgetting. So a common research goal in this area is finding all kinds of algorithmic approaches and methods to overcome forgetting and try to decrease it. However, I'm trying to focus on this more basic question: why do we actually have forgetting? What is the reasons behind this? Does it always happen? And can we say in what setting it occurs? So this basic question seems to be unclear even in the simplest setting. So what is the simplest settings? As usual, we start with gradient descent, or SGD, on linear regression, right? It's the simplest model. You can try to answer things and try to answer those questions here. So just to, what are the main questions we're trying to understand? First, can forgetting become catastrophic? Meaning we can't fit all the tasks, even in this simple, very basic model. So as a spoiler, the answer is yes. Even in a very simple model, we can get catastrophic forgetting. Next, is there a way to prevent this forgetting in this simple model? Well, the answer is yes. We can do various things. For example, we can repeat the task, just show the task again after some time, or just randomize the order of the task. Both things will prevent this issue of catastrophic forgetting and will show we guarantee to converge to a solution without forgetting. And lastly, how does the task similarity affect forgetting? So if we have 2 tasks and we want to remember both of them, is it better to have similar tasks or different tasks? So there was already previous theoretical work trying to answer this question. For example, Duan et al. In a linear regression model claimed that with high task similarity, you obtain the maximal forgetting. So if you have very similar tasks, you have the worst case. You don't want to have similar tasks. Another work in a different setting claimed something different, that you have intermediate task similarity causing your worst case forgetting. So even though it's a different model, this seems to be a conflicting conclusion, was kind of confusing. So what we find, at least in the linear regression case, that both actually can be true. It just depends on the number of tasks you've seen. So it can be also high task similarity or intermediate. This will be one of our conclusions. Okay, so this is the take-home message in case you fall asleep in the rest of the talk and this part. So let's go into the details. In our setting, we again use continual linear regression, meaning we observe a sequence of tasks, x1 and it's labeled y1, until y1 until xt and yt. And then we learn a linear model sequentially to want it to succeed on all tasks at the same time. And the task we assume, like it's common in deep learning, we always can perfectly fit all the data together because we have sufficient capacity. So here also there exists at least one model, W star, which can fit all the tasks at the same time. So they're jointly realizable. And we just use the simplest fitting procedure, vanilla gradient descent or SGD, meaning we initialize first at 0, and then at each iteration, each task we see, starting from the previous solution, we minimize our loss, just square loss for linear regression, either with SGD or gradient descent until convergence. And then we set the initialization to the next task as the solution to the previous task, and then repeat over and over again. Okay, and the final output of the algorithm will be the last solution we find when we fit to the last task. Okay, so just to define some quantities of interest, what we might be interested of. So suppose there is some offline solution which we can get by fitting all the tasks together. What will be the distance over the solution we get during the task? Distance for that solution to the best solution, this offline solution. So this is one thing we want to know, to understand. And the second thing is forgetting. So what is forgetting? It means what is our prediction on the previous task in comparison to what was the best prediction, like what was the error of our, if we've done optimally on the task, they just predicted the correct label, in comparison to what we predict now after we've seen all the tasks, like how much we forgot since we saw that task. So when we average this on all over the task. So this was a common definition in previous work. And also like Duan et al. So just to small note, this is a bit similar to regret, but it's not regret. Okay, I'll leave it to you to make sure it's something different, and it behaves quite differently from regret. So what can we say here? So just mathematically, because it's linear regression, we solved with SGD, we know that the solution we converge to is a very specific, unique solution. This is the mean norm solution, which can get a closed form formula. You can see it here in the bottom. And now we can start from this point and say what do we get when each time we just get this WK using the solution of the minimum norm. So we can express this in a slightly more intuitive geometric way. Just rewrite the equation and say that each time we're going through a task, what happens is the distance or the difference between the solution to the task to the optimal offline solution, this difference is actually multiplied by some projection metrics. So each time we fit using linear regression, we are actually projecting to a new subspace, which is determined by the new task. Okay, so we have some solution space where we're at, which is the difference from our solution to the optimal teacher, and each time we're getting to a new task, we simply project using this matrix, and get this new solution here. And that's kind of a way to show it. Now, if we do multiple tasks, we just do a product of these projections. Okay, so you can now move from this task of continual learning to just repeated projection. So we formulate this mathematically. Okay, so now again, if we have this final another task, we do another projection until we get to the end. And so it seems that when we learn each task, we contract the distance to the offline solution, right? Each projection is cannot expand; it can only contract or keep things the same. So intuitively, it seems maybe if we just do more tasks, we should converge to the offline solution. Okay, we're kind of monotonically decreasing in our distance to the teacher, to this W star, so we should eventually converge, right? But yeah, if we monotonically decrease, but we not necessarily decrease at a constant rate, we might get stuck at some point. So the question is, do we actually converge? And then another quantity we defined, the forgetting, how can we look on this geometrically in our problem? So the forgetting is just, if you write the expression you had before, you can see it's the sum of these projections, the other orthogonal projections, the complementary projections on all the tasks. And you can just visualize this as the distance between the last, where you are, to all the sum of all those projections back to the previous tasks. Okay, so now we have an expression for the forgetting and distance for the teacher using these projections. The question is now, what can we say mathematically? Some results. So the first question was, can we get catastrophic forgetting? Is it possible to get that we don't converge it all to the teacher? And the answer is yes. So we can construct a series of tasks so that we're arbitrarily bad in terms of forgetting, meaning the distance to the teacher and the forgetting both are bounded by some constant which can go to 1 arbitrarily bad as t goes to infinity. So the intuition behind this example is that we do very small projections in the beginning, so we maintain a constant distance from the W star. We don't really contract so much. And then we do larger contractions in the end, and we get a high forgetting. If we sum all those differences, in the end, we get pretty large forgetting. So we can be arbitrarily bad if we do get such types of tasks. Okay. Now the question, can this be prevented? We don't want to get a high forgetting. So let's look on some setting where we can show it's preventable. So one setting, for example, is a cyclical setting. In some cases, tasks occur in some natural order. For example, I mentioned the time or the day, so morning, afternoon, and then evening. Then you get some repetition in the task. You sometimes see the task again. What happens in this case? Again, each task has a corresponding projector, P1, P2, P3, and then we see P1, P2, P3 again. So we can just write this series of projection as a cyclic operator, which is we simply take some projections, take the product, and then to the power of n, the number of times we see those set of tasks. Okay, so in this setting, it's a well-known field. It's called the alternating projection. It was studied since maybe von Neumann in 49 or the 60s later. So there are a lot of results in this area. So let's see if this helps us. Let's look at the simplest case. So the simplest case is, say, we have 2 tasks, and we want to just repeat between the tasks, go back and forth. What happens? So we have task 1, and then we project to task 2, and then we project back to task 1, task 2, and so forth, until if we do it enough time, like we see that we will converge to this teacher, the best solution. So you can show mathematically that after n cycles, if you do this alternating projection, you can find the rate of convergence. And just using, here we assume that the teacher has some, without loss of generality, it has some scale. So if we use this scale, we can write this as just this norm of the projection matrices. And then we can bound this using standard result from alternating projection. And we get this is the function of the angle between the subspaces. Okay, so here in this 2D example, it's very easy to visualize this angle. But more generally, it's the smallest principal angle between the tasks. Okay, so when you have a small angle here, this is bad, because this will converge very slowly. We'll have small angle, the cosine will be close to 1, and we'll have very slow convergence to the teacher. So essentially, it could be arbitrarily slow. If we have the worst case task, then still forgetting can go very slowly to 0, which is bad. So this is distance to the teacher, sorry. So distance to the teacher can be arbitrarily slow convergence. So, right, because again, if you have this, oops, sorry. if you have this very small angle between the tasks, then you do very slow convergence. So what about forgetting? So we talked about distant teacher. However, forgetting has a more favorable behavior. If you write forgetting for this analysis, which was actually, this part was not explored in the alternating projection literature. This was kind of novel. We get a different expression where we have this 1 minus cosine times this cosine to the power of the number of tasks. And now this expression is actually upper bounded universally. This is all the principal angles, and you can upper bound it universally with this decaying function as a function of n. Okay, 1 over 4 en. So it doesn't matter which angle you use, you know the forgetting will always converge to 0 with this upper bound. Okay? So this is actually a sharp upper bound. You can show lower bounds. So what do I mean by sharp? So it's not tight, because for every n, you will decrease exponentially, right? It makes sense. You do alternate integration, you have decrease exponentially, but you can go a very slow rate. However, this sharp upper bound determines that you can't get eventually slower than this power law. Okay, so you can get very slow exponent, but the power law is upper bounding all those exponents. Okay, so that's kind of a nice universal behavior we get here for t equal 2. And what happens if we don't do repetitions? We just do 2 tasks. Okay, so we have n equals, here n equals 1, and we have this expression. So what can we say about just 2 tasks? So if we look at this expression, we know that if the angle is 0 or pi over 2, meaning the tasks are identical or orthogonal, then we get 0 forgetting. So that's the good situation. Exact similarity or exact orthogonality are the best cases. What is the worst case? So if you look on the worst case, it's actually the middle here. It's the angle 45. So this is for 1, if we don't do any repetition, n equals 1. So we see that if we don't do any repetition for 2 tasks, we get the worst case, the maximal forgetting, and what is when both tasks have intermediate similarity. They're not exactly the same and they're not orthogonal, there's something exactly in the middle. However, if we increase the number of repetitions, we get that the maximum point of this expression is actually getting smaller and smaller. So if we see a task a lot of times, we actually get that the worst case is in a high similarity. So very similar task will actually converge slower. Okay, so this kind of reconciles previous observations and results in the literature. Okay, what about the general case, more than 2 tasks? So there we can derive a bound, again, the universal bound, which depends on the number of tasks, the number of repetitions, and we can either have a dimensionless bound, which has worse dependence on n and t, and with dimension we can get a better dependence on t and n. So we think it probably could be improved. It's hard for the last iterate analysis, but with averaging you can get around t over n. So you can, for some setting, you get better performance. Another case you can prove a bound, again for general number of tasks, is if you do random ordering, stochastic ordering, not cyclic ordering, with or without replacement. So this means that in that case, we look at the average forgetting over this random ordering of a task, and we see that it behaves as 9 over d to 9 of d over k. So again, if you do averaging, you can get rid of this dimension constant. Okay, so in this case, actually, if we do, you can prove it for both if, with, and without replacement. So without replacement case tells us that because this does not depend on, because this does not depend on t, it means that we can actually show an infinite number of tasks at random order, and it will still be, you get forgetting going to 0. So you don't need to repeat the task, you just need to show them at random order. So this is also showing that it's random order claim. Okay, so how is this relevant for practice? So this is, for example, a recent paper scaling the number of tasks in continual learning that showed that actually if you do use task repetition, you don't have much forgetting. So what they did there, they chose 2 classes. I think it's from CFAR, 2 classes from CFAR. This is, each task is 2 classes. And then these are the different tasks, and then the test set was on all the classes together. And they use vanilla SGD to train the network. And if you just repeat the task, they have a lot of tasks. I think or here it's MNIST, but they also have CFAR 100. And if you do this repeatedly, you actually get convergence to pretty good accuracy. So it seems that repetition indeed prevents forgetting. So it was kind of nice, and also 2 previous work that showed that. Okay, just to summarize this first half of the talk, generally we showed that even in linear regression, forgetting can be catastrophically bad. You might forget everything. And we quantified the exact effect of task similarity, how tasks should be similar to be good or bad in terms of forgetting. And we showed that if you do sit, click, or random ordering of the task, then forgetting diminishes linearly with the number of seen tasks. Also in the paper, we show other things we didn't mention here. What are the conditions for zero forgetting, which are more general than just the zero angle or orthogonal data. We have matching lower bounds. Well, not tight lower bounds. We have lower bounds. There's some gap there. And then we talk about the relations to other algorithms, catch-match method, alternating projection, stochastic proximal point algorithm, and many more. Okay? So, yes. Questions about this part? Yeah.
A couple of questions.
Yeah.
The first one is in the realizability assumption.
Yeah.
There is no reason to believe that the W star is unique.
Yes.
And all of your distances were distances to one W star. Shouldn't you have used a distance to the set of all global minimizers?
No, because this it's interesting because you do all your in gradient descent and SGD, all your iterates are lying on the manifold of the data. Okay, so it means that if you go over all the tasks, you can only converge to the minimum norm solution on all tasks together. So it is unique because it has, because of this property, it has to be the minimum norm solution.
Of implicit bias, okay. The other question is, it seems that this is a problem of vanilla SGD more than the fact that forgetting is a general phenomena there. Namely, there are all of these techniques where you rather than just following the gradient, you project onto the space or the subspace corresponding to the previous tasks.
Yeah, there were previous methods like that.
And so isn't it the case that if you do that, then you don't need to do random, you don't need to see new examples?
Yes, you don't need it, but there is a cost to that,
okay.
Right? You need to store the data in some ways. Like storing the data or projection, it's has pretty high cost.
Well, in general, maybe yes, because you need to store the data. But here, because it's linear regression, you just need to store a basis for the subspace.
Yes, but I think in practice, like in neural networks, people do that, and it has some limitations. Eventually, you run out of budget. You can't do that. I think also other linear regression, right? You need to store subspace times the number of tasks you saw. So that could be quite a lot.
No, because here there is just one subspace, right? At the end of the day, you're trying to intersect multiple subspaces. They're all linear. You're trying to find a solution W that is in the intersection of a collection of subspaces. And so every time you get a new task, you're just reducing the dimension of the intersection.
Intersection of the new task, I see. Yeah, I guess that could help. I think there are still some issues there in terms of, we can discuss this offline. Okay. Any more questions? Okay, so I'll keep going to the next part. Okay. So yeah, so the next part is about the implicit bias of minima stability. This is a joint work with Rotem Mulayev, Tom Michaeli. This is the first work from NeurIPS. And also there's a continuing work with my student Mor Spiegel-Naxon and Greg Ongi, who joined in. It's under review about the implicit bias of minima stability in multivariate shallow value networks. Okay. So the motivation here, we want to understand the behavior of neural networks in an overparameterized regime. And as we know, given some data points, we can perfectly fit to those data points if we have sufficiently large network. However, there are many different solutions we can get. Okay, so the question is, which of those solutions do we converge to with our optimization algorithm? Okay, so this is the algorithmic bias, implicit bias, an inductive bias of the algorithm. So in gradient-based method, there was a conjecture already in 2017 that the implicit bias of the algorithm can be expressed as some form of regularization. And this was actually shown in many works, linear regression, matrix factorization, linear classification, separable data, and many nice examples. However, there is limitation. This does not always work, this analysis. For example, for a mean square loss, it was shown that to get this to work, you need to have some manifold property to hold, and does not always hold. And in some cases, it was shown that it fails. For example, Ohad Shamir and Galvardi had the paper, and also Razin and also here, and Cohen, Nadav Cohen showed this. And so this is one issue. And another issue is we do not capture the dependence of the step size. We don't know how that step size is affecting the results, because most of the results assume either gradient flow or small enough learning rate step size, so we're not much different than a gradient flow. So, however, the step size has quite a lot of impact on the performance and the function we get. So if we train a neural network with some small step size, so we see the loss function is decreasing, and we get a function that perfectly fits the data point, and this function is quite changing rapidly, like it's changing quite a lot. It has high frequencies or overfitting. However, if at some point we increase the learning rate, and then we train with this high learning rate, we see that the function we get in the end is much smoother, at least in this middle part. It's actually quite, there's a large slope here in the end, but in the middle it's much smoother. So this seems like it's overfitting less. And also in practice, people use high learning rates to get better performance in terms of generalization. So it seems that high step size does get better performance. So it's maybe good practice to use high learning rates. So we want to understand this. And to do so, we use the property that SGD converges to stable minima, or gradient descent converges, and SGD goes to there maybe with some noise. And this property always holds. If you converge to a stable minimum, we have some property that has to hold. So we can use that property. So what do I mean by stable minimum? So we have different types of minima. We can have flat minimum or sharp minimum, minima. And if we use gradient descent or SGD on flat minima, then we can converge to the minimum. However, if we use the same learning rate on sharp minima, because of the dynamics optimization, it can escape exponentially fast. And so we call this a stable minimum, and the other one an unstable minimum. And so the condition for gradient descent to be stable is that the lambda max, the maximal eigenvalue of the Hessian, will be smaller than 2 over the step size. Okay, and if it's higher than 2 over the step size, then we're unstable. We will escape exponentially fast. So for gradient descent, this is a necessary and sufficient condition, and for SGD, it's just a necessary condition. Okay, and then we'll use this condition to derive our results. So what do we show in this work? Just to summarize, first, the problem is that to use stability in ReLU networks is problematic because they're non-differentiable, right? So how can you use stability for non-differentiable minima? So we devised a framework for analyzing switching system, which is more complicated than just differentiable minima. And we show that with large step size, we do converge to a smoother function, like we saw in the results, meaning it's not only smooth, but smoother in the center of the training distribution, but not in the outside distribution. And we verified this behavior experimentally. So in this talk, I will focus about the two last parts, because the first part is more complicated to explain. Okay, so we focus first on the very simple case of a univariate shallow ReLU networks, meaning our input is scalar and the output is scalar. So we have first layer W1, B1, ReLU, W2, B2, and then we get a scalar again. So this is the function we have, the neural network, and we have a ReLU activation function. So we denote by this calligraphic F as the set of all functions of this type, all the ReLU functions. And for a given k, it's a piecewise linear function with k knots, k breaking points. And we train this using a quadratic loss, MSE loss, on a certain all the data points. And we assume that we're in an over-parameterized regime, so the number of neurons larger than the number of data points. So we can get a small error and specifically get to 0 error, perfectly fit all the data points. In this case, there are infinitely many solutions, and I'm trying to see which solution are the one corresponding to stable minima. So to answer this question, we first had to answer some more basic question: how do you define the flatness of some function? So we say we converge to this function with a neural network. What is the flatness or the lambda max of the Hessian for this function? So it's not really clear because there are several implementations we can use for the ReLU networks to implement this function. One implementation can be flat and one implementation can be sharp. For example, if we just scale the layers, just multiply the first layer and the second layer by some constant, and we change them, we can change this sharpness quite arbitrarily. So there is some ambiguity, and the way we propose to solve this here in this case, we just, if we define the set of all parameter vectors that implement the same function as a capital omega of f, then we focus about bounding the flattest implementation, meaning the set of parameters that have the flattest lambda, the smallest lambda max of the Hessian, the least sharp. So we'll show why is this useful. Okay, so now I want to ask how flat is this flattest implementation where we're learning with a certain step size. So our first lemma that everything builds on is that this flattest implementation, the lambda max of this case, the flatness, is lower bounded by 1 plus 2 over this, it's kind of a weighted L1 norm of the second derivative of the function. Okay, like the TV norm we saw before. But the difference here, we have this G function. G is a weighting which depends on the data. Okay, so again, it's an integral of the absolute value of the second derivative f times G, and f, the second derivative here is in the weak sense, right? It's a ReLU function, so we get delta. Second derivative of ReLUs, we get delta functions. Okay, so what are the properties of this G function, which is data dependent? It's non-negative. It depends only on the data set. You can get an explicit formula for it. It's just complicated, so I didn't write it here. And it has most of its mass around the center of the distribution. For example, this is, I think, for some uniform distribution, you get this is the G function, meaning it's 0 outside of the distribution support and has this peak in the center. And again, generally it vanishes outside the data distribution, it's 0. So we don't care what happens outside the support of the data. And again, we have this closed form expression for G, but I just don't show it here because it's complicated. And because we know that if we converge to a stable minimum, we have this property that the lambda max is smaller than 2 over the step size. We also know that this stability norm I defined is also smaller than 2 over the step size. Okay, so that's kind of the interesting result here. And why is this important? Because it means that if we converge to a stable solution with SGD of some step size eta, then this stability norm is upper bounded by 1 over the step size minus half. So this is a step size. If we use larger and larger step size, this stability norm will decrease. The function will become smoother. It will have to be to conform to this bound. So this bound we derived under the assumption that we converge to a twice differentiable minimum, meaning the data points do not coincide with the kinks. However, we have analysis in the paper showing the correction in the case you do have some kinks that are coinciding with the data points. Okay, but again, this is in the paper. So now just to simulate to see what we get. So if we have some data point here and we fit them using different learning rates, and here we show the G function we have for this data point, and we will show also the absolute value of the second derivative of the function we have on the left side. So for small learning rate, we get this function which is kind of overfitting, and we see that second derivative in the absolute value is quite high, even though it's a bit lower at the center of distribution, which seems that there's some weighting effect there. And as we increase the step size, we get smaller and smaller second derivative, and the function is kind of smoother. And with higher learning rates, we get much flatter solutions. Okay, so it seems to correspond to the behavior of our bound. And let's look also on the more specific comparison of the bounds, the things we bound. So here we have the x-axis, the step size, and we show 2 over the step size, this line. And if we converge using a one hidden layer ReLU network, we get, because there's this property of edge of stability, you might have heard, it's popularized by the paper by Jeremy Cohen, that we get actually the lambda max is sitting almost precisely on this 2 over eta. We sit almost always on this edge of stability after we converge. And if we look at how this lambda max at convergence is different from the lambda max of the flattest implementation, we see there is some gap, even though this gap is very small for the high learning rates. And if we look at our bound, again, we see this bound is lower bounding this flattest implementation, and the bound is actually not bad with the high learning rates. Okay, so at high learning rates, it seems that we get to capture some of the behavior more accurately. Okay, so far I talked about the very simple case of a univariate neural network. What's with multivariate neural networks? So we had this expression, this integral over second derivative. So what do we get for a multivariate case? So for the R norm you saw maybe previously with the weight decay, you didn't have this G. We get some complicated expression with redundance form. But here actually we can get the more, I don't know, maybe more intuitive expression, which seems like an apt generalization of this. Instead of absolute value of second derivative, we have the absolute value of the Laplacian. And we have this raw function, weighting function, instead of this G, which it has some relations. And again, this is upper bound by the 1 over eta minus half. Again, we call this the stability norm. And we just to get some intuition how it works, so suppose we have some 2D function, right? We have the data points are in blue, and we have the function here in gray. Then we take the Laplacian, we get this delta function, which are the kinks of this function. These are the different delta functions, and each one has different weighting. So this is this part, the absolute value of Laplacian, and we multiply this by this weighting function, which is data dependent. So it looks like this for this data, and then we can calculate the stability norm. Okay, so we can get this exact expression, which is nice. But what can we do with it? So first we can say that, like before, if we use larger step size, then it means the derivative here, the Laplacian, the weighted Laplacian will be smaller, so we get smoother and smoother functions as we increase the step size. And we can also show that if we converge to a stable minimum, we have a stable shallow network, we are not universal approximators, in contrast to standard results, meaning, for example, consider this pyramid function. This is the ReLU over 1 minus the L1 norm of x. Then this function, you can actually implement it precisely using a two hidden layer ReLU net. If you train it with finite step size, there's no problem, you can converge to this ReLU net, you can prove this. And however, if you calculate this stability norm of this function, you find it's infinite. So this means that with one hidden layer, you can't converge to a stable minimum, which is this function. You cannot approximate with any finite step size. So what can we approximate with this stable shower neural network if we can't approximate this function? So it turns out that we can approximate all functions with a certain bounded weighted Sobolev norm. Okay, that is the space of function we can approximate. Okay, so just to summarize this part, we showed that if SGD converges to a stable minimum, then the stable minimum becomes flatter as the step size increases. We must go to a flatter minimum in parameter space. And this flatness in parameter space corresponds to flatness in predictor space, meaning smoother functions. Okay, so that was kind of the message of this part. And this can also lead to better generalization. So it seems intuitive, but can we say more precisely, like what was about generalization? What can we show? So empirically, if we just take this shallow neural network on MNIST, and we check all our bounds, we see the bounds are actually tighter than in the synthetic data case. And if we increase the step size and we go closer to the part where the function is smoother, we actually get improvement in accuracy. Okay, here we use the very large initialization, so it's kind of starting in the kernel regime. So for small step size, the performance is quite bad. So using high step size, you can go far from the kernel regime and get improvement in generalization. Okay, but can we say anything theoretically? So to do so, I just mentioned briefly a result we have from a paper with Moore, Kaviar, Ravichandran, and Nati Cerebro about the implicit bias of step size in linear diagonal neural networks, trying to quantify this generalization performance. So here I'll go to a simpler model to understand the generalization. So this is a very basic, commonly used model. It's a diagonal linear neural network. We have a linear predictor, but the linear predictor is parameterized as some parameter to some power, and we have two parameters so we can represent positive and negative numbers. So this is a very common model to understand implicit bias. And what we show that if we use a similar analysis on this diagonal neural network, we can bound the norm of the predictor we get after optimization in stable minima. We have this weighted norm of the predictor is upper bounded by some 2 over d squared. D is the depth of the network times the step size. So larger step size will cause smaller norm. And specifically, we get this bounded norm which depends on the depth. For d equals 2, and if we assume that the mean of the data is non-zero, which is kind of common, what we get for a ReLU at least, the mean is non-zero. Then we imply this bounded weighted L1 norm, which is kind of similar to the rich regime, meaning we're far from the kernel. You can't represent it using a kernel. And in this case, we can show we can get generalization, good generalization in a sparse regression setting, similar to previous works on this subject. Specifically, if we just do a simulation on this model, when we sample the x's from the Gaussian distribution with some mean and variance, and the label are as sparsely generated with the k-sparse predictor from the xn, then what we see is that if we use very small learning rate, this is the curve, the spin curve here, then for small initialization scale, we get the kernel regime, which has bad generalization. Sorry, small initialization of the opposite. Small initialization scale, we get the rich regime, which has, it was proven before to have good generalization. High initialization scale, we get a kernel regime, which has bad generalization in this sparse regression setting. However, when we increase the step size, we see that the generalization improves until at the maximal step size we can use, we're actually close to this rich regime. We have this good behavior in terms of recovering good solutions for generalization, and we can prove that we get a similar generalization behavior as we'd expect with k polylog d over delta, and there's this constant here which depends on the ratio between the variance and the mean of the data. So if the mean here is 0, actually you don't get improvement generalization. This depends on the mean of the data, which is we didn't expect that. It's kind of curious. Okay, so thank you very much for listening. Let me know if you have any questions about the second part or in total.
Any questions for Daniel from the audience?
Hi, a very nice talk. I have a small question regarding the slide with the pyramid function.
Yes.
So maybe you said it and I missed it, but is the result about the fact that you cannot approximate this pyramid function using a neural network trained with gradient descent some step size, or is it actually that no one hidden layer neural network can express this function?
No, just trained using neural network. We're using a finite step size, and any finite steps you can.
Okay, thanks.
All right, nice talk. I was just wondering if you had ideas for the multivariate case as well, or other losses, or is this very specific to the setting you described?
You mean in the continual learning case? Did they try other?
Sorry, I mean the implicit bias. I'm sorry, the minimum stability results.
The mean stability. Oh, so we can generalize this to other losses which are like have a unique root, like quadratic. For classification, you get different. You can get different things, I think. Yeah, because in classification, for example, on separable data, right, you go to infinity, so it's a bit more tricky. What is how to define minima stability, and is it important? Like essentially, if you train long enough with cross entropy, your gradients will be very small, so you will be stable asymptotically. So it's much more tricky to understand this concept there.
And multivariate, would it be easy to extend, or maybe I missed it?
Was the extension of the multivariate easy, or the extending beyond the multivariate easy? What's the question?
Oh, okay. So I thought maybe I misunderstood, but your results were on f of x. X was one-dimensional, right?
So the first, I had the first part. Oh, sorry. First part. Where was this? No. First part was on univariate.
Right.
So I derived this result, and then I said in the second paper to be extended to the multivariate case, and that's the result there.
Sorry.
Okay.
Hi. My question pertains to the first part of the talk on forgetting. Given that forgetting can be pretty bad, even in the linear regression case, have you thought about alternative formulations of continual learning? Like, for example, you can maybe store some of the data, some of the models, or a scenario where forgetting isn't as prevalent.
Can you repeat the last part of what is the last word you mentioned?
No.
For example, what? For example, you said something.
For example, let's say you can store like data from the past, or you can store maybe store the weights from like previous.
It's a great question. We didn't get to that, but I think it's a great question for a next step you can think of. Yes.
Thank you.
Hi, thanks for the great talk. So in your deep linear model, I forgot, do you have like the bias terms in your?
The linear diagonal models?
Yes.
No, we don't have bias.
Oh, okay. And what would happen if you include the bias terms? Is it like does it change it?
Would it change? Yes, I think it would change because it depends on the depth. The depth is changing. Actually, it's curious. Like, it's kind of in contrast to previous results, and the previous implicit bias results for small initialization showed that as you go deeper, you get higher sparsity. Like we saw one talk here that you have 2 over L norm, right? It's closer to the L0 norm. And this is what happens with higher depth, you get better sparsity. However, if you use higher learning rate, you get the opposite. You go from L1 to L2. Like you get worse and worse in sparsity if you use high learning rates in deep models. So yeah, it's kind of curious what's going on there. And I guess if you add bias or do some non-homogeneous model, it will be different, right? For each component, you will have different behavior because it's diagonal. It's separate for each component.
I see. And another question, is this stability norm for the multivariate part, is this like an upper bound on the R norm, or is it at all related or not?
Is it upper bound on the R norm? I don't. Maybe I don't see why, but if you can prove it, maybe it would be nice.
Okay.
All right, if there's no further questions, let's thank Daniel once more.
Thank you.
Next, we're very happy to have Ivan Dokmanic from the University of Basel speaking to us about statistical mechanics of graph neural networks.
Okay, can you hear me now? Great. So thanks, Sam, for the introduction. It's great to be here. I'm having a blast. And really, I've been learning so much. So this is great. I'm going to talk about some of the work that students of mine and postdocs we did on machine learning in situations where your data sets that you need to learn from are structured like networks. And I have another job that involves running a center for data analytics, where people come to us with all sorts of interesting quantitative data analysis problems. And previously, all this network stuff to me was a little bit like I didn't want to work on it for some reason. But once I started working with people who really need help analyzing data, I realized that at least 50% of these data sets, especially for people who come from life sciences or computational chemistry, which there are many in Basel, where I come from, are in fact problems where you have to learn from networks. And so I think this is interesting stuff. And to motivate learning on networks, maybe I'll recall the usual standard setup that we've been hearing a lot about of supervised learning. So in general, what we do when we do supervised learning is that there is a set of objects that we're interested in that we want to reason about, maybe a set of paintings. And to reason about it may mean something like we want to determine which painting was made by which painter, in this case, either Jean Dubuffet or Georgia O'Keeffe. And the way we want to do it is by building a function. And the way we build this function is we select it from some set of legal functions that we can use. And of course, the one that we want to take, so each function makes some assignment. This one happens to be correct. And the function that we want to take is the one that makes this not too many mistakes. So the way we formalize this is we say that we want that the probability of mistake made by our function is the smallest possible. Now, this is a little bit of a religious statement because it means that we do believe that there is some probability distribution out there that's spewing out paintings, and it can spew out an arbitrary additional number of paintings. That's fine. We don't know anything better, but we don't know this probability distribution. So the best we can do is we settle to work with a set of paintings that we have access to, maybe the set of paintings that are hanging on the walls of a Kunstmuseum in Basel, and we pick the function that makes the smallest number of mistakes in Basel. And then we hope that this function will also make few mistakes in Amsterdam or in the Louvre in Abu Dhabi, right? In general, this works very well. Now, there are all sorts of problems where data points are not, these independent samples from a probability distribution, or they are, but you know a little bit more, right? So you know that certain pairs of data points are in some sort of a relation, right? And this relation could be anything. For paintings, it could be, maybe they were made by the same painter. Maybe they come from the same era. Maybe they use the same kind of canvas. Maybe, they use similar colors. So there could be all sorts of different relationships, but all of them can be encoded by a mathematical combinatorial graph, right? So when we work with this kind of data, where we have some pairwise relationships that can be very, very esoteric and very semantically different, it's a good idea to model them as graphs. And so in this graph, each vertex corresponds to a data point in our data set, in this case a painting, and edges signify whether or not these paintings or data points are in some abstract relation. Typically, we model these graphs using adjacency matrices. So if objects or data points I and j are in some relation, we put a 1 at that position in the adjacency matrix. Otherwise, we put a 0. Right? That's fairly standard stuff, and I guess most of you know it. And this model is extremely sort of realistic and useful. It does model many, many real data sets. Some of my favorite applications are, for example, in neuroscience, where you study biological neural networks. So each neuron is characterized by so to speak, a whole bunch of metadata. Right? So it has a position, physical position in the brain. It has some other biological properties. Maybe we're recording signals from this neuron, so a feature corresponding to the neuron could be the time series. But we also know, maybe from some independent experiments, that some of these neurons are connected, and it's very important for the functionality of this biological neural network. Similar story for, let's say, transportation networks. You can think about cities. You can associate to each city a feature vector. That could be a satellite image, very, very detailed, right? But then there's some independent piece of information that's telling us that some of these cities are connected by air routes, right? And this gives rise to a network. Right? Especially important kinds of networks are interaction networks between molecules. Right? A link in a graph signifies that two molecules, maybe big ones like proteins, interact. Okay? And I'll come back to that. Now, today, if you receive a network structured data set, you're probably going to use a graph neural network to learn from it. And the reason you're going to use a graph neural network is that it works extremely well, and it's extremely simple to describe and to use, right? It makes sense. So, most of these graph neural networks that are being used today work as follows. To each node, or each vertex in a graph, you associate a state. And then you recursively update those states using some functions. And these functions respect the structure of the graph. So in particular, the so-called message passing formulation of graph neural networks works so that each neighbor of a given node that we're updating, that's the yellow node in the middle, computes a message. This message is just a function of the current state of the node that's sending the message, that's receiving the message, maybe some other stuff. And it can be implemented, let's say, using a neural network that is parameterized by some vector of weights data. And then this central node updates its state by computing an update. That's, again, a parameterized function, potentially complicated, potentially simple, that depends on its current state and on some permutation invariant aggregation of the messages sent by its neighbors. Okay. And simple as this paradigm is, over the past, maybe it's just 3 years, we've seen really killer applications in the real world, on real data, that go far beyond benchmarks that we've been hearing about yesterday. And one of my favorite ones is that a couple of years ago, graph neural networks were used as a key, as a centerpiece tool in the discovery of a new antibiotic. It's called halicin. It's actually a known molecule that is structurally very different from all the antibiotics that we have known up to that point. It's hard to overstate the importance of that because everyone knows how dangerous these superbugs, antibiotic-resistant bacteria are. And the reason I think this is particularly significant, more a meta reason, is that the pharma industry has been running these mass throughput screenings since the 1980s. And between these 1980s and 2020, the number of new antibiotics clinical data discovered is 0. Right? So something did change. These functions are really much more precise, much more accurate. They give useful information to people who have to then do experiments and go to clinical trials, right? A completely different application that's very, very recent and again, to me, extremely impressive, is modeling granular materials. Okay? So this is a very important problem. If we want to understand, for example, earthquakes or our planet, we have to understand why certain granular materials like rocks slip. So why there are faults that slip. It's also very important to understand, in civil engineering, structural health, many other applications. And the way the way usually forces are transferred in these materials is that something that is called force chains is formed. So forces and stress are concentrated along some low-dimensional substructures within these 3D bulk things. And it was a very, very hard problem. In fact, completely unsolved. It was considered to be a completely hard problem to predict where these force changes will appear. But a very simple graph neural network, a convolutional graph neural network, turns out to be able to very accurately predict the formation of these force changes in granular materials. So that's, again, extremely important. And if you want to learn particle interactions, simulate physics, compute energies associated with molecules, all of these applications are currently dominated by graph neural nets. Now, since it's so important, it's good to ask the following question. Where do these networks a priori come from in some canonical way, right? So we have these data points, maybe paintings. One way to form a network, even if there's no network to begin with, is if we have some metric associated with our space of data. So for example, maybe just norm of the difference between two images. Now, if we have this metric, what we can do is we can connect each data point to its k nearest neighbors, and we get a KNN graph. Now, that certainly makes sense. It makes sense in particular if your data comes from, let's say, a low-dimensional manifold, then it's related to things like Laplacian eigenmaps that Misha has spearheaded, and diffusion maps, and manifold learning in general. And in some sense, this graph is a proper discretization of your manifold. But it's not the situation that I'll talk about today. And the reason I'm not going to talk about this situation today is that here the graph is somehow a deterministic function of your data, right? So you can use it to regularize some subsequent learning. You can use it to organize your calculations, but it's somehow a very deterministic function of your data, so it inherits the sort of the metric notions that you used to produce the graph in the first place. Okay? Now, there are completely different situations. There are situations where, okay, let's talk about, for example, protein-protein interaction networks. Okay, so now we have these two huge molecules, and they're described by, let's say, their amino acid sequence, right? So in principle, you could run molecular dynamics simulations to determine whether, some pairs of proteins in a big database of proteins will interact. But you cannot do that in practice, because we're still far from being able to, run molecular dynamics simulations at that level, right, of precision. It's just too slow. So for all practical purposes, whether or not two proteins interact, and this stuff is determined experimentally, is an independent piece of information that we cannot just calculate from the data set, right? And so the picture is a little bit like this, right? You have some, latent biochemical mechanism or some other, and this mechanism gives rise both to the protein and it determines which proteins will interact. But these two chains are somehow noisy, and independent to an extent, right? So both give, a little bit more information about the process of protein interaction or the phenomenon. And since this thing has so many killer applications, of course, you'd expect that, or, there's a lot of theory about it. Now, I kind of dislike these statements that we don't understand anything about, we don't understand anything about deep learning, and we have to work. It's a little bit like, I think in this crowd, as if, Kellogg's tells you that eating a huge breakfast is very important. But, but in relative terms, there is even less theory than, if I accept this game, for graph neural networks. And what is out there can roughly be split into approximation statements, or results, and generalization results. Approximation results simply ask, can this message-passing graph neural network compute a certain function? And they're typically framed in a sense of whether the graph neural network can discriminate different graphs, right? And the seminal result shows that they cannot do better, message-passing graph neural networks cannot do better than a certain graph isomorphism test that basically determines whether two adjacency matrices are permutations of one another, right? And then, the generalization question asks, well, if I give you a class of functions, can you reliably learn from finite data sets, right? So, the first question is definitely extremely important. For example, in computational chemistry, you have to be able to distinguish between very similar molecules. In the past, we've had some horror stories where things like chirality, caused really a lot of suffering because they were not accounted for. But this perspective of approximation doesn't explain at all why, when we have features associated to vertices, why is it that very, very simple architectures can learn from very, very few labeled data on very, very, very diverse graphs, right? And I'll talk more about that. So that is basically what I want to talk about today here. So, maybe the emphasis being on the diversity, right? So we've seen that these relations can signify many, many things. They can signify interaction, they can signify similarity, they can signify an error root, right? So why is it that we can use the same architecture for all of these things? Okay, and I want to organize this somehow in three pieces. The first one will be, I want to talk about physics, not mathematics, but physics of graph neural networks. And I'll sort of expound a fairly standard statistical physics program that will give interesting results. And then I'll show you that this physics program gives interesting phenomena that we actually observe much beyond the sort of toy model or stylized setting that I'll be analyzing. And then there's something that I was not planning to talk about, connections between this story and geometry, but since this is a workshop on low-dimensional models in machine learning or deep learning, then I thought, maybe I add that. And it's actually quite nicely related to everything else. Okay, so to motivate talking about physics of graph neural nets, and especially generalization in graph neural nets, let's recall, how normally we study generalization of machine learning models. So a very standard statistical learning theory-based, recipe is, okay, recall that, we would like to select a function out of our hypothesis class, script f, that makes, that minimizes the probability of a mistake. We cannot do it. We take the one that minimizes the number of mistakes in Basel. And what we want to know is, how much worse do we do? Because we did not see the whole distribution, right? So we want to characterize something that's called a generalization gap. And you can show that this thing is bounded by some measure of the complexity of your hypothesis class, which is not very surprising, and then some term that comes from the fact that you're randomly sampling your training set from this distribution, right? And there is any number of these complexity measures. I think we've heard about maybe all of them already at this workshop. VC dimension, Rademacher complexity. Gita earlier today talked about Kolmogorov widths, and so on, like metric entropy, yada, yada, right? And somehow they are similar. Some of them are good for this situation, some of them for that. But it turns out that if you try to carry out this program for graph neural networks, and I'll show you some figures towards the end of the talk, you get results that are utterly not useful, right? In the sense that they do not say anything about the phenomenology of learning on graphs, and in fact, they are completely vacuous. So a quantity that is supposed to be between 0 and 1 is something like a gazillion, right? And so we cannot really use it, neither to guide design, nor to claim any understanding, right? And these are great papers, by the way, technically deep, and so the authors of these papers admit that, right? And so there is a sort of a quest for the right complexity measure, but I'm not gonna do that, right? I'll do something that physicists do, which is I'll postulate a toy model that I can analyze, but the way I'll design this toy model is so that it has some knobs that are problem specific, that are really important for people who do network science and learning on graphs. An example of that was, again, what Misha did yesterday when he showed a precise analysis with, let's say, Gaussian designs, right? So that's something that you can do. And these things have started emerging over the last 10 years. We have these analyses for, let's say, regularized sparse regression based on, Gordon comparison lemma. We have people in physics doing this stuff. We, sort of precise analysis of simple models, right? And I said, I'm gonna create this computational laboratory where I can tweak things, and these things must be relevant to the domain that I'm talking about. So what is one of the most relevant things when you think about complex networks and the culture? What are the conversations that these people are having? It is the meaning of the edge in the graph, right? That's really central. I'll give you an example, right? So if Alice and Bob both know Jane, they're friends with Jane, then it's reasonable to assume that Alice and Bob are also friends, right? But now think about an interaction graph, right? So you have a protein A, which interacts with protein B, okay? And so then A undergoes a small mutation. Now this small mutation is still quite likely to interact with B. But there's no reason that this mutation interacts with A, unless A already interacted with A, right? It's very, very different, because in the first case, what you get are these loops of length 3. You get these transitive relations, triangles in a graph. And links signify similarity, belonging to the same class. While in the second case, what you get are these loops of length 4. You get k-partite structure, or bipartite in this case, and links signify belonging to different classes, right? Totally the opposite. Right? But we're using the exact same architecture, right? So let's try to, see how we can model that. A very good model, a very classical model with a relatively new addition that I'll use is called the contextual stochastic block model. Now, stochastic block model has a long history. It's been used as as an analytic model, tractable, in fields ranging from biology to computer science to whatever. And what a stochastic block model is, it's a graph with a planted community structure. So nodes in this graph, I'll talk about 2 classes, can belong either to class 1 or to class 2. And links between the pairs of nodes are established independently at random, but the probability that you get a link between nodes in the same class is different from the probability that you get a link between nodes in different classes, right? So that's all. It's a sensible model. We'll use a very particular parameterization of these in-class and out-of-class probabilities of connection. And this formulation is useful because it's normalized by the size of the graph. So n here is the number of nodes in the graph. Now, the reason why it's useful is that then we can specify these probabilities in terms of the average degree, right? So we can say that, we can kind of control the average degree. which is an important parameter. And so the way we'll do it is we will say that the probability of connection in the class is this average degree, and then plus some square root of the average degree, some lower order quantity, times lambda. And out of class is going to be minus square root d times lambda. Now, if you think about this, if you set lambda to 0, then these probabilities are the same. You get an Erdős-Renyi random graph, and this graph is useless for learning. You can throw it away. But if lambda is very large, let's say square root d, then you get a graph that's completely clustered, right? Then the problem is very easy. So lambda acts as a sort of a signal-to-noise ratio parameter for the graph, right? It tells you how noisy the graph is. But perhaps, just as important is the sign of lambda, right? If lambda is positive, then we get more connections between nodes of the same class. So we get a homophilic graph. But if lambda is negative, then we get more connections between the nodes of different classes. So we get a heterophilic graph, which is exactly what we wanted. We wanted to have a knob that tells us whether a graph is homophilic or heterophilic and how hard it is to learn on this graph, to classify. Now, contextuality comes from the fact that we also want to associate feature vectors to each graph vertex, right? And so the way these feature vectors are built is basically a spiked covariance model. So each feature vector is f-dimensional for every vertex. U here is some unknown latent f-dimensional vector, and then the feature is this vector is scaled by either a +1 or a -1, depending on, sorry, some people can't see it, but depending on the class membership, right? And then what we do is we add noise. So psi here is noise. And so again, we get a parameter mu here that tells us the relative strength of this feature signal to the feature noise, right? So we have two SNR parameters now, mu for the features and lambda for the graph, okay? That looks good. That's looking good. Okay. And the second part of this computational laboratory is that we're not going to use any general graph neural network, but a particularly simple one, which is called the graph convolution network. Now, a graph convolution is, again, just a message passing network, but the messages are very simple. So the messages that the neighbors are sending are simply linear combinations of the features by some matrix W, right? Or of the current state. And then the aggregation is just the sum, okay? So your neighbors send you linear combinations of their features with the same coefficients, and then you just sum what the neighbors sent you. That looks a little bit like convolution. It is a convolution. Anything else to say here? Yeah, so it's very convenient to write this as a single matrix equation. That'll be convenient for later. So it turns out that we can actually do that if we stack the f-dimensional features into the rows of some feature matrix capital X. This matrix has n rows and f columns for f features. Then it turns out that we can write this update at once as multiplying this feature matrix on the right with the weights. We're used to multiplying it on the left with the weight matrix, but it's just like transpose in the head. And we do signal propagation over the graph on the left using this adjacency matrix A, right? And then we hit it with some nonlinear activations. Okay. One surprising thing about this is that the nonlinear activations don't really help in graph convolution networks, which sounds outrageous, but it's true. So you can try it for yourself. And this has been the subject of several recent works. And state-of-the-art node classification results by GCNs are, in fact, not using intermediate nonlinear activations. Now, people who are used to thinking about feed-forward networks must be, foaming at the mouth, because there, if you remove activations, what you get is a simple linear or affine mapping. And sometimes people indeed call these graph neural nets linear, but it's totally misleading. They're not linear. And the reason they're not linear is that, recall that both the graph and the features are bona fide parts of the input to our network, and we're multiplying them, right? So we kind of interfere the graph and the network. And if you do it multiple times, it becomes very nonlinear. And even more, if you do create your graph from the features, like it's a KNN graph, then actually the entries of the matrix A depend on X in a very smart way. So it's totally nonlinear, right? Okay. And so I use this as a justification to analyze networks without activation. So this is a simple model that we've analyzed. We will do propagation over the graph on the left by some polynomial of matrix A, and we'll use shallow networks. So K will be equal to 1, 2 layers. And then, there will be one set of weights that we'll try to use to perform classification. We'll fit this using least squares, not some classification-specific laws, because we know how to analyze this. But from a practical point of view, we've trained a lot of these things, and it doesn't really matter. It doesn't make a huge difference, right? But this is something that we can actually understand at this point in time. And we're going to work in a proportional scaling. We're going to look at large graphs, and the number of features will scale proportionally with the number of nodes. And you can ask, why is this necessary? It turns out that if you don't do that, the problem becomes very easy. And also, I have to emphasize this. We work in a regime, so all the scalings of all the quantities are set up in a way that the problem is hard. Right? There have been some publications where you don't do that, where things are linearly separable. Right? So that is not so interesting. And why is this scaling good can also be justified in a post hoc way. Right? So it's good because when we look at the phenomena that, sort of our expressions in the end show, they match the phenomena that we see on real graphs. So somehow is a post hoc justification. Okay, and so just to summarize, here's the knobs, of our computational lab that we can tweak. It's the graph SNR, the feature SNR, how many features we have in relative terms, how many nodes do we use to train? I did not say anything about this. So, in graph learning, you have this graph, and so you have to pick some fraction of nodes. I mean, you have labels for some fraction of nodes. It's called transductive, or similar to semi-supervised learning, right? So we use some percentage of nodes to train, and then we also have this regularization parameter. Okay. Maybe I skipped this. And so since this statistical learning theory program which currently does not work for this problem, we turn to physics. And it's kind of obvious that we can interpret any graph as a system of interacting particles, right? So we have some properties associated with these particles, and these properties are determined by the features. And then we have some interactions, and interactions are given to us, right? And so somehow what we want to understand is the meaning of these interactions to be able to learn. And so, you take, a textbook, statistical physics, and you look for, how have people addressed problems where you have systems of interacting particles in the past. Right? Of course, this paradigm has had many great successes. One of the famous stories is understanding ferromagnetism. Right? This is a really important problem, and still is. And so if you look at ferromagnets under a microscope, you see a picture of this set of magnetized domains where particles, little elementary magnets, are all oriented in the same direction. And if you, expose this magnet to a very high temperature, then this looks very random. If you cool it down, it doesn't look so random anymore. Right? So in the early 20th century, German mathematician Lenz was trying to understand this problem. So he built a model, basically, that we're all familiar with today. So he said, okay, let me try to just model this as a system of very simple particles that can be in one of two states, spin up or spin down. And the way these particles interact is that particles like that their neighbors have the same spin. Okay, so we build an energy, or Hamiltonian, corresponding to this configuration, sigma, that is small if neighbors have equal spins. Spins can be an either +1 or a -1. And then, we can add some external field, that's the HIs. And so, the question is like, so what will be the state of this system? What will be the state of the magnet? So you could say, well, I mean, if spins all need to be the same, I'll just set them all to be the same. I get the minimum of the energy, right? But it turns out that we live in a world at finite temperatures, not at absolute zero. And so, what Boltzmann taught us is that we should construct a probability distribution that somehow takes temperature into account, very specific, right? So I'll call it here the Gibbs distribution. And this Gibbs distribution, has a relatively simple form, right? It's very logical, right? So you have some exponential term, and this term is large when the energy is small. That makes sense, right? You have to normalize it. So there is something that we call the partition function that I'll come back to. And there's a temperature parameter, actually inverse temperature parameter beta. Right? So when beta goes to infinity, temperature goes to absolute zero. We're going to use the exact same thing, except that our energy will be our loss function. Right? And we will not look for a distribution over particles, because particles are given to us, and interactions are already given to us. Right? So what we will look for is the physics, the weights of this network. What is the right interaction for which my system has the smallest possible energy? Somehow, what is the interaction in this universe of my data set? And again, well, I'm just repeating stuff, so I'll form a Gibbs distribution now over W's, over the weights, and we'll look at the partition function. Now, this is the following is very, very important, like the important intuition about the Gibbs distribution. If the temperature is very high, there's a lot of thermal fluctuation, and the distribution is very diffuse. All the states are, likely. But if the temperature is very low, then Gibbs distribution will concentrate on global minima of the energy. And if there is a unique global minimum, it will concentrate on that one. To understand why this happens, note that this is just like a continuous softmax, right? So since it's a continuous softmax, if I send beta to infinity, then it concentrates on one atom on the global minimum of H, or maximum of the argument. Okay, this is exactly what I said. And so the reason this is interesting is that now we can use this Gibbs distribution to compute interesting quantities, observables, so things like test error or test accuracy. And the way we compute them is, well, we integrate them against the Gibbs distribution, and then we send the temperature to 0. Okay? And so this will give us the test error for that choice of weights, which minimizes the energy, which is exactly what we want to do. Okay? And so, you can manipulate these expressions a little bit. You can actually see that really the quantity that is the most important, that tells you everything about the system, is the partition function. And there's a trick we can use. We can form something that's called an augmented partition function, where we add in the observable that we're interested in the argument here with some multiplier t. And 2 lines of elementary calculus then show that that expression, the expectation of an observable, is related to the logarithm of this quantity, actually, to the derivative of the logarithm with respect to t evaluated at t equals to 0. Okay? And so that logarithm of the partition function seems to play an important role, and indeed, it even has a name. It's called the free energy density, and that is the quantity that we want to compute. Okay. Now, the thing is, computing this quantity is very hard. So this first quantity that we want to compute is called a quenched average for some reason in physics, and it's typically not possible to compute it directly, right? So we will use physical methods that are non-rigorous, but that are nevertheless, that have been used for the past 40 or 50 years with great success, right? So, and these methods start with the observation that what is much simpler to compute, still not very easy, you need to use random matrix theory, you need to calculate a lot, but it's possible, is the so-called annealed average. So you can take the expectation of the partition function, right? Then you can use, again, some elementary calculus to see that because z is a normalizer of a Gibbs distribution, if I take an integer power of z, this is a normalizer of a distribution of n independent copies of my system, right? So that's something that I can work with. So this thing you can check, it holds. And this thing that's called the replica trick that we use to do our calculations uses exactly this identity, but then it says, now you should pretend that n is a real number. You should click your heels 3 times and take a limit as n goes to 0, right? Okay, so that is that is the non-rigorous part. Nevertheless, Giorgio Parisi 2 years ago won a Nobel Prize in Physics, to a large extent, for his contributions related to the replica method and applications of the replica to solutions of many, many open problems in physics, right? So it's a very powerful framework. Now, the reason this is useful for us is because it allows us to somehow handle this interaction between the graph and the features. So you look at the previous theory papers. Nobody is really talking about how the graph is interacting with the features, but that is really the key question, right? It is also a key difficulty, because if you want to do random matrix theory now for the graph here, for A, that's a binary, symmetric matrix. It's a complicated object. We know some random matrix theory results, right? But it's in general very tedious and complicated to work with it. And so what, I should mention this. So the work is, all the work that I'm talking about here is done by my student Chang Shi, who is sitting here in the audience, right? So I should always say, he did everything. So what he was able to show using replica is that you can write down the free energy as a saddle point of some very low dimensional equation that depends on a small number of so-called order parameters, right? It's like 6, 8. And it has a very particular structure. It's a sum of 2 terms, the first of which only depends on the adjacency matrix, and the second of which only depends on the graph, or on the graph features. Now, the reason why this is powerful is that now we can think about this term. So for example, what if we could replace these binary adjacency matrices by something else that doesn't change the value of this, maybe asymptotically, because we want an asymptotic result, right? And this is exactly what is possible, right? So what is possible is to show that in the limit of large graphs, there exists some Gaussian random matrix, right? And the expectation of this quantity C will be the same, whether I'm averaging over the Gaussian ensemble or the binary adjacency matrices, right? Now, we can again demonstrate this using physical methods in some cases, and in some cases, it's really a fully open conjecture, which you can only verify numerically, right? So this, I think this is a very interesting problem, right? And this is inspired by the work, on the original contextual stochastic block model by, Andrea Montanari and people like Yash Deshpande, who used similar arguments to, prove different things for unsupervised learning. Okay, and now you calculate and calculate, and, you really get not a generalization bound, but what you get is a precise expression for the test risk, right? So this is way beyond anything that, statistical learning theory can currently tell us about graph neural networks. And in some cases, we don't even have to solve the saddle point equation, which is a trivial problem in Mathematica. I mean, it takes, a nanosecond, right? But in some cases, we can even obtain precise explicit expressions, right? There's no need, to try to parse this expression. I'm just showing it to tell you that, we get a relatively simple expression that involves the knobs that I was telling you that, matter for the problem in hand, right? Okay, so now we have this characterization of generalization in graph neural nets. So what we can do is we can see whether it's any good. First, maybe for the contextual stochastic block model for which we developed it, right? And so we can look at the test risk curves as a function of the proportion of nodes that we get the labels for, How many labels in this graph were revealed? So that's a relative thing. That's between 0 and 1. And so here they are. So, the dashed lines are theoretical expressions, and these little crosses are trained networks. So they, of course, match perfectly. Now, what is interesting to note is that, of course, it's not very surprising. I mean, Misha gave his talk yesterday, is that there exists this regime where more training data hurts performance. Now, this regime, of course, also exists classically. Classically, what you vary is not the amount of training data. What Misha was showing yesterday is he was varying complexity. So the way to think about these curves is as a flipped version of the curves that Misha was showing yesterday. And by the way, here, the number of training points cannot go to infinity. Tau can only go to 1. We can at most use the whole graph, and that would not be very, very good if we had to do it, right? So what you see is that the surprising regime is the one where you have very little data, but still adding more data doesn't help, it hurts, right? And of course, as you increase the strength of regularization, again, we've seen this yesterday, the set of interpolation peak goes away, and you get better test risk. And if you're over-regularized, then again, it starts, the blue curve is above the green, right? So it starts getting worse. Now, one meta reason why I think this is very interesting is that, recent work, very good, very influential recent work, claims that there's no observations of double descent in graph neural networks, and that the reason there's no double descent in graph neural networks is that there's all sorts of implicit and explicit regularizations that you need to train them, and so we can just never see it because it's always very regularized, right? But now that we sort of know exactly how to tweak the knobs, we can go to real data sets and real big models, and this is a little bit hard to read, so I'll just guide your eyes. The blue curves are the test risk error, and the white curves are accuracy. And so what you can see is that always there is this counterintuitive regime, right? So in the beginning, in many cases. But if we, so these cryptic letters, they correspond to different regularizers that we like drop out and so on. If you add a lot of regularization, then these curves become monotonic. And so it turns out that, Ono and Suzuki were actually right. Most of the time we cannot see it. Another reason we cannot see it is that we are always looking at test accuracy. It turns out that once you round things to the nearest class, then it does become hard to see it. But if you look at the test loss, right, then you can actually see it, right? So it does exist, of course. The second interesting phenomenon is related to that thing of homophily and heterophily, which is very important for complex networks people. Okay? So what now researchers know is that you will get much better results with your graph neural network, graph convolution network, if you add self-loops, right? And this corresponds to adding an identity to your adjacency matrix. This improves the results by a lot. But people also noticed that if you do this for a heterophilic graph, it actually hurts performance. You have to remove it. So people don't use this on heterophilic graphs. Okay? All right, so what we can do is, we can try to understand it. We can actually look at, where's the laser? No, hopeless. Okay, so we can look at, we can add self-loops to the graph, but we can multiply the self-loop by some scalar C. Okay, so we can control the strength of the self-loop. And crucially, we also allow the self-loop to be negative. Now, if you have, negative self-loops, this gives you, I don't know, like an indefinite Laplacian and so on, right? So this is a bit weird for people who are used to signal processing on graphs, but there's absolutely no reason not to do it, right? And so what you can see is that if, for homophilic graphs, for lambda that is larger than 0, indeed, the best test risk is achieved when you add a positive self-loop. For lambda 0, so erda Šrenji, it doesn't matter. It's always very bad. But for heterophilic graphs, it turns out that the best risk is achieved for a negative self-loop, right? And you can say, well, yeah, sure, on contextual stochastic block model, anything goes. But then you can do this on important benchmarks that are known to be heterophilic, and where usually graph neural nets perform quite poorly. I can explain to you, offline why these are heterophilic. The first one, as you guess, is about chameleons, and the second one about squirrels. And you can see that really the best test accuracy is achieved for a negative self-loop. And see here, it's for a negative self-loop, right? So that's interesting. We can do a little bit more. So we can take a state-of-the-art graph convolution network that achieves the state-of-the-art results and node classification. So this graph neural network uses some sort of filter bank, okay, constructed from the adjacency matrix. So we do one small modification. We add a couple of filters. No, we add just one filter that has a negative self-loop. And it turns out that we get a new state-of-the-art. I personally really don't care about this, but what it shows is that designing the right stylized model is really telling us something about a very non-stylized model. Okay, yeah, this makes sense. Why? What is the mechanistic explanation for this? I wanted this explanation to be very esoteric. And first, I was actually torturing Cheng to find an explanation that involves, the Helmholtz equation and optical diffusion tomography and all sorts of fancy things. And the reason for that is that, in fact, there is a paper that explains why it's hard to solve the Helmholtz equation. You get a very similar thing. And I don't want to get into that now because it's far removed from what I'm talking about here. But it turned out that the explanation is much simpler, and in hindsight, almost embarrassingly simple, right? So anyone who knows any signal processing will immediately understand what is going on. The homophilic graphs are a little bit like low-pass signals. The reason why they're so is that the labels very rarely change across an edge, right? Because neighbors are similar. Whereas heterophilic graphs are a lot like high-pass signals because the labels almost always change across an edge, right? And extreme high-pass signals. And so, if you know your DSP 101, then if you build a filter, a two-tap filter that is 1-1, well, that's just a moving average. It's a low-pass filter, right? And if you build a filter that is -1-1, well, it's a high-pass filter, right? So, and this is really what is going on here. So you want to make sure that you suppress the noise and you don't suppress the signal, right? Okay, that's a very signal processing explanation. Now, I want to, spend the last maybe 10 minutes, or I don't know, less, talking about the geometry behind this, which is maybe not entirely obvious, right? And also, talk about some other work that we did. So, what we did is, so what people do in supervised learning typically is you look at this data set, and then you try to extract information from individual data points. And this is a little bit like this. So suppose that this is your data set. It has n points. Here n is 4. So every point has a feature vector associated with it. And this is an f-dimensional feature vector in our case. And traditionally, we apply functions along these f dimensions, right? So this is how we hit our data. OK. But what we did now is we were also multiplying this feature matrix of ours on the left by something, right? So we were hitting this data set dimension, right? And so we know already, right? So everyone knows that this makes sense. I mean, we've done it before. So this certainly does make sense when, let's say, your data is on a manifold. I mean, then we could do something like Laplacian eigenmaps. Well, this really corresponds to working along the data set dimension, right? And so then we know that it makes sense. So it turns out that there is somehow a connection between this and learning a good representation for data, right? So what we do is we multiply the thing on the right linearly with some weights, and then we hope that this is going to be a good classifier, right? So one way to interpret this graph neural network is that, as always, we're propagating information on the graph, so interacting the data points, and then we somehow hope to compute a better representation, which can be linearly classified, right? So the overarching question here is that of representation learning. Right? So the question is then, we have this data set, okay? It may or may not have some interactions associated with it, but what we want to do for a generic data set, endpoints, a finite data set, is we want to compute a good feature map and find a good representation space, I mean, in any order, right? And what we kind of, okay, so what is a good feature map? I mean, one way to define it is metric, right? So if we do have a metric, which, I mean, I say we do for X, then maybe R is also a metric space. Then one way to say what a good feature map is that is a map that to some extent preserves the metric, right? And so what we do in machine learning in 99% of the cases is that we're using Euclidean metrics, either explicitly, because you're using a Euclidean loss, because you're applying linear operators and yada yada, or implicitly. But what has been becoming clear over the last 10 years is that Euclidean metrics and spaces are not great for some data types that are extremely common. For example, hierarchical data. There's a result of Sarkar in 2011 that says that trees cannot be embedded without large distortion in any Euclidean space, no matter how large the dimension, right? But at the same time, trees can be embedded in hyperbolic spaces of very low dimension. Any tree can be embedded with arbitrarily low distortion in a two-dimensional hyperbolic space. Okay, it looks like this. By the way, the slides were made by my, graduated already PhD student Puyata Bagi. So these beautiful figures. Yeah, I really love it. And so, of course, I mean, there are other data types like cycles. Okay, your data could be roughly a cycle. Again, a cycle cannot be embedded in any Euclidean space without large distortion. But a cycle is very easily embedded in a spherical space, right? So we have to then look at spherical spaces if our data is cyclic. Okay, fine, that works. But what about this? What is this object? Okay, it's a cycle of trees. So what do we do now? You guessed correctly. We embed it into a product space which is a product of a spherical and a hyperbolic space, right? And that works. That's the right choice. You guessed correctly. But the thing is, you can see that this quickly gets out of hand. First of all, how do I know what I should do up front? And second of all, I mean, there's a great variety of things that could happen. So, one question that we could ask is there something universal that we could do? Is there a space that always works? Or do we really have to, do this bricolage? And so, there are some results that have this flavor of universality. One such result is the Johnson-Lindenstrauss lemma, which says that any endpoint metric space, you can embed it in Euclidean space of dimension about log n with a small, with very small distortion, right? So, I mean, there's also distortion here that I'm not showing. But the thing is now, the dimension depends on the size of the data set. So that's a little bit like, can I really have just a single space that always works? Right? So the question is, do this kind of representation exist at all? And the second question is, can they be computed by neural networks? Because this is what we in the end do. We put a linear classifier in the end, but everything before is hoping that this linear classifier or whatever will do a good job, right? And these are very deep questions, that were addressed. I mean, Fields medals went out for these things, and but let's, be a little bit naive. So let's say that, maybe why don't we then maybe find a manifold, like a hyperbolic space, but it has somehow the right curvature? People have done it, you know. They looked at mixed curvature, they try to adapt curvature to different places in the space. That works well. But it turns out that you can show that there are always counterexamples, always, as long as you're in finite dimension, right? So abstraction is that this is too small. Okay, if that's too small, then let's go to an infinite dimensional space. Right? But that is also not solution, at least not alone. Because, you know, it's an old result of Bourgain that you can embed anything in L2, continuous L2 of R, with distortion log n, but there are always data sets that need at least almost log n, right? So again, you know, you suffer large distortion, right? So it's too flat. That's the reason it doesn't work. What we need is infinite dimension and lots of curvature. And it turns out that this exists, but you have to work with spaces of probability distributions, right? And so 8 years ago, Andoni Naor and Ayman published this, you know, really seminal result where they show that any endpoint metric space can be embedded in the space of probability measures over R3. So over a low-dimensional Euclidean, over a low-dimensional space with arbitrarily low distortion. Yeah, it's a very deep result. But what you have to do is you have to, you know, accept some deformation of your metric. So it's not going to be by Lipschitz, it's going to be by Hölder. Okay, I'll tell you what this implies. And you know, the reason this works is that, you know, there's lots of curvature and lots of dimensions, right? In fact, this also works, and this is what we use, this also works for spaces of probability distributions that we can actually parameterize in a computer, like spaces of Gaussian mixtures. So Delon and Desaulnoux published this very, very nice paper about spaces of Gaussian measures that are, sorry, Gaussian mixtures that are equipped with transport theoretic distance, but the couplings are also constrained to be Gaussian mixtures, right? So those things are somehow easier to work with, at least, or more explicit, right? And it's just an intermezzo, you know, a random slide. I mean, to tell you, these metrics, when you go from by Lipschitz to by Hölder, people call them snowflaked. And the reason they call them snowflaked is that, think about Euclidean distance, you know, and points in the plane. Now, if you have a very small distance, and you take a square root, then the distance will become larger, right? But if you have a very large distance, and you take a square root, it'll become smaller, right? So if you somehow want to represent this in the plane, which of course you cannot do, is you have to make a fractal, right? And so the idea is that somehow the shortest paths then become a little bit like walking on a snowflake. So that is the reason you know, for this terminology. What we can show is that using a very simple neural network, which we generously call probabilistic transformer, but it's in fact just, you know, 2 layers of attention, computing the parameters of a Gaussian mixture, we can calculate these embeddings, right? So it's important to know that not only these embeddings exist, but you can actually calculate them, and you can actually calculate them in very small neural networks, right? So we can do even a little bit more. So we don't have to go to R3, we can go to R, but then we get some distortion that is expected, right? Nevertheless, we somehow expect better performance because of lots of curvature everywhere. But if we go to R3, then we can get arbitrarily low distortion. So this is really just, that part is just a mapping of Naor's result. But the point is, we can compute these things with neural networks. Of course, what to do with it is then another question. We can discuss that. We can also get stronger results when we know that the data is structured, right? Maybe a manifold, a tree, a fractal, or something like that. You can just, this is great, right? But what you should ask is, we never do this, and things always work. So we always use either Euclidean or, you know, lately hyperbolic spaces. So why do they work? We know that we cannot embed our data in these spaces. You know? What is more, you know, I mean, if you look at how these proofs for counterexamples, for lower bounds, for distortion, or embedding dimension are made, you usually produce a graph, a metric space, that is worst case. And often this worst case metric space is something like an expander graph, okay? But if you think about the stochastic block model in this regime that is hard, it's expanding, right? So it's a bad situation for these things, right? And the reason this works is that we really don't care. If we're doing binary classification on a graph, we really don't care about preserving distances, right? We only care about classifying nodes as being a +1 or a -1, right? So asking for preserving a metric is a little bit too much. If we could do it, that would be great, because we would have a guarantee that any downstream task will benefit from it. But in reality, we don't really need it, right? And so I somehow stumbled upon a master thesis of Lena Vankadara, if I'm pronouncing that right, who is doing his master thesis with Ulrike von Luxburg. And they're addressing exactly these questions. I still have to understand the implications, but I think this is somehow the right sort of direction to move in, to ask what are the right measures of distortion for machine learning, not for metric geometry, right? Okay, and I'm more or less done. But what this is implying is that, it does not make all that much sense maybe to look for a one-size-fits-all solution, right? To look for a silver bullet or a panacea, right? It's good to sort of adapt your tools to all individual situations. And I think the same is true of explanations. I don't think we should be looking for one universal explanation for machine learning or deep neural nets or whatever. I mean, I don't see like a particularly compelling reason. Now, I show you, so this is my summary slide. What we did is, okay, so we made some progress on analyzing generalization in simple graph neural networks by making this analogy with systems of interacting particles, right? If you look at the bounds that are obtained by, and I should have put the reference here, I'm sorry, but I can edit post hoc. PAC-based analysis, or using Rademacher complexities to analyze generalization in graph neural networks, you get things that look like this. So, oops. The yellow is PAC-based, the blue is Rademacher. These quantities are supposed to be between 0 and 1. The ordinate axis is in log scale, so they are, e to the power 20, right? So they're not between 0 and 1, right? Very, very far from saying anything. And the paper that this is taken from is a great paper. It's really like a technical masterpiece of analysis. Applying this PAC-based analysis is very technical, right? Applying it to graphs and finding a way to do it sort of the right way, but still, it doesn't give much, right? So the improvement is very marginal, right? So that's why I think, it's worth being a bit more open towards the kind of tools that we're ready to use to sort of, understand deep learning. The second thing is, I didn't talk about this, but we use a lot of random matrix theory. Now, this simple signal processing explanation is correct, but there is one thing about graphs that we don't have on grids, and that is that this spectral density of the adjacency matrix, or of the Laplacian, is very inhomogeneous, right? It's interesting. And I believe that by playing on this density, we can get much better representations, right? But then we have to do something more complicated, not linear, right? And the last thing is it's a philosophical connecting, to the panel and to a lot of things that we've been hearing here yesterday, is about, what does it mean to understand? So if I derive these results using, let's say, Gordon's min-max, convex Gaussian min-max theorem, Gordon's Gaussian process comparison lemmas, will I be able to say, oh, now I understand this much better? In my opinion, not. Actually, I understand interacting particles better than, comparing Gaussian processes. And the worst thing is if you remove Gaussianity in these results, then the lemma is not true anymore, right? So this is just a philosophical thought that I maybe like to discuss with some of you. So these are the two references that I described in the talk, and with that, I'll thank you for your attention.
Any questions for Ivan?
Thank you for the very interesting presentation. Actually, my question concerns your part on graph convolution networks, and especially about the assumptions that you made on the adjacency matrix. So what's the degree, like the assumption, the average degree, for instance, or this kind of?
So the average degree has to grow with the graph size, but it can grow arbitrarily slowly. Okay, somehow, as long as it grows, but it grows slower than n, that's fine.
Okay, so the graph, so the adjacency is a dense matrix in some.
No, it's sparse.
It's sparse.
It's very sparse. Okay. Yeah.
Great, thanks.
Hi. So you went into the at the end about how to extend these results for more structured graphs. So I want to know your more comments on. So all these results on lower bounds, they use expander graphs, which are really a very worst case situation. And in practice, for data sets like Cora or the data set that you show, it's nowhere near expander graphs. It's much more well behaved. So what are your comments on what is really missing in how we construct these lower bounds, or what do you think should be done to restrict the class of graphs that we consider to get these lower bounds to be much better?
That's an interesting question. I mean, I agree. So quorum, you know, is it's the homophilic graphs, and especially these things are they are low dimensional somehow. And so so the reason I made the comment is because the stochastic block model, which we analyzed, is not like that. You know, it's high dimensional, but we only need one good cut to classify, right? It's a half decent cut. Right, so a short answer to your question is I don't know, right? This, at least not when it comes to metric geometry, because this is really sophisticated math that I cannot, I don't understand at the moment. As far as machine learning goes, I think it has to be task driven, right? So, and we've heard this, I think it's like on Wednesday, you know, I think the way we have to learn, there's some value in learning task-driven representations. So I think usually people always extol the value of having very, very universal representations. But I think you're missing out if you're not thinking about the task when you're designing your representations, right? And so when you do that, you get, I mean, you quickly see that you do extremely well with these GCNs. Okay, so somehow a tangential related comment. There exist results, there exist fundamental detection bounds for the stochastic block model and for CSBM. In an unsupervised regime, where you do something like a spectral method, right? So you know the information theoretic best bound. And what we can show here is that with just a couple of labels, with a GCN, a really stupid one, we can break this unsupervised detection bound, right? So going back then to your question, you know, I think this is because the task is simple. It's binary classification, right? So I'm afraid that I didn't really answer anything. But yeah, I think thinking about the task, not trying to look for something universal.
Thank you.
If there's no other questions, let's thank the speaker once more. We have a few extra minutes, so we'll take the coffee break and poster session now, and we'll see you back here at 4 o'clock for the final two talks.
How does it work? Okay. There's a screen. Okay. Oh, there's the, oh, okay. Yeah. Okay.
All right, let's get started. Welcome back to the final two talks of the session. Next, we're very excited to hear from Jason Lee from Princeton, speaking about feature learning with gradient descent. Thanks.
All right. Hi, everyone. I'm going to talk about some work today with my student Alex Damian, Maddie, whom you've all heard from 2 days ago, and Chile, whom you've also heard from. Maddie's at USC, of course, and Chile was a former postdoc, now at NYU Courant Institute. Yeah, so today I'll talk about learning representations or features using algorithmically with gradient descent. As a very fast motivation, pre-trained models are all the rage now. A very standard paradigm is you train on some large data set that's not exactly from the same distribution as the data you will test on. You extract some features or a representation from this large pre-trained model, and then you fine-tune or adapt on a small validation set and then use that as the final predictor. So this can be supervised or unsupervised. The pre-training stage both work very well. This figure is taken from this report by the Stanford group. And this is a pretty standard pipeline these days. And my goal of this talk is to understand some simple cases where we can provably learn good features and representations. So the questions I want to look at are what kind of pre-training tasks do we need, what kind of architectures, and how many samples you need to do this. Okay, so essentially the observation in the literature right now is that neural nets can learn representations of the data which allow for efficient transfer learning or in generalization. Roughly speaking, the weights have like magic information in them. They were trained on task A and they can work for task B. So the weights are not only just good for predicting the task that they were trained for, but somehow they learn features and representations that are useful for other tasks that can be quite different. All right. So, starting from roughly 2018 or 17, a lot of the work on deep learning theory has focused on a regime in which it's equivalent to kernel methods. This theory is very useful for optimization if your only goal is to show that the training error decreases to 0 or decreases to an approximate global minimizer. This theory is extremely useful. It's essentially the only generic tool we have even today for proving theorems of that style. Maddie briefly mentioned this. However, this theory cannot explain or even address transfer learning at all because the features never changed. In this, if you forced your algorithm to be equivalent to the kernels, the weights are essentially, the representation layer would be frozen and you could never get any benefit from transfer. You would just have to retrain from scratch. Okay. So for the first part of my talk, I'll look at supervised representation learning, and I'll give an end-to-end analysis using gradient descent. Then if I have time, I'll talk about self-supervised learning briefly. Okay. So here's an interesting toy example. For the first part of this talk, the major assumption will be the covariates. The distribution of the input is Gaussian. So you can tell I'm a theorist. And the signal follows y equal f star of x. Okay, f star will be the ground truth. In this toy example, it'll depend on this fourth order polynomial and only on a single direction. So this function, although the ambient dimension can be very high, it only depends on a single relevant direction, and it's a degree 4 polynomial in that direction. Okay. So this function you can think is pretty simple. If I told you the direction u star, you just fit a univariate polynomials that needs samples, something like order of the degree, and you would be done. Okay. Let's see what happens when we run two standard algorithms. One is the blue line is I train a 2-layer neural net with, it's very standard RALUs, and I used a initialization scheme that's kind of small, the mean field or mu p initialization, they're equivalent. And you can see that the test loss can drop below this line. I'll tell you in a second what is this dotted line. Okay. And this red line, random features or a kernel method, it just levels off and gets stuck at this line. So what's happening here? Essentially what's happening here is that the kernel method, the sample size or the width was constrained to be roughly d squared. So it can only learn as well as a degree 2 polynomial. So the relevant quantity here is to look at log base d of the width or sample size, the smaller, the worse of the two. And that's at best how well a kernel method can do. So here, this line at around 0.7, okay, this thing stopped working anyway. Around 0.7, that's the best you can do with a degree 2 polynomial. So you see that g of x is degree 4. I'm in Gaussian space, so the best you can do is keep the second order Hermite expansion of g, meaning you take the dot product with the second Hermite, x squared minus 1, and keep that. And that's exactly going to give you that line slightly under 0.7. And that's exactly what the kernel method converges to. The neural net, when you start passing number samples, starts passing d squared, you can see there's a phase transition around 2, between 2 and 3, and it starts improving. Eventually, in the beginning, it also cannot do anything. There's just not enough samples. And eventually, it can start passing it, and it can learn to high accuracy. And at the end, you can see that there's some feature learning happening. The neural net one, all of its neurons are in the direction of u star. Okay. Yeah, so here's an animation of what's happening. Sorry, yeah, so we're going to play it a few times. So what happens is that here the dotted black line is the best degree 2 thing. And that's exactly what kernel methods will fit, and they stay there forever. So you can see on the right-hand side, you just go, you fit to that, and you stay stuck there. In the full network with gradient descent, with a kind of small initialization, mean field or mu p, you go to that one, and then you snap out of it, and you eventually will learn the degree 4 thing. And that's also reflected in the loss here. The neural net plateaus here for a brief amount of time, and then it can escape it. So our goal is kind of to get something like this, where there's feature learning happening, and you actually learn the u direction. Okay. Oops. Okay, yeah. So, oops, sorry. I apologize for the question marks. The citation should be to a series of lower bound papers. Some of them are by Andrea Montanari, some are by myself and Tengyu Ma and others. Essentially, this group of theorems say that, that when you have a rotationally invariant kernel, and your number of samples is dimension to the p, you can only learn polynomials of degree p and no better. So if you look at the kernel, either the random feature kernel, the NTK, it doesn't matter which, of a 2-layer net or even any fully connected net of any depth, you need both number of random features bigger than d to the p and sample size bigger than d to the p. And what happened here is one of them was capped, so where at p equals 2, so you can only learn as well as degree 2. And d to the p is a bad result here in the sense that for that previous signal class, you should only need d samples. if you just by parameter counting, the minimax rate for this function class is D. Okay. Okay, so that's exactly what's happening here. Our goal is to show that gradient descent can learn something close to the minimax optimal rate, but in a regime where kernel methods kind of fail. All right. So if I have a polynomial of this type, x1 to the p, and a general polynomial of degree p with arbitrary coefficients, the kernel method, the rotation invariant kernels all need samples and width d to the p. And the question is, can you do better by training a neural net? It's very clear that if I knew my function was like axis aligned like this, then you can get better sample complexity, at least statistically. This is very simple. The main question is how to do this algorithmically. So of course, for arbitrary polynomials, if I want to be able to learn all polynomials of degree p in dimension d, that's impossible. There's just d to the p of them. That's just how many there are, and you can't do better than this. Okay. But for structured polynomials, this is possible. So for the rest of the talk, I'll focus on a special case of structured polynomials, which I think is fairly natural. So I'm going to look at polynomials f star. They're of degree p. There's some normalization here. The output is roughly 1. And there's this hidden subspace s star of dimension r. And the function is of the form g of u star x. So g is general. It's anything of degree p, and it's a polynomial, or it can be more general. It can be anything in a certain RKHS. But for now, let's say it's polynomial, and you have this projector matrix that reduces from dimension d to r. So in the example I showed you, r was 1. There was only one relevant direction. Here, you should think of r as much smaller than d. Maybe there's only a handful of directions that matter, but in the ambient dimension was very large, 10,000. Okay, so what is our goal? And of course, the assumption is you have Gaussian noise, Gaussian covariates or features, and there's some additive label noise on the y. Okay. The learner or the model will be a standard two-layer network of this form. Sigma is ReLU. Okay. And the primary assumption, besides Gaussian covariates or features, will be about the expected Hessian. So this is an important assumption. It's always true that this Hessian has rank at most r. You can just check, you can just calculate the gradient. This doesn't even need that the features are Gaussian. It's always the case, it's rank r. This is intuitive. The function only varies in the r coordinates, so the gradient and the Hessians can always only vary also in those coordinates. But the important non-degeneracy assumption will be that we assume it has rank exactly r. So a bad case is that its rank deficient. For example, if the function f star of x was the 10th Hermite polynomial on the first coordinate, this matrix would be degenerate. It would be just the zeros matrix. And that would be a bad case. In a smooth analysis setting, if you look at the set of polynomials and you add a small noise to their coefficients, this is actually well conditioned. And that's what this assumption is saying, is that the condition number of this we're going to call kappa, and our bounds will depend on this. The division by square root r is correct here. It's because that's the size of the eigenvalues here. So in a function that's well conditioned, this would be order 1 quantity. The root r is just some scaling here. And we know that there's a simple lower bound here you can prove, is that if you violate the non-degeneracy assumption and you restrict yourself to what are called correlational statistical query algorithms, you need at least d to the p, which is what I said was bad, what the kernel methods get. So at least restricted to correlational statistical queries, in some limited sense, this is necessary. This is learnable in the SQ model, though, without this assumption. If someone can ask me after if they're interested in a reference for that. Okay. We're going to look at an algorithm that's a modification of gradient descent. It's not standard gradient descent. The major change is we delete the linear part. We're going to just fit a linear least squares. We're going to get rid of the intercept and the linear least squares. The simplest form of the algorithm is you do one gradient step on the hidden layer and then many on the A's. This part afterwards is not essential. So the prediction looks like this. There's many variants that kind of work. So this is the algorithm. Do one gradient step and then many on the A's. There's many variants that also work. All of them require removing the linear component. The linear one causes some annoying issues. You can do several gradient steps on the W, drop the step size, then do many small ones on the W. This is fine. You can do several ones on the W, then many small ones on the A. These are all fine. You can train both. It doesn't really change anything. The point is you need this discontinuity. You need a place in the algorithm where you drop the learning rate from big to small to force, essentially, for the experts, we all know that when you use small learning rate, big initialization, small learning rate, you can mimic kernels. Okay, this is a well-known result. But the goal is I don't want to mimic a kernel at the random initialization. I want to do it after a little bit of feature learning. And that's what exactly the first phase is here, the one or several steps. I'll look at the simplest algorithm for now, but the analysis and the results are essentially unchanged. Okay, so the intuition, like I said, is that we know how to get neural nets to mimic kernels, at least since like the Rahimi-Rect results, or Amit Danieli had many results of this type, and more recently, the neural tangent kernel literature. There's several ways to do this. You can do it by training only the A's or training the hidden layer with small learning rates. And the random feature is, of course, just a special case of NTK. So if you told me the subspace, the span of the U star, this problem is almost trivial. I would just initialize the neurons at random in the span of U instead of all of RD, right? The span of U is some R-dimensional subspace of the full RD. I initialize at random in this subspace and run kernel method or train the output layer or train NTK. All of these would work. And then I've solved the problem. So the more interesting part is why do you learn good features? Why do you learn the subspace? And you not only need to learn the subspace, you need to learn things in a subspace that are sufficiently still random in that subspace. Okay, so for now, here's the theorem we proved. The sample size is, for this result right now, is quadratic in D squared times some poly R factors. And then the risk is going to be dr to the p. So the ideal thing would be if you had r to the p. We have an extra d here. And this is sort of the transfer learning. If I have m new samples from a new target function, and I train just the output layer. But let me kind of just describe, let's say n and m are equal for now. Oh, sorry, m is the width here. Sorry, m is actually the width here. I'm confused myself. So essentially, you need number of samples, dr plus r to the p. That's sort of what the minimax rate for this class is. And we're off by a factor of d. So it's a minimax rate times d. That's kind of how I would read this result. And the width is r to the p. And this is necessary for this. You can kind of see, even if you just did random features and I tell you the subspace, you would need r to the p. In comparison, kernel methods need both sample size and width d to the p. Okay. Oh, and this funny way of writing is because this is actually the correct way to look at it because I have noise and the noise was size zeta, so I'm subtracting off the noise here. Okay. There's a similar result for transfer learning. Let's say I have a new target function, f tilde. This f tilde depends on the same r-dimensional subspace, but it's a different function. It depends on the same r coordinates, but it can be an arbitrarily different function. So what we do is we pre-train using the feature learning, throw away the head, keep only the hidden layer, and then retrain the head. That's the algorithm. We retrain the final layer. And you have big N samples. So then your rate is now R to the P over N, and it's independent of the dimension, right? You only depend on R. And R to the P is, again, optimal because you can have an arbitrarily different polynomial on the subspace, and that clearly needs R to the P samples. So the transfer learning only requires samples and width R to the P independent of the width. The point here is you're completely independent of width, and in the pre-training, the dependence on the width is a fixed polynomial. It's never D to the P. It's like D or D squared, and actually, I'll talk about later how to make it linear in D. Okay. Okay, so let me kind of just sketch kind of the proof. The idea is not too difficult. We're going to look at the kth Hermite tensor of the target function. That's very simple. That's actually just the expectation of the kth order derivative and then integrated over the data. These are also, because the input is Gaussian, this also happens to be the Hermite coefficients of order k. Like I can take any function in Gaussian space and write it as the sums of the Hermite polynomial tensors with coefficients. And the first order coefficient, there's d of them. And then the second one's a matrix, there's d squared of them. The third order is a tensor of order 3, there's d cubed, and so forth. Okay, so we're going to Hermite expand the gradient. And okay, I've written the Hermite expansion here. This is just a calculation. But what's important is that what you're left with is these terms here. Okay. So these terms disappear because remember, these terms turn out not to matter because I do this linear regression pre-processing step, and so I just remove them. This one's a constant independent of the thetas, the parameters, so it doesn't matter. And the important thing is this one here. So what happens is that you need this to extract information from the kth tensor. You need to concentrate the gradient to accuracy roughly d to the minus k over 2. Okay, so we're actually only going to use the second order tensor, the matrix, so it's k equals 2. And that's where you get the d squared samples from. Okay, so this term is very good. Remember, my non-degeneracy assumption was exactly about this T2, which is the Hessian, the expected Hessian. So this guy times the W is sort of like a random feature in the space, because I told you that the H, the span of it is exactly the subspace. So if I do one step of power method on this matrix, I now get something in the span of U. It's not, perfectly isotropic, and that's handled later in the kernel analysis or random feature analysis, but it's close enough to isotropic up to these kappa distortion factors, which was the conditioning of this T2. So this term is what we kind of care about, and where all of the feature learning is happening, is you're just getting things in the span of the H's. Okay, so roughly speaking, if I have d squared samples times some poly r factors, my gradient looks like something like the second order tensor times the W plus some perturbations. Okay. And then that's exactly what this first step is doing. You get HW, one step of power method with respect to a matrix that has the correct span. Okay. They're approximately Gaussian with the wrong covariance. They're not isotropic on the subspace. They're distributed according to covariance, which has condition number kappa squared, because H has condition number kappa, and they're supported all on the span of U star. So they're like up to kappa factors, poly kappa factors, isotropic on the correct feature space. And then afterwards, you just, then it's very standard. Now, I do one gradient step, I construct the A stars, I can just calculate the norm of the A star I constructed. And it happens to have norm something like r to the p. And then this problem is now even convex in the A's now. So if the existence of a solution plus convexity plus gradient descent convergence and convex optimization, just standard convergence analysis, after t steps, where t is polynomial and everything, you have the loss small and the norm is not too big. And now it's just standard generalization analysis for kernel methods. Is that, you know, this kernel can learn, the kernel induced by ReLUs can learn polynomials of degree p, which I think most of us know already. So then it's just standard Rademacher generalization bound for a two-layer network to bound the risk by the empirical risk, and we've made the empirical risk, we've made the empirical risk very small, and then it's just a standard generalization bound. Okay. So like I said, this result is suboptimal by a d factor. The correct result for this problem is dr, that's the cost of learning the subspace, plus r to the p. Given the subspace, you need r to the p samples to learn polynomials in r dimensions. That's kind of just the rate. And we're off by a factor. Okay, so we've been working on this with Maddie, of course, and Alex for a while. Actually, the second term, this dr to the p to r to the p is easy to improve. You just do some standard data splitting. So in the transfer learning setting, it's for free because in transfer learning, you just have a new batch of data. For the, so we just need to do some sample splitting. And then for smooth ReLU, we're in fact able to improve the first term to a d times r. Okay, and then there's some extra generality which I didn't talk about. Is this g, it doesn't need to be a polynomial as long as it's in the random feature reproducing kernel Hilbert space, everything is still fine because you're just mimicking kernel method at this point. Let me check my time. As usual, I'm very fast. Okay, so there's two future directions that I'm personally very interested in. One that I like the most is to look at the case where your features are now nonlinear. Okay, so so I have a function now that looks like g composed with a bunch of h's. The h's are nonlinear, the g is nonlinear, and I have r of these h's. So essentially, it's a function that only varies on r directions, but the directions are nonlinear, right? It's like only a submanifold matters for the y. Like the data can be anything, but only a manifold mattered. So you can consider a special case where these h1 to hrs are polynomial, g itself is polynomial. The current one is exactly when the h is linear. So the goal would be to learn this. Why is this an interesting model? One motivation is that it also allows you to remove the assumption that x's are Gaussian. For example, if you believe in GANs, let's say x came from a two-layer network, like A, nonlinearity of VZ, then if you can learn things of G of UX, it's exactly of this form. So a non-Gaussian data passed through a two-layer net is exactly equivalent to this kind of two hidden layer net, or three-layer network, essentially. Three-layer net with two hidden layers. So if you can do something like this, you can learn data also that's non-Gaussian. Also just nonlinear features seems to be somewhat more realistic. Okay, since I have some time left, I'll quickly, were there any questions? Maybe I should take questions now for this half. I think that's a better idea. And if there's lots of questions, I don't even need to talk.
Any questions for Jason?
Yeah.
Hi, Jason. Very nice work. I wanted to ask, how likely do you think that these techniques might apply if you just want to analyze plain gradient descent, like without the algorithm modifications you talked about, or like you probably need something totally different?
I think it's, not totally different. I think if R is 1, you can do standard gradient descent. There are some issues when R is big. And kind of one major issue is that, so actually this animation was with standard gradient descent. And also it's R equal 1. So kind of this is very technical, but the issue with, when R is 1, the H is a rank 1. So if you just do gradient descent, it's like power method on H, and you just get the direction, and that's fine. But imagine that H is rank 2 now, and there's 2 eigenvalues of different size. One of them is 1, the other is half. If I do power iteration, I only convert to the top one, and I completely lose the second one. And that's disastrous. And that's the case I think I don't know how to handle.
Let me see.
Yeah.
Okay, thanks.
Yeah.
Hello. So you mentioned that you used network in mean field parameterization, right?
Yeah, everything here is mean field parameterized. Actually, the way I wrote the algorithm is actually any parameterization, but you should really think of it morally as mu p or mean field. Because I added this weight decay step that actually makes it work for any parameterization, but if you don't have the weight decay, it's for mean field.
Yeah. So in this respect, it's interesting. So in mean field parameterization, we kind of naturally have this feature learning ability, even when a width is infinitely big. But if you take, for example, the NTK parameterization, we would also have feature learning ability for finite network, but it would be like of a different nature because of finite width. So did you check like how your results change if you consider either this mean field, wide mean field network or like less wide NTK network?
Okay, so I think you started with saying, okay, first I have some issues with your claim. When they say mean field learns features, it means the features move. It does not mean they proved it learned anything good, to be clear, right? Just because I move my features doesn't mean you've got good generalization error or sample complexity. So to be clear, there's no result in the literature that says, if I do gradient descent on mean field parameterization, I will learn good features. No such thing. So I think basically, and also there's no result I know of using NTK parameterization, but you force the width kind of to be small, and you escape it and you learn good things, at least in any generality. There's also no results, I think, of that type. So I guess, yeah, so I don't really understand your question, taking into account my remarks.
Okay, maybe, okay, thank you.
Yeah.
Hi, thank you for the interesting talk. So just to add to the previous question, so for me, the way I understand this parameterization is that the only difference is that they give you different infinite width limits, right? But for finite width networks, isn't it the same, basically? Because you train maybe with different learning rates, so you get the same kind of representation.
Okay, so there's several confusing things here. Okay, so if you are willing to use per layer learning rates, you can always go between parameterizations. Parameterizations are sort of like, I have enough parameters to mimic any parameterization if you allow me per layer learning rates. So they're equivalent in the sense that if you tune per layer learning rates, yes, you can go from mean field to NTK. Does that answer your question?
Yeah, yeah.
Okay.
So I'll ask one question. Since it's ongoing work, maybe it's too early to say, but I'm curious about the direction you mentioned extending to nonlinear inputs. If you can talk a little bit about what making that kind of an adaptation might entail, in the sense of, do you need to use maybe a different algorithm, like for the sort of linear representation learning? You are taking one step.
The architecture I have in mind is different. Because you can kind of see this is going to be very hard to learn with a 2-layer net, right? Because the first hidden layer cannot really, before the nonlinearity, it cannot express this. But then if after the nonlinearity, so you kind of, the algorithm I have in mind is a 3-layer net with 2 hidden layers. And the feature learning is happening on the first hidden layer. And then you do a small number of gradient updates on the first hidden layer, and you hope those can learn the H's. And then after you get the H's, then you just fit a kernel method over the H's. So the output of if I have, let me see if I have the notation here. If I have a learner that's 2 hidden layers, the output of this part would be roughly the H's. And then to get the G part, I just add another A transpose ReLU of U, ReLU of VZ. That's kind of what I would imagine this looks like. We don't actually have any, the only case I know how to do it now is when, I think, let's see, the H's are homogeneous polynomials, I think. Yeah, when the H's are homogeneous and the G can be general. Yeah, I think that case I think I know.
Thank you. And is there any relationship to the type of analysis you're describing in the backward feature correction that we saw?
That paper is too complicated for me to understand. I don't know of anyone that's read it and said they understood it. Yeah.
Thanks. Any other questions? If not, we still have a lot of time, so if you'd like to
I still have a lot of time? All right.
discuss the rest.
Okay, I'll quickly talk about self-supervised learning. So kind of the setting of self-supervised learning, this is now work with Chile, who spoke a few days ago, is you have pairs of data, x1 and x2. And you want to learn a representation psi that only looks at x1 and x2, and that can linearly predict psi. There's 2 family of algorithms I want to talk about today. The first are based on masking or reconstruction, sort of you corrupt part of the input and then you try to fill it back in. The second one is similarity methods or SimClare. SimClare, SimSciAm, think about that class of algorithms, where you tell it x1 and x2 are similar, usually they're augmentations of the same image. And I was kind of very interested that you have these 2 seemingly different family of algorithms and if there were some intrinsic connections. So this part of the talk is completely statistical. There's no algorithm whatsoever. Okay, so this is a context encoder or mass autoencoder. Pikachu, his eye got deleted, and the goal is to reconstruct Pikachu's eye from the rest of Pikachu. So the architecture looks something like y is going to be a linear function. You learn psi. Psi is the reconstruction function. It takes psi of x1 will be roughly x2. And then you want to add on a head on top of the reconstruction to predict y. So that's the algorithm I'll look at. And that's essentially a context encoder. And MAEs are kind of similar-ish. Okay, so formally this is the algorithm. I minimize over my networks to get the psi. And then I train a head, W, to predict the y. And this works very well in practice. The goal is now, why does this psi get low error? This psi turns out to usually be very low dimensional, but yet y is in the span of the size. So it can linearly separate or linearly reconstruct. The other class of algorithms I'll look at, I wrote down SimSciAm here. I'm going to call it just canonical correlation analysis. It's essentially, to me, it's a nonlinear form of CCA, is SimSciAm. So what is CCA, or SimSciAm? Is you learn 2 functions, 2 eigenfunctions, or singular vector functions, psi and eta. You demand they're orthogonal. Let's just look at the case where they output a single scalar. It's a lot simpler. You try to maximize the nonlinear correlation between x1 and x2. So you're essentially asking, there's also a more intuitive reconstruction form, is basically Given functions that are normalized have scale 1, psi, and eta, how well can I predict psi of x1 from eta of x2? This is exactly CCA. CCA in traditional statistics is a linear form of this. The nonlinear generalization was done by like Brayman and Friedman. They had an interesting name called alternating conditional expectation. And it's a thing in statistics. Okay. So a very simple observation is that these methods are very similar and in a very precise sense. This masking objective in autoencoders or context encoder, the optimum is going to be given by the conditional mean, right? The minimizer of square error is always a conditional mean. So if I want the optimal predictor of eta, it's going to be given like this. So if I had discrete random variables, when x2 can only take on a finite number of values, the mask objective, actually the minimizer, is going to be just a conditional expectation operator, or function, if you like. So just think about the discrete case, the conditional expectation operator applied to a Dirac delta function, everything's discrete, so it's just the conditional probability. And it turns out that the minimizer of that CCA function, you can show that it turns out to just be, you take this conditional mean expectation operator, it's an operator, a matrix, when things are finite, and you take the SVD and keep the top k. And that's exactly going to give you back the minimizer of the sim-psi-m thing. So in other words, this masking objective plus a rank k PCA is exactly equivalent to the CCA for the discrete case. It's easy. So kind of using this observation, I already had a paper on analyzing these masking methods, and all I did in the slides is take all the theorems and convert them to now apply to sim-psi-m. So kind of the regime we're thinking about usually for the masking methods is kind of the joint distribution between x1 and x2 is a nearly low rank operator. That essentially is equivalent to conditional independence. But x2 cannot perfectly predict y. So sort of mixture models, topic models are all of this form. The other case, when I look at sim-psi-m, I'll be looking at when x2 can almost perfectly predict the label, but they're not independent at all. Sort of think of like, if I'm an image and I add some augmentation, the augmented image, although distorted, is still a very good predictor of the label. That's kind of like the second setting. And I'm going to have a measure of how close to low rank it is. Essentially, it's just the left minus the right. And that's how like not conditionally independent it is. Small is good, bad, high is bad. And then the correlation of x2 with y. That's the other thing though. So this slide is kind of confusing, but I couldn't figure out a way to present this well. So you have 2 algorithms and 2 bounds, so that gives you 4 theorems. So the representation error of either algorithm, anyway, is less than either of these 2 bounds. So there's 2 theorems, I take the min of them. The first, and the only thing different for the 2 algorithms is how you define these. One is the measure of conditional expectation, and the definition of correlation. So the only difference is that everywhere you see an eta, it's constrained to be linear in these masking methods. So sort of in the mask in autoencoders, you depend on the linear correlation of x2 and y, but in the contrastive methods, you depend on the nonlinear correlation. Like you can apply arbitrary functions. So rho is only better for the sim-psi-m, but the other side gets worse. When you measure conditional independence, you want to fix eta to be linear, and it gets worse in the sim-psi-m. So there's some trade-off here. And these trade-offs I wrote here below. So kind of, it's just a perspective to tell you that these, you can kind of look at these in a kind of essentially a unified way, that similarity and reconstruction are not too different. And of course, so let me just quickly conclude. For me, the major issue with this kind of statistical analysis only is it tells me nothing about why our algorithms or how our algorithms, the mechanism in which we learn good representations in mass autoencoders or contrastive learning. At the end of the day, I would still like an end-to-end analysis showing that SGD or on some architectures can do this. And that's kind of unclear. And that's all I really have.
Thank you, Jason. Are there any more questions from the audience? If not, let's give Jason another round of applause.
Hello? Okay.
For our final talk, we're very happy to have Fanny Young from ETH Zurich, presenting on inductive bias and harmless interpolation. Let's welcome the speaker.
Right. First of all, I want to thank the organizers for this very nice workshop in a place I've never been to before. And it's been wonderful to hear about all the exciting results in this field in the past few days. So today I just, hopefully not talk too long because everybody is tired, etc. Just present the work that I've been doing with my student, Konstantin, and a lot of master students and more junior PhD students in our lab, and which is about understanding the effect of the strength of an inductive bias on whether interpolation is harmless or not. So I'll explain in a second what I mean by inductive bias. So first of all, we've heard a lot about how neural networks have defied classical wisdom in the sense of double descent, etc. So I'll only quickly go through this first few slides. So this is the slide I usually use for my Introduction to ML course, where, of course, if you use a high-degree polynomial without regularization, you will highly overfit on noisy data points. And if you regularize with, for example, a rich penalty, then you will get a much closer function to the original red function. Okay, so regularization helps in low-dimensional settings. That has been well understood. But there's been this new kind of story, which is for neural networks is not quite the case. So this is an experiment done by Nakaran et al. So basically they looked at noisy C410 samples. So it's important that they add artificial label noise because you don't know whether C410 is actually a noisy data set, or maybe there's almost, or very little noise. So let's say we have noise, then there could be a problem of overfitting, right? So now what is the x-axis? Right, so double descent always needs an x-axis. In this case, overparameterization is reflected by this width parameter of a ResNet. So we have a fixed depth ResNet, and we vary the width. On the y-axis, we have the test error. And all the different curves are the test errors of trained neural networks at a particular epoch. Right? So the blue one is if we take each of these neural networks with different width, we train it until convergence and look at the test error. Right, so the blue one is the one that is trained until convergence, and then there are some intermediate epochs. Right? So what you see here is that for one, that we have this double descent phenomenon, that for the blue curve only, we see it goes down, it goes up, and it goes down again. So this is the one part of the double descent, is that there is a second descent after the first one. Okay, so this has been a bit puzzling, but by now kind of well understood, as we saw in previous talks this week. And then there's a second phenomenon. If we focus now on the very far end, and we not only look at the blue one, but also at the red curve. The red curve is basically an oracle curve, so you look at for each width parameter, which is the epoch that gives you the best test error. But if you're at the very far end, what you see is the blue and the red curve are the same, which means optimal early stopping does not help generalization. But if you're close to the interpolation peak, of course it helps. So as we have seen in many talks, regularization gets rid of the peak. Okay, so we have, for large models, we have that interpolation is harmless. So we have these two phenomena. And the other phenomenon is, of course, that generalization is still good. So basically what we want to understand is, for what kind of interpolators do all three of these properties hold? So for one, we have the second descent, which is overparameterization helps interpolators. Then we have harmless interpolation and good generalization all at the same time. And so what people have usually studied so far is basically we fix one particular interpolator, for example, minimum L2-1 interpolators, and then we look at when can it generalize well, when do we have benign overfitting, meaning that we have consistency as DNN go to infinity for linear models, or when do we even have good rates. And so this usually depends on some sort of spike covariance model where we have effectively low-dimensional covariance. So yeah, also the first point is quite well understood. We've seen these in previous talks yesterday. And so I will focus on the 2 and 3 and when these actually can hold. So we'll see in a second what I mean by this good generalization. So it goes beyond consistency, and it basically is looking at actual high-dimensional distributions in the covariance space, meaning not spike covariances, but isotropic ones. Okay, so we have a lot of interpolation possibilities, right? So in high-dimensional models, over-parameterized models, we can have infinitely many interpolators. So the question is, what kind of interpolators can satisfy all these three properties? So a lot of literature we've also heard this week is focused on, if we take an optimization algorithm that is minimizing some loss, such as gradient descent-based methods, then we have some implicit bias towards a certain interpolator. So this is what's called implicit bias. And so what I'll use a lot in the rest of the talk is the concept of structural or inductive bias. And what we mean by that is, given a certain interpolator, for example, minimum something norm, this norm has, or this interpolator has a structural or inductive bias towards a certain structure, right? An inductive bias towards a structure such as sparsity invariance, certain types of invariances, or small filter sizes. Okay, so basically, we are focusing on, given some interpolator, looking at its inductive bias towards a certain structure. So we're not looking at the left side, only on the right side. So we're not looking at the optimization algorithm, etc. So we're just looking at fixed and comparing different types of interpolators with different strengths of inductive bias here. So, okay. So before I go on and give an example for inductive bias, so we will focus on the case where, again, the covariates are high-dimensional in the sense like isotropic, so we don't really have a spike covariance model. So this is a big difference compared to previous works. And in this case, right, good generalization can only happen if you have some sort of clue where to search, right? So that's the whole idea behind regularization towards, for example, in the L1 case, in the sparse ground truth case, you want to have regularization towards sparse ground truth, right? So if you have really an over-parameterized model and your covariates are really high-dimensional diverse, you really need some sort of clue. Okay, and so you need this inductive bias if you're over-parameterized and you have isotropic covariates. And so the key mechanism for when all of these three holds is now the strength of this inductive bias. Right. So how strongly am I encouraging my interpolator to have this simple structure? So this is going to be the key knob that we will turn, and that is different to compared to previous results, which usually look at the knob of overparameterization. We look at fixed overparameterization and check how the strength of the inductive bias is influencing all these properties. and particular harmless interpolation. Okay, so this is the main story of this talk, that we'll focus on the strength of inductive bias. Okay, so again, so what is the role? So I'm going to actually tell you what we observe first, and then I'll give some concrete results. So the story, the role of the inductive bias is really simple to just illustrate with a very cartoonish picture. So we have these two regimes, right? So on the left side, the x-axis here is overparameterization, the standard one. On the left side, we have underparameterization, right? So we cannot fit data perfectly. Training error is above 0. And then we have beyond the interpolation threshold, we have the second descent, and we can achieve 0 training error. So now we add this essentially second dimension to the overparameterization, which is the strength of inductive bias. So now let's look at classically how we think about strength of inductive bias. So classically in the left regime, right, so say we're kind of close to interpolation, but not quite there yet, or generally what we've, the kind of intuition that we have, if we allow the inductive bias to prevent interpolation, such as in lasso, right, so we add a regularization penalty, then basically our intuition is that the bias increases and the variance decreases, right? So we're shrinking the amount of flexibility to fit the data. That means we potentially increase the bias and decrease the variance because they have a smaller space to search over. Very important here, okay, so here is towards the left side is increasing inductive bias via the regularization parameter. If we increase lambda, variance drops and bias increases. But at the same time, it's important to note that we're allowing the training error to go up as well, right? So we're sacrificing fit to gain some structure, or some simplicity of structure. So this is the classical view of inductive bias strength. It kind of helps to some extent, in particular if it's not too large. So it's somewhere in between, and then regularization can do well. We get minimax optimal rates, etc. So now we're in the second regime where training error is always 0. So how is the effect of the strength of inductive bias in this case? So here the picture is actually the opposite. Okay, so the difference here is, again, we are increasing the inductive bias via some structural terms. And in the case of linear regression, we would be varying the p-norm between 2 towards 1. Right, so p equal to 1 has a strong inductive bias towards sparse solution. P equals to 2 has essentially no inductive bias towards sparse solutions. So this is what you can imagine the inductive bias is doing, or like turning the knob in this case would mean. And very importantly, the training error is always 0. Right, so we're in the interpolating regime. In that regime, the strength of inductive bias actually is varying bias and varies the opposite way. Okay, so as we increase inductive bias, the variance increases and the bias decreases. Now, of course, this is only true if the inductive bias aligns with the optimal parameters or the optimal solution. But let's assume that's the case, right? So we know our solution is sparse, for example. So now the question is, should I choose p equal to 1 or should I choose p equal to 2? Of course, p equal to 2 is probably not true, but not good, but what about p equal to 1? And we see actually p equal to 1 is also not good because the variance is going to be high. So kind of the takeaway here is, if you're forced to fit noise, right, having a smaller or less flexible set, which is the set of sparse solutions, actually increases your variance. Okay, so if you think about, I don't know if I have a slide on this in the end, but if you think about it like this, essentially, previously, right? So previously, you vary your size of the set, and by varying those, the size, you basically say, okay, don't fit the data perfectly, you're going to be closer to your ground truth. In this case, you're saying, still fit the data perfectly, but with a much smaller set. What this means is, for example, if you think of the linear case, and you think of W star is equal to 0, So you have to fit noise when you interpolate, right? But if you have to fit noise with sparse solutions, the norms of these vectors are going to be larger. They're going to be larger, and hence your variance, which is essentially the norm of the W hat, is also going to be larger. Whereas if you basically say I'm allowing all directions, then the vectors that if you're forced to fit noise, then you can choose a vector that kind of uses all directions, right? So you don't you allow more flexibility, and hence you can find a vector with smaller norm. And that is the whole idea that essentially if you're forced to fit noise, a smaller set can actually blow up your variance. So it has the opposite effect than for the case where you allow to sacrifice data fit. So this is basically the takeaway of this talk. The rest of it is just going to be trying to understand how well can you do in the middle between p equal to 2 and p equal to 1. And we also are going to see some results for p equal to 1 that basically prove that your rates are still very bad, even though you can get consistency. Okay, so I always mentioned these linear examples because that's easiest to think about. A lot of people are familiar with sparsity. So in the first part, I'll just show you some results for sparse ground truth and for p between 1 and 2. But more interesting, I find, is the second part, hopefully can get to, which is for nonlinear models, where the structure is going to be the filter size of convolutional models. We have both theory for kernel interpolators, and we have experiments for neural networks. And then we also study this kind of bias variance trade-off for rotational invariance for neural networks in some controlled experiments. Okay, so let's start with linear interpolators first. Linear regression setting, we've seen a lot already this week. So we look at Gaussian covariates isotropic. It's different than most other works that achieve consistency for spike covariances. And we have Gaussian noise. And importantly here is that we can only prove this for Gaussian covariates. Essentially, all of the results crucially rely on those, and we and a lot of other experts don't know yet how to extend this beyond. So this is an open question, but for Gaussians, we can show what I'm going to talk about next. And then we assume for this talk that W star is just 1, 0, 0, or just one sparse, but our results hold for all of S sparse ground truth, or S that is on the order of n over log d. Yeah, and so then the degree of overparameterization, instead of looking at the regime where d is of the order n, which we've seen a lot, right? So we saw a lot of asymptotic results there. We'll focus on the regime where d is of the order n to the beta, where you can actually achieve consistency. So when beta is bigger 1, d is bigger than n, and so you can interpolate, right? So as beta grows, we have more and more overparameterization. So the interpolators will compare our minimum LP norm interpolators, subject to y equal to xw, the interpolation constraint. And because we want to look at harmless interpolation, we also compare this with regularized estimators and their rates, in particular the lasso. Okay. And of course, I don't need to mention that minimal P norms are somewhat natural to study because of implicit bias results, in particular for classification, but also for some P for regression, in particular P equal to 2. But yeah. We also have results for classification for anything talking about today, basically logistic regression, or just say hard margin SVM, and for hard LP margin SVMs, but I won't talk about them, so otherwise it become too crowded. And the performance metric for regression here, there's the prediction error, which in the case of isotropic covariates is just the estimation error W hat minus W star L2 norm. Okay, so yeah, so the the right-hand side on this 3-plot slide before was basically varying the inductive bias strength, right? And I said for linear models, this just means varying p equal to 2 towards p equal to 1, between 1 and 2. That's what we study. This is our knob. P equal to 1 has strong inductive bias to sparsity, and p equal to 2 has no inductive bias towards sparsity. Previous work has focused on p equal to 2. And so today we will populate the picture beyond p equal to 2. But before we go there, I just want to briefly recap what's already known for p equal to 2. For p equal to 2, you look at the minimum L2 norm interpolator and the ridge regression estimate. You can compare these two. And what is nice about p equal to 2 is that you have a closed form solution. You can use random matrix theory pretty directly. That's also one reason people have studied this extensively. What we see for p equal to 2, these are just some very simple experiments for isotropic covariates, is that for d over n bigger than 1, we see both the second descent and we see harmless interpolation. Right? Harmless interpolation means the optimally regularized one and the interpolating estimator have the same MSE. In particular, if you have very high overparameterization, harmless interpolation holds. Okay, and the reason is that as you increase d over n, the variance drops. So if you remember Misha's result n over d, right? So as you increase d over n, this lower bound drops, and the lower bound is essentially coming from the variance in this case. So here, variance drops. So if the variance is really low, regularization is not going to help you anymore. So this is why you have harmless interpolation. So you can basically, the fact that variance decreases, you have implicit regularization, explains both second descent and harmless interpolation for p equal to 2. Okay, so we have these two, but we wanted good generalization as well. And then that's the problem with L2, is that the Bayes error is somewhere there, and because the bias is increasing, right, so you really have no clue where to search, the risk is also very high, much higher than the Bayes error and what you could get if you used Lasso, for example. And so for isotropic Gaussians, you have a very high bias and hence a very bad generalization and no consistency. Okay, so this setting is not satisfactory, and that's why we looked at p between 1 and 2. Okay, so here, p equal to 2, as I just pointed out, for high overpolarization, variance is small, but the bias is high. So the bias is driving the test error. So now let's look at p equal to 1 first. In this case, between p equal to 1 and 2, we don't have a closed form solution anymore. So the techniques that we'll use are essentially based on localized uniform convergence and CGMT, Gaussian min-max theorems, etc. Okay, so first for p equal to 1, a lot of you are familiar. If you have sparsity, then we know that encouraging a small L1 norm is going to help. Right, so matching strong inductive bias is small L1 norm. For noiseless case, basis pursuit, which is min L1 norm interpolation, gets you perfect recovery for an n of the order of S log d. But once you have noise, people usually look at the lasso, which is adding the regularization term with lambda non-zero, and then for the optimal lambda, you can get a minimax optimal rate. Okay, this is the story everybody knows. And so our question is now, what if we use basis pursuit on noisy data? So basically this combination, how much does basis pursuit suffer when it's forced to fit noise? So one question is, can we get consistency? And if yes, what's the rate? Okay, so this question has been lurking in the literature. There's essentially there's a gap between two kinds of results. So the first lower bound by Muthukumar et al. Was a lower bound that was saying it should be the lower bound is of the order sigma squared over log d over n. So if d is of the order n to the beta, essentially is a sigma squared over log n rate. So it should be consistent Whereas other works that have focused on adversarial noise, meaning the noise is adversarial, but it's consistent if it decreases with n, if the norm decreases with n. These kinds of results have basically conjectured that the upper bound should be constant. So for adversarial noise, their bounds are optimal, but the question is whether their bounds are also optimal for IID noise. So what we basically showed is that the lower bound was correct, so we could close the gap and actually get precise bounds even up to the leading constant factor. So we get the estimation error rate with high probability that is equal to sigma squared over log d over n. So we have a 1 over log n rate, essentially. Okay, the proof is based on some previous work by Köhler et al. And their results couldn't show consistency, but if we use some more tight analysis, we could get this result. Okay, so here's just a few remarks. So for one, we could only show it for Gaussians, but actually it holds for more distributions. We just don't know how to show it for beyond Gaussians. You could see exactly the 1 over log d over n rate for all the other distributions as well, like log normal and Rademacher. Okay, so as I said, we have a 1 over log n rate. We do have consistency, but we are far from harmless interpolation, right? Because we know that if we use the penalized version plus lambda L1 norm, we could get a S log n over n rate compared to 1 over log n. That's definitely not harmless. And that is because, as I mentioned in the beginning, it's because the variance is too large. Okay, so this is the picture now. So we've seen that we don't have consistency for p equal to 2, but for p equal to 1, we have a very slow rate, and we are still not generalizing well in the sense of compared to what we could achieve without interpolation. And here, the problem is the variance, whereas for p equal to 2, the problem was the bias. Okay, so we don't have harmless interpolation. There we have harmless interpolation, but bad generalization still. So for both cases, we're not happy. So the question is, let me just maybe skip this. So the question is now, can we get better rates in between? Since there seems to be a trade-off, there should be something like a U-curve again. And so if there's a U-curve, what is the best rate we can achieve? And how close do we get to the minimax optimal rate if we vary p in between 1 and 2? Okay, so here is just how I will present our results for p in between. So we use this kind of plot. On the x-axis, we have this beta, which is reflecting how much we're over-parameterizing. So beta equal to 1 is d of the order n, and otherwise is d of the order n to the 2 and 3, etc. Right? So the higher beta, the more over-parameterization we have. And on the left side, we have the rate exponent. Right? So we can get results if we plug in d of the order n to the beta into our theoretical bounds, which are quite complicated, so I'm not going to show them. But we can compute this rate exponent alpha. And this alpha will be non-zero and be actually smaller than 0, otherwise would it show this? And so for alpha equal to -1, this is equal to rate 1 over n, so that's really what this minimax rate optimal. And for alpha equal to 0, that's what we got with the interpolators for p equal to 1 and 2. So here, it's up to log factors. So basically, this 1 over log n term, we just say it's of the order 1 because we don't, like, log n is too slow for us. So we're just ignoring log factors here when I write this alpha. Okay, the question is how close can we get to alpha equal to -1 for p in between 1 and 2 in this graph? Okay, so here's the graph now populated with our rates. So we can get order matching upper and lower bounds. And so how the bounds are, like, these are theoretical plots. These points are theoretical. And so what does this tell us? So let's just fix a beta, just fix over-parameterization, and then vary p. What you can see is if you start with p equal to 1, you're at alpha equal to 0. But once you add a little bit, so P is 1.01, you immediately drop to a rate that's really close to the minimax optimal rate. Then now if you increase P again, then you get closer to P equal to 2, so you go back to this constant, inconsistent regime. And so if you look at beta equal to or close to 2, the rates can get arbitrarily close to 1 over n. And for classification, you can actually get it precisely, to get 1 over n precisely. Okay. So these are essentially, this is the illustration of our bounds when we plug in n to the beta for d. So our bounds are general for d and n, but I just plugged it in for illustration purposes. So what do we see in this plot? So from one, we also see this second descent, meaning after the interpolation threshold, the rates get better, generalization gets better, the test error drops. So this is essentially this test error drops kind of equivalent in terms of rates. And then we have harmless interpolation in the sense that we get very close to the minimax optimal rate, and also good generalization because we're close to the minimax optimal rate. So basically, adding a regularization is not going to help that much anymore if we choose a good P in between 1 and 2. So there are some caveats to our analysis. For one, I already said it only holds for Gaussians, and so that is a little bit disturbing because it does seem to hold more generally, we just cannot prove it. And yeah, we've been trying, but so because we crucially rely on the Gaussian minimax theorem, we're not able to show it in a different way. One caveat that also is the reason why we couldn't show experiments is that we require D to be really, really large, which is then hard to actually implement. So for example, P equal to 1.01, D needs to be basically 1 over log D needs to be 0.01. So D has to be really large to see these phenomena. Okay, so this is why we require this is because we need, in the analysis, we need to concentrate the LQ norm of Gaussians, and to get a high probability result, this is necessary. We don't know how to get around that either. Okay, these are just some technical caveats. Okay, but now on to perhaps some experiments. These are experiments for classification, since the classification results are a little bit more benign in the sense of how large the D needs to be. So here we just have a very synthetic experiment with isotropic Gaussians and a sparse ground truth linear. And what we see here is following, it's important to take away also for the second part. So first focus on the blue line. The blue line is when we have noiseless data. So for noiseless data, you have a sparse ground truth. Of course, you want to choose P equal to 1, right? So you want to enforce sparsity. Noiseless data always use the strongest inductive bias. So there's a big drop in terms of error between P equal to 2 and P equal to 1. So now if you add noise, which is the orange curve and the gray curve, sigma is the noise level, this is random label flips. In this case, you don't want to choose P equal to 1 here, but you want to go a little bit towards 2 to reduce the variance. Right, so the best point is going to be here somewhere close to 1.15 or something. So this is for synthetic data, and so we did an experiment also on a high-dimensional data set on leukemia data, and there the same kind of trend can be observed. So the blue line is if we don't add artificial noise, so it could be that's already noisy, but you know, we get pretty good accuracy, so maybe it's fine. So we just assume that this blue curve is some sort of proxy for noiseless data. So in this case, you also want to choose P equal to 1, the strongest inductive bias. So now if you add a little bit of artificial noise, the optimum of P is again shifting towards 2. Okay, so basically one takeaway from our theory, another way to think about the bias variance trade-off is that the strongest inductive bias is best for interpolating noiseless data, but medium inductive bias is best to interpolate noisy data. So you'll have these two kind of curves where the optimum shifts towards a weaker inductive bias. Now, I need to add that this is not a kind of constructive or methodological analysis or research, right? So we're not saying, please interpolate and please choose this kind of inductive bias, but we are saying, if interpolation ends up working, if you get an interpolator that generalizes well and you have very noisy data, it could be that it has kind of a medium inductive bias towards the simple structure of your ground truth. So this way around is how we would sell our result. So it's not saying you should use this method. Okay, so what's the full picture for the linear models for P in between 1 and 2? So for 1, what I just said, use the strongest bias for noiseless and medium bias for noisy. And the other one was this more kind of bias variance trade-off idea. And this is saying you kind of have harmless interpolation and not for the strongest inductive bias, but if you have some sort of medium inductive bias. So these two, A and B, these two conclusions, we will want to transfer also to nonlinear models. So for this, we need to, of course, discuss what is structure and what is strong inductive bias, and we'll do this now. Okay, so the first part will be on filter size of convolutional models, of convolutional kernels, and we'll show some theoretical results, and then we'll go to neural networks. So what are convolutional kernels? You can just consider for each x, so your covariate x that's d-dimensional, you look at patches of size q, right? So you have a d-dimensional vector, you look at patches that are q-dimensional, and you have d of them. And now your convolutional kernel is essentially dependent on inner products of the patches between the one covariate vector and another one, right? So k of xz is going to be an average of some function on the inner product of these patches. So the q is the filter size here, and and the kappa here that we allow needs to have some regularity, and that is satisfied by the exponential function, for example. Now for high-dimensional kernel learning, so we look at the regime where D is growing with n, and D and n grow together. And so here again, actually it's quite hard to analyze. So most works are focused on this kind of distribution, which is kind of uniform on this hypercube of thing where you only look at the vertices, -1, 1 to the power of d. So that is maybe not so satisfying. We conjectured that you can also get these results that I show you for uniform distribution of the sphere for a very particular kernel. Because for these, essentially, you can write down the eigenvalues, or you have a very tight characterization of the eigenvalues. And generally, this is not the case, and that's also one of the reasons why people have analyzed this particular distribution. So for high-dimensional kerneling where D is growing, it's actually pretty hard to have a very tight characterization of the eigenvalues for general distributions. And okay, but for this kind of toy model, with Gaussian noise, and for a ground truth that has a small, essentially only depends non-linearly on a small patch, we can try to see if these two conclusions that we had for linear models also carry over. So now it's important that the ground truth also satisfies the simplicity, right? So before we had the sparsity, and now we use filter size as some sort of proxy for structure. So small filter size, we assume that like essentially you can use a small filter size to learn F star, and hence a strong inductive bias would be an estimator or a kernel method that's based on small q. And then we compare kernels with different q's given a ground truth that only depends on L star coordinates. Okay, so here we are in the high-dimensional regime, which means that n and d grow together. So L is essentially the not overprecision. L is essentially the how large n is compared to d. Again, here we're not in linear regime. We're over-parameterized anyway because we look at kernels. So here this L is had nothing to do with over-parameterization. Then we have L sigma. This could be 0 if you have constant noise. So it's just more general. And then gamma is important because gamma is reflecting how strong your inductive bias is, right? So if gamma is small, this means you have a strong inductive bias towards small filter size. Strong inductive bias towards small filter size, yeah. Okay, so what we compare, so we want to see if harmless interpolation happens for a weak inductive bias and if basically what we saw before, a strong inductive bias prevents harmless interpolation, right? So we need to compare regularized estimators or ridge regularized estimators, KRR estimators with the interpolators, mid-norm interpolators in the RKHS. So that's what we do, and so the result looks kind of complicated, but I just want to throw it out. You don't need to parse. And what I'll show is actually just the graphical version of it. So our bounds are tight again, and this is important to make the statement that there is a trade-off, and otherwise if it's just an upper bound, you cannot actually say that much. So they are tight. And what we see here, first of all, is the result for the interpolator, which is this wiggly line on the blue line. And if you're familiar with the literature, you might be reminded of a paper by Liang, Rocklin, and Dai, who also showed multiple descent, or showed an upper bound for multiple descent as a function of over-parameterization. So here, on the x-axis, they actually had d over n. And they also saw some multiple descent. And so that is because of, well, very high level, it's because of the eigenvalue structure. As d grows, you will essentially have this sort of staircase structure, and that's what causes these wiggles. At the same time, if you disregard the wiggles, you'll see a trend that's going down, right? So the interpolator is somewhat getting a better rates, at least the minimas are getting better rates. And at some point, it matches the regularized, the optimally regularized estimator. So this is the yellow line here. So this is the KRR with the optimal chosen lambda. That is the rate that you get. Again, this is the rate is n to the minus alpha, n to the alpha, and alpha is between 1/2 and 0, or minus 1/2 and 0. So this should be n to the alpha here. Okay. But, okay, so just disregarding the wiggles, right? So if you just look at the high-level curve here, this blue line here and the yellow one, you can see again, for large gamma because if Q is of the order D, you essentially don't have any real filter size, you just use the entire covariate vector in your kernel, so you essentially don't have that much of structure. In the case of very weak inductive bias, you have harmless interpolation, whereas when you have strong inductive bias, using a small filter size, you have a big gap between optimal regularized and interpolating estimator. So we see the same thing, and the reason is also a bit similar, that as you increase the inductive bias, i.e. the smaller the filter size gets, the variance grows, as we saw in the p equal to 1 case. So p equal to 1 was here, and the variance was growing, and the bias was decreasing. Okay, then there was another result that I just added yesterday because of Misha's talk. We can also show that for, is this the right way around? Yes. For weak inductive bias, that fitting noise is actually necessary, and not just that it doesn't hurt. So in order to present this result, we need to define a couple of things. So first of all, lambda star is the optimal lambda for your KRR to get the optimal risk bound for a given choice of L sigma, the noise, N, and the filter size. You have this optimal lambda star. And then gamma star is basically separating this plot into weak inductive bias and strong inductive bias. So if you're on the right-hand side, so if gamma is bigger than gamma star, then you're in the weak inductive bias side. Okay, so the theorem then says that the training error, the expected training error in probability converges to some tau times sigma squared. And if I'm in the strong inductive bias regime, this tau needs to be 1. And if I'm in the weak inductive bias case, the tau is smaller 1. So the optimally regularized one has to fit noise a little bit. Otherwise, it's not the optimal lambda star. Okay, so what tau equals to 1 means that just basically says don't fit my noise to some extent. Right, don't fit my noise means is the same as basically saying ignore the noise and just try to focus on your structure. So that's the usual regularization regime that we are used to, right? So you should not fit noise, just try to circumvent it somehow. Okay, so this is what I already said. And yeah, so this is an experiment on CNNs. I will show later in a couple of slides which particular experiment I mean here. But basically, we saw for a particular kind of CNN and image data that this exactly happens, is that if your filter size is very large, then you will need to fit the noisy subset of the training set, because it's synthetic, so we can actually define noise, like noisy labels and non-noisy labels. We know this in advance. So the training error on the noisy subset has to be 0, which means we have to perfectly fit noisy data. But if you go into the regime where you have a strong inductive bias, you really should ignore the noise. Right, so this because the training error on the subset being 100% means that I have not fit the noisy data points at all. Okay, so what is this CNN and image data set that I was showing? Well, we had some difficulty trying to think about a controlled experiment that really captures our intuition. And so we were thinking of essentially some sort of synthetic data sets where we know that the ground truth only depends on very few pixels, and so the filter size required is really small. And so here we have circles versus crosses on some images. And the neural network we use is really a very simple one-layer convolutional network. But for this one, so in order to see any kind of phenomenon that is transferring from our intuition in the linear case, you really need to be careful there, because it really hinged on the fact that the ground truth had a particular structure. And so it wasn't clear to us that any natural image would have that particular structure of small filter size being the optimal estimator. So that's why we had to use this synthetic data set. And so on this one, we could actually see as well on this nonlinear model that, first of all, if you don't have noise, then always use the smallest filter size. And once you add artificial noise, 20%, then the interpolator needs to, basically, you should use a filter size that's in between the smallest one, 5, and the largest one. So you go towards a larger filter size. And also, the other thing is that there is no harmless interpolation for strong inductive bias, and there is harmless interpolation for weak inductive bias, which is large filter size. Okay, so beyond filter size, we're thinking, okay, how can we go to a bit more natural images? Because the synthetic circles and crosses was a little bit unsatisfying. So we're thinking about maybe rotational invariance could also be a structure that is interesting or natural in image data sets. So what kind of images should be completely, okay, so for which kind of image data sets should the optimal classifier be invariant to rotations? And so we thought that this kind of data set called Eurosat, satellite images, should definitely be in that category. In particular, So there, the task is given some picture of a satellite image. You have to label whether it's a residential area or agriculture, etc. So these are the labels, and so it really shouldn't matter what your orientation is in order to label a satellite image in this way. And so now the question became, okay, this should be a structural simplicity that makes sense for images, but how do we vary the strength of inductive bias? Right, because we do not have like a particular optimization algorithm that gives us an interpolator that is, has some sort of invariance. It's not an implicit bias kind of result. It's not like a min-norm thing as in the linear case and in the kernel case. It's not that easy. So how we thought about varying the strength is via the amount of data augmentation. So the number of rotations that we add to the regularizer, or the consistency regularizer, essentially. Right, so for each image, we would add k, I think, or k number of rotated versions of the same image, and say, please also predict the same label on these rotated images. And that's the number of rotations that we add, or the more like how fine the grid is our strength of inductive bias. This is the best we could think of, but very happy to hear if anybody else is more interesting or even more practical ideas here. And again, for this rotational variant experiment, we see the same thing, which is the number of rotations. As I mentioned, if we have a lot of rotations, we have a strong inductive bias towards rotational variance. And if we only, so for rotation equal to 1 is just the original image. And then we see if, in the noiseless case, you really want to use, for the interpolator, as many rotations as possible. But once you add noise, so I'm comparing this one, the interpolator, right? So the dashed blue line is best for the optimum, the largest number of rotations. But once you add noise, then you want to move towards fewer rotations. And this has been observed previously before. Once you add data augmentation and you have noise, then you should not interpolate anymore, and you should already stop. And there's actually a big gap. Oh, okay. Okay. There's a problem. So, yeah. This was basically also what I had, but are there any questions, maybe, in the meantime? Okay, so since they're not, I'll continue. Just a recap, right? So we started with the linear models. We had these two conclusions from theory and also in experiments. And then we went to kernels. We had the same for the structure that is filter size, and also these two observations for another structure that is rotational variance. So of course these are only preliminary results. I wouldn't say this claim is very general, but this seems to be one possible ingredient in trying to understand when interpolation works for noisy data. So this kind of structural bias perspective. Okay, so this is just a summary of the story. So the main takeaway is that we have this inverse bias variance trade-off as a function of the strength of the inductive bias when we are forced to fit noise. So when the training error is forced to stay at 0. Then in this case, the strongest inductive bias is good for noiseless data, but then for noisy data, you would want to be in the middle to have a medium inductive bias. And so here are still some open questions. So as I already mentioned, we only can show it for Gaussians, and it's very difficult to go beyond. For nonlinear, of course, how do you, again, go beyond toy distributions on the kernel, like -1? uniform distribution -1 to the power of d is kind of toy. How do you go beyond? And then the other question, of course, is neural networks. Can you prove something about those? But the experts are in the audience. And I'm personally also very interested if you have any other ideas how to test the hypothesis that we postulated for the linear case and then tested for a couple of structures. What kind of structures could also be interesting to try our hypothesis on for neural networks or for anything else? Maybe also graph neural networks, maybe some other kinds of structures. So yeah, so this is, these two papers are the ones I primarily talked about. And these are the L1 results, and these are the structural bias results. So yeah, so now I want to thank you, everybody, for staying until so late in the last talk, and again, for the organizers for this wonderful workshop.
Thank you, Fanny, for the great talk. Are there any questions from the audience?
Very nice talk. I have a question about this. So you said that the lower bound, there was optimally regularized predictor whose training loss was below the noise level, right? Can you say a little bit more about that?
Yeah, that slide was for you. No, that's too fast. For the kernels, yeah, why am I going to the linear ones? For the kernels. Yeah, so we have results for every lambda. So for every lambda, we can show, we get tight bounds for the regularized estimator. Here. So for every L lambda, which is the order of the lambda as a function of d, we can get tight risk bounds, and then we just kind of minimize, take the lambda that minimizes the sum of both. And so that's our lambda star, right? So because the bounds for every lambda are tight, that's why you can get this necessity, essentially.
And how much lower than the noise level it is?
Yeah, that is a very complicated expression, this tau gamma.
But can you say it's like 0.5 the noise level or something? Can you get some separation from 1?
Yeah, but I'm not entirely sure. We didn't numerically calculate it. But
all right. Thanks, very nice.
Thanks.
You showed that changing the inductive bias, changing the inductive bias, you find that with noisy inputs, noisy data set, you get better results with less inductive bias. So is that, do you think that works in reverse order? Like you could find if there is noise in data by changing the inductive bias.
Can you repeat the last sentence?
Okay, so can you find if there is a noise in the data by changing the inductive bias?
I see, that's an interesting question. Yeah, well, we don't have the theoretical results, but experiments kind of show. But you're basically saying, okay, you could vary the inductive bias, and if the strongest one is the best, then maybe that means that you don't have noise. Yeah, maybe you can try experimentally, but yeah, it's not a theoretical result.
Yeah, thank you.
Thanks, that's a very interesting talk. You said just for the linear case, you had the p between 1 and 2. Do you have a specific model where you get p between 1 and 2 as an implicit bias? Because I know like p equals 1 and 2 you can get in linear diagonal models, but is there...
You mean like implicit bias, whether you get
P between 1 and 2? Do you
Yeah,
have
so no, we just looked at the actual, like, the optimal solution. We didn't look at the optimization procedure towards that.
Okay, just I want to say, because the model I showed in my talk, the last part, in linear diagonal models, you actually get P between 1 and 2. So
yeah, cool.
So if you get, like, for depth 2, you get P equals 1, and as depth goes to infinity, you go to 2.
Okay, yeah, nice.
So that may be a case that
cool.
could be useful that I need to check.
Yeah, thanks.
Further questions? Let's thank Fanny for the great talk once again.
Thank you.
So that's the last talk of the day. Before we adjourn to the poster session, I want to invite Philip Purnell from MBZU AI up to the stage to just provide a few small gifts to various folks involved with the workshop. First, Philip wants to recognize a few of the folks in the community whose leadership is both directly and indirectly